This video introduces vectors and basic operations on them. A vector is a quantity with direction and magnitude. Magnitude is also called length. Vectors are usually drawn with arrows. The tail end is called the initial point, and the tip of the arrow is called the terminal point. Two vectors are considered to be the same if they have the same direction and the same length. The position of the vector, that is, where it's drawn on the plane or in space, doesn't matter. Please pause the video and decide, for each pair of vectors, are the two vectors equivalent? The first two vectors are equivalent because they have the same direction and the same length, even though they start and end at different points. The next two vectors are not equivalent to each other. They have the same length, but they point in opposite directions. In fact, if we call the first vector A, where the decorative arrow at the top is a way to represent the fact that it's a vector, then we'll call the second vector, the one that has the same length but points in the opposite direction, we'll call it negative A. The next pair of vectors also are not equivalent to each other. They have the same direction, but they have different lengths. A scalar is another word for a real number, like 5 or pi. A scalar does not have a direction, in contrast to a vector, but it does have a size or a magnitude. Now that we've defined vectors, we can talk about adding them together. If we have a vector A and a vector B, we can define the vector A plus B as follows. First, we move the vectors so that they're end-to-end. In other words, the terminal point of A coincides with the initial point of B. Then, we draw a straight line from the initial point of A to the terminal point of B to complete the triangle. That's our vector A plus B. There are other equivalent ways to find A plus B. For example, we could move our vectors A and B so that they share the same initial point. Then we draw the parallelogram with sides given by A and B, and the diagonal of this parallelogram is the vector A plus B. If we superimpose our two pictures, we can see that they really are equivalent. This is also a good way to see that A plus B is the same as B plus A. Suppose we wanted to draw A minus B instead of A plus B. Well, A minus B is the same thing as A plus negative B. And we know that negative B is just B pointing in the opposite direction. So we can line up A with negative B and connect the initial point of A with the terminal point of minus B, and we get our vector A minus B. Later, we'll see another way of defining A plus B and A minus B in an algebraic instead of geometric manner. It's also possible to multiply scalars and vectors. If we start with the vector A, then the vector 2A goes in the same direction, but is twice as long. The vector negative 3A goes in the opposite direction because of the negative, and is 3 times as long. The vectors I've drawn are only rough approximations. To get a more accurate representation, I'd need to use a ruler, or put my vectors on a coordinate grid. In the next part of the video, I'll be using coordinate grids for the vectors. If we place the initial point of a vector A at the origin, then the vector can be completely described by giving the x and y coordinates of the terminal point. For example, this vector has a terminal point at an x-coordinate of 3 and a y-coordinate of 4. And we can unambiguously describe the vector as the vector with initial point at the origin and terminal point at the point 3, 4. A shortcut for writing all this out is just to say that the vector has components 3, 4, and we write the 3, 4 with this angle bracket notation. So the components of a vector are just the x and y coordinates of its terminal point when the vector is written with its initial point at the origin. If the vector is written with its initial point somewhere else, like for example right here, then we can't just read off its components by looking at its terminal point. Instead, we have to first shift the vector so its initial point is at the origin, and then we can look at the x and y coordinates of its terminal point, which here are 3 and 2. So this vector, I'll call it B, has components 3, 2. And it still has those same components, even if we draw it way down here. Vectors can also be drawn in three-dimensional space, as well as in a two-dimensional plane. In this case, the components of the vector in 3D are the x, y, and z coordinates of the terminal point of the vector when its initial point is at the origin in 3 space. Please pause the video for a moment to find the components of the vector that starts at the point 3, 1 and ends at the point -2, 5. By moving the vector so that it starts at the origin, we can see that it extends -5 in the x direction and 4 in the y direction. So its components are -5, 4. In fact, we could have predicted that without physically moving the vector. The difference in x coordinates tells us how far the original vector extends in the x direction, and the difference in y coordinates tells us how far the original vector extends in the y direction. So we know our vector should have components -2 minus 3 in the x direction and 5 minus 1 in the y direction, which is just what we got before. And in general, the components of a vector that starts at a point x1, y1 and ends at a point x2, y2 are x2 minus x1, y2 minus y1. A similar statement can be made for vectors in 3D with 3 components. We can also talk about vector addition and subtraction and scalar vector multiplication algebraically in terms of components. Given 2 vectors, A and B, defined in terms of components, and a scalar C, we can define A plus B by adding the components together. A1 plus B1, A2 plus B2. Similarly, to find A minus B, we subtract the components, and to find the scalar C times the vector A, we multiply C by the components of A. Similar formulas hold for 3-dimensional vectors. So, for example, if we want to add the vector 1, 2, 3 to the vector 5, 7, 12, then we get the vector with components. Let's see, 1 plus 5 is 6, 2 plus 7 is 9, 3 plus 12 is 15, which also happens to be 3 times the vector 2, 3, 5. Now you might be wondering to yourself, we've defined vector addition, subtraction, scalar multiplication now in 2 different ways. First, by drawing arrows, and second, in terms of components. So why are these 2 definitions equivalent? We can get a sense for why the definitions of addition are equivalent by looking at this picture. If A has components A1 and A2, and B has components B1 and B2, then the vector A plus B extends over in the x direction by A1 plus B1 and extends up in the y direction by A2 plus B2. So the vector addition in terms of drawing arrows works out the same as the vector addition in terms of adding components. We can also see that the two definitions of scalar multiplication work out the same. If we start with the vector a and draw, for example, 3 times a, then whatever the components of a are, we'll call them a1 and a2, the components of 3 times a are going to be 3 times as big. So scalar multiplication also works out the same, whether we think about it in terms of drawing arrows or multiplying components. Many of the properties that we know and love from arithmetic still hold for vectors. For example, addition is commutative. A plus b is the same thing as b plus a. Addition is associative. We can group in any order we want and still get the same answer. There's a zero vector whose components are all zeros. And when we add 0 to any other vector, we just get the same original vector. Vectors have additive inverses, or negatives. And when we add a to its negative, we just get the 0 vector. All components become 0. Just like in arithmetic, we have the distributive property for multiplication over addition. And there's a second distributive property. If we add 2 scalars and multiply by a vector, we can distribute that as well. Scalar multiplication is associative and can be grouped in different ways, still yielding the same result. And there's a scalar multiplicative identity, which is, you guessed it, 1. If you multiply the scalar 1 by any vector, you just get the same vector you started with. All of these properties can be proved algebraically by writing things in terms of components, or geometrically by drawing vectors as arrows. But I'll omit the proofs here. This video introduces the idea of vectors, which can be represented either with arrows or in terms of components. We used both representations to work out ideas of adding vectors, subtracting vectors, and multiplying vectors by a scalar. This video is about finding the length of vectors, finding unit vectors, which are vectors of length 1, and working with a special collection of unit vectors called the standard basis vectors. The length of a vector W is denoted with these double absolute value signs, or some sources will use just a single absolute value sign instead for length. If the vector has components W1, W2, W3, then the length is given by the square root of W1 squared plus W2 squared plus W3 squared. This vector has 3 components, so it's a vector in 3D. If instead we had a vector in 2D, say with components V1, V2, then its length would be given by the square root of V1 squared plus V2 squared. If these formulas for the length of vectors remind you of the distance formula, you're exactly right. If we draw our vector in 2D and put its initial point at the origin, so here's V with components V1 and V2, since its initial point is at the origin, its terminal point will just be at the point with coordinates V1, V2, and so you can use the distance formula to find the length. The distance formula is just the square root of the difference in x coordinates squared plus the difference in y coordinates squared. So that's v1 minus 0 squared and v2 minus 0 squared, since this initial point is at 0, 0. So that's exactly the same thing as the length of the vector. And you can do a similar distance formula argument to see that a vector in 3D, its length, given by the distance formula, gives us this formula here. The length of a vector is also sometimes called its magnitude or its norm. A unit vector is a vector of length 1. So, for example, the vector A with components 3, 4 is not a unit vector. because the length of A, which is the square root of 3 squared plus 4 squared, is 5, which is not 1. But what if we wanted to find a unit vector in the same direction as A? Well, since A is 5 times too long to be a unit vector, the simple thing to do is just multiply A by 1/5. So 1/5 times A is 1/5 times the components 3 and 4, so that's 3/5, 4/5. We can check the length of this vector 3/5, 4/5 is going to be the square root of 3/5 squared plus 4/5 squared. I can factor out a 1/5 squared from each of these terms and rewrite this as 1/5 times the square root of 3 squared plus 4 squared, or 1/5 times 5, which is 1. Notice that to turn A into a unit vector, we divided by the norm or length of A. Or in other words, multiplied by the reciprocal of the norm of A. This same technique works anytime we want to find a unit vector in the direction of a given vector. So we've already answered this question. To rescale any vector v to make it a unit vector, we just multiply v by 1 over the length of v. This process of rescaling a vector to make it a unit vector is also called normalizing the vector. Please pause the video for a moment to find a unit vector that has the same direction as this vector with components 5, 1, 3. Well, since the length of our given vector is the square root of 5 squared plus 1 squared plus 3 squared, that's the square root of 35, we need to take our vector and multiply it by 1 over the square root of 35. That can be written in components as 5 over the square root of 35, 1 over the square root of 35, 3 over the square root of 35. So this is our unit vector. There's a particular collection of unit vectors that's very handy to work with, and these are the standard basis vectors. In 2 dimensions, the standard basis vectors are the vector 1, 0, we call that the vector I, and the vector 0, 1, which we call the vector j. If we draw these 2 vectors on the coordinate plane with their initial points at the origin, then the vector I goes in the direction of the x-axis, and the vector j goes in the direction of the y-axis. In 3 dimensions, the standard basis vectors are denoted I, j, and k, and they have components 1, 0, 0 for I, 0, 1, 0 for j, and 0, 0, 1 for k, and I, j, and k are the vectors that extend along the direction of the x-axis, the y-axis, and the z-axis, respectively. Note that all of these vectors are unit vectors. They all have length 1. Any vector can always be written in terms of sums of multiples of standard basis vectors. For example, if we wanted to write the vector with components 3, negative 2, 7 as a sum of multiples of standard basis vectors, then we want to write it as something times I plus something times j plus something times k. It's not hard to see that if we just use the components here and put them in the blanks, 3, negative 2, and 7, and then work this out, we get 3, 0, 0 plus 0 minus 2, 0 plus 0, 0, 7, which is 3, negative 2, 7, like we want. So the vector with components 3, negative 2, 7 is the same thing as 3i minus 2j plus 7k. And in general, a vector with components, say, v1, v2, v3, can easily be written as v1i plus v2j plus v3k. A similar statement can be made for vectors with two components. In this video, we use the distance formula to find vector length. We defined unit vectors, which are vectors of length 1, and we notice that if we take a vector and multiply it by the scalar 1 over its length, then this gives us a unit vector in the same direction as the original vector. We also introduced the standard basis vectors I and j, or I, j, and k in 3 dimensions, and showed that any vector can be written in terms of standard basis vectors. This video introduces the dot product of two vectors. Suppose the vectors a and b are given in terms of components. Then the dot product, a dot b, is given by multiplying together corresponding components and adding them up. That is, a dot b is a1 times b1 plus a2 times b2 plus a3 times b3. A lot of textbooks will write the dot product using a dot. I tend to write it with a symbol of a circle instead, just to distinguish it from ordinary multiplication of scalars. Let's find the dot product of these two vectors. Well, let's see. 4, 2, negative 1 dotted with 7, 0, 5. I just multiply together corresponding components and add them up. So that's 4 times 7 plus 2 times 0 plus negative 1 times 5, which adds up to 23. Notice that the dot product of two vectors is a scalar, not a vector. Although I've defined dot product for vectors with 3 components, so 3-dimensional vectors, it's also possible to define dot product analogously for 2-dimensional vectors or even n-dimensional vectors. I'll write it out for 2-dimensional vectors. If the vector c has components c1, c2, and d has components d1, d2, then the dot product c dot d is, as you would expect, c1, d1 plus c2, d2. Dot product satisfies some handy properties. First of all, it's commutative. That means a dot b is the same thing as b dot a. This follows from the fact that regular multiplication is commutative, because if we write it out into components, a dot b, that means a1, a2, a3 dotted with b1, b2, b3. That's a1, b1 plus a2, b2 plus a3, b3. Well, I could use the fact that multiplication is commutative to rearrange that multiplication. So that's b1, a1 plus b2, a2 plus b3, a3, which is the same thing as b1, b2, b3 dotted with a1, a2, a3, in other words, b dot a. So dot product is commutative. Dot product satisfies the distributive property. If I take a dotted with b plus c, that's the same thing as a dotted with b plus a dotted with c. I won't write out the justification for this one, but I encourage you to try it yourself. The fact that dot product is distributive just follows from writing it all out in components and using the fact that regular multiplication and addition are distributive. There's an associative property for dot product, but it might not be the thing that first springs to mind. What might first spring to mind for me, thinking about associative property and dot product, I might want to write down something like a dot b dot c is equal to a dot b dot c, like this. But in fact, this does not make sense. The reason it doesn't make sense is because b dot c is a scalar, but a is a vector, and you can't dot a vector with a scalar. So instead of doing this, to write down associative property, we have to combine both scalar multiplication together with dot products. So if C, for example, is a scalar, then we can write down C multiplied by A dot B. Because now A dot B is a scalar, we're just multiplying two scalars, two numbers together, so that makes sense. And this is the same thing as C multiplied by A dotted with B, which is also the same thing as A dotted with C multiplied by B. So this is the associative property for dot products and scalar multiplication. And again, you can justify it by writing everything out in terms of components. What happens if you take the 0 vector and dot it with another vector? Well, the 0 vector is just the vector whose components are all 0. If you dot that with any other vector, you just get a bunch of zeros added up, which is the 0 scalar. So the 0 vector dotted with any vector is the 0 scalar. Now, what happens when you take the dot product of a vector with itself? Well, let's see. If I have a vector and I write it out in terms of components, and I take the dot product of that vector A with itself, I just get A1 squared plus A2 squared plus A3 squared. Hey, I recognize that. That's just the square root of A1 squared plus A2 squared plus A3 squared squared, or in other words, the norm of A squared. So we have the fact that A dotted with itself is its length, magnitude, or norm squared. This fact will come in handy in the future. So far we've defined dot product in terms of components, but dot product can also be defined in terms of magnitudes and angles. If we have two vectors, A and B, and theta is the angle between them, then it turns out that the dot product of A and B is equal to the magnitude of A times the magnitude of B times cosine of that angle between them. Note that there are actually two angles that you could use for the angle between these two vectors. You could use this one, or you could use this big one here. But it doesn't actually matter which angle you plug into your formula, because cosine of 360 minus an angle, so that's that bigger angle, is the same thing as cosine of the angle. Let's use this alternate definition in the following example. Suppose V and W meet at a 45-degree angle and have lengths of 4 and 6 respectively. Then the dot product, V dot W, is given by the length of V times the length of W times cosine of the angle between them. So that's going to be 4 times 6 times cosine of 45 degrees. Well, that's 24 times the square root of 2 over 2, or 12 square root of 2. In this example, we use the length and the angle to find the dot product, but can also turn things around. And if we're given the dot product and the length, we can use that to find the angle between the two vectors. Here, we still know that A dot B is the length of A times the length of B times the cosine between them, but now we're given that the dot product is 20 and the lengths are 10 and 4, so it's easy to solve for cosine of theta as 20 over 40, or 1/2. Based on the unit circle, we know that an angle with cosine of 1/2 corresponds to an angle of pi over 3, or negative pi over 3. So we can say that the angle is pi over 3, or 60 degrees. A negative angle doesn't really make sense in this context. The same ideas used in the previous problem can be generalized. In general, if theta is an angle between two vectors A and B, then cosine of theta is equal to A dotted with B divided by the length of A times the length of B. This follows easily from the fact that A dot B is given by this formula and simply solving for cosine theta. So if we want to find the angle between these two vectors, we can start by computing cosine of that angle as the dot product divided by the length. This works out to 20 divided by the square root of 14 times the square root of 53. Working out the cosine inverse of this quantity gives us an angle of about 42.76 degrees, or about 0.7463 radians. In this video, we saw two different definitions of dot product, one in terms of components and another in terms of magnitudes and angles. Both these definitions together give us a handy way of calculating the angle between two vectors when all you know is the components. Namely, we can use the second definition to find the cosine theta in terms of the dot product and the lengths, and use the first definition to actually calculate the dot product. Now, you may be wondering, are these two very different definitions of dot product actually equivalent? Will they actually give the same answer for any possible vectors? Well, yes, they are. But to see a justification for why that's true, based on the law of cosines, you'll need to watch the next video. We've seen that there are two possible definitions for the dot product of two vectors. The first definition is in terms of components. So if v and w are two vectors with the following components, then the dot product v dot w is obtained by multiplying corresponding components and adding them up. The second definition is given in terms of the length of the two vectors and the angle between them. The dot product v dot w is equal to the length of v times the length of w times cosine of the angle between them. In this video, I'll use the law of cosines to show that these two definitions always give the same answer. I've written down the two definitions of dot product for reference. I'm going to assume the component definition of dot product and prove that the other formula for dot product will hold. This will show that the two definitions are equivalent, because whatever a number I get as my answer for the component definition, I'll get the same answer for the other definition. Although I'm working here with two-dimensional vectors, vectors with two components, the argument actually still holds for vectors in 3 dimensions or n dimensions. We'll need to use a few properties of dot product that follow readily from the component definition. We'll need to use the fact that dot product is commutative. So for any vectors a dot b is equal to b dot a. We'll need to use the fact that dot product is distributive over addition. And we'll need to use the fact that when you take the dot product of a vector with itself, that's just the norm of the vector squared. These 3 properties follow immediately from the component definition of dot product, just by writing out all the vectors in terms of their components. Now we'll get started on the main part of the proof. Let me draw any two vectors, v and w, and I'm going to connect the terminal point of v to the terminal point of w with a new vector. I'll call it u. Notice that v plus u is equal to w, and so we can write u as w minus v. Now, by the law of cosines, we know that the length of u squared is equal to the length of v squared plus the length of w squared minus 2 times the length of v times the length of w times cosine of theta, where theta is the angle of the triangle opposite vector u. So that's the angle here between v and w. If I rewrite u as w minus v, I get this equation. Now I'm going to use the fact that the dot product of a vector with itself is the norm of the vector squared to rewrite the norm of this vector as the dot product of the vector with itself. Continuing, I can write the norm of v squared as v dot v and the norm of w squared as w dot w. Now I can use the distributive property on this collection of vectors to get w dot w minus w dot v minus v dot w plus v dot v. The right side I'll leave the same. Now if I cancel out like terms on the left side and the right side and rewrite this negative w dot v minus v dot w, that's the same thing as minus 2 v dot w, using the fact that dot product is commutative. So now I have this equation, and dividing both sides by negative 2, I have exactly the relationship that I was looking for. So the law of cosines gets us from the component definition of dot product to the length and angle definition of dot product. And that's all for the proof that these definitions are equivalent. This video gives an introduction to the cross product of two vectors. The cross product is defined for vectors in 3 dimensions. If we're given two vectors in terms of their components, then we can define the cross product as the determinant of the following expression. We put the vectors I, j, and k at the top, and then we put the components of vector A and the components of vector B in that order. Then we compute the determinant as we would with any matrix. One way of doing this is by expanding along the top row. By that, I mean we take the first entry here, I, and we multiply it by the determinant of the submatrix A2, A3, B2, B3 that we would get by crossing out the row and column that I is in. Then we subtract the vector j times the submatrix, determinant of the submatrix A1, A3, B1, B3 that we would get by crossing off the row and column that j is in. Finally, we add the vector k times the determinant of the submatrix A1, A2, B1, B2 that we would get by crossing off the row and column that k is in. Notice that the positive and negative signs alternate, plus I, minus j, plus k. Now we evaluate these little 2 by 2 submatrix determinants by just multiplying down the diagonal from the top left to the bottom right and then subtracting the other diagonal. In other words, we get I times A2 B3 minus B2 A3 minus j times A1 B3 minus B1 A3 plus k times A1 B2 minus B1 A2. If we don't like the negative j here, we can factor it through and rewrite our cross product as follows. I'll rewrite it one more time using component notation and cleaning it up to make the a's always before the b's in each of these products. So this fairly complicated formula is the formula for the cross product of A cross B, but as we'll see, it's worth the trouble because the cross product has some very nice features. First, let's get a little more familiarity with the cross product by computing an example with numbers. So if I want to find A cross B for these two vectors, I'm going to take the determinant of I, j, k, and I'll just fill in the components of my vectors here. And now I'll expand out along the top row, and I get I times the determinant of 2, 3, negative 1, 10, because that's what I get when I cross out the row and column for I, it just leaves that submatrix. And now I do minus j times the submatrix I get by crossing out that column and that row. So that's 1, 3, 5, 10, and then plus k times the term of the submatrix I get by crossing out that row and that column. So that's 1, 2, 5, negative 1. And now I'll compute the determinants of the submatrices. So this is 2 times 10 is 20 minus negative 3. So that's, I'll just write 20 minus negative 3 minus j. Here I have 10 minus 15. And I have plus k times negative 1 minus 10. And that simplifies to I times 23, or 23i, plus 5j minus 11k. So my cross product vector is given by that answer. I'd like to list some important properties of cross product. I won't prove the properties here, but I will prove them in a later video. The first property has to do with the length of the cross product vector. If theta is the angle between the vectors a and b, so I'll draw that. Here's a, and maybe here's b, and theta is this angle here. We want to be sure to choose theta to be the smaller angle between a and b, the angle that's between 0 and pi radians. So in the picture, we want theta to be this angle and not the larger angle around here. So if we do that, then it turns out that the length of the vector a cross b is equal to the length of a times the length of b times sine of theta. Notice that when theta is between 0 and pi, sine of theta will be positive, so this expression will be positive. So it's at least plausible that it could represent the length of the vector a cross b, which is also a positive number. So this property tells us about the length of a cross b. Now the next two properties are going to tell us about the direction. First of all, it turns out that the vector a cross b is perpendicular to both a and b. So as a picture, if this is the vector a and this is the vector b, and here's the plane that contains both those vectors, then the vector a cross b must be perpendicular, sticking straight out of that plane somewhere. And even if we specify the length of a vector perpendicular to a and b, as we do in this formula, there's still two options, because the vector could point in this direction, or it could point in the opposite direction. Well, it turns out that the direction of a cross b is given by the right-hand rule. What I mean by that is if I arrange the two vectors so that they share an initial point like they do in this picture, and I put the palm of my right hand at that common initial point, I point the fingers of my right hand in the direction of A, and then I curl my fingers towards the direction of B. If I do that with my right hand, then whatever direction my thumb ends up pointing, that's the direction of A cross B. So in this case, A cross B should be pointing up out of the plane. And if instead my vectors are arranged like this, now when I curl the fingers of my right hand in the direction from A towards B, my thumb ends up sticking down out of the plane, so A cross B will be in this direction instead. These three properties of cross product give us a way to characterize cross product geometrically in terms of length and direction. Finally, let's use these geometric facts and formulas in this example. We have two vectors, vector A and vector B, whose magnitudes are given. We're also given an angle of 210 degrees between them. We want to find the magnitude of A cross B and decide if it's directed up out of the page or down into the page. Well, to figure out whether it's directed up or down, we can use the right-hand rule. So I'm going to put the palm of my hand at the common initial point of A and B, put the fingers of my right hand in the direction of A, curl my fingers towards B, and when I do that, the thumb of my right hand points up out of the page. So I'm going to circle out of the page, and I invite you to try it yourself. Now, to find the length of A cross B, we can use the formula from the previous page. It says that this is the length of A times the length of B times sine of theta, where theta is the angle between the two vectors, but it's got to be an angle between 0 and 180 degrees. So it's not the 210 angle, it's this angle right here, which is 360 minus 210. So theta is 150 degrees. Now, if I plug all my information into this formula, the length of A is 5, and the length of B is 10, and that's times sine of 150 degrees. Sine of 150 is 1/2, so I have 50 times 1/2, which is 25. So A cross B is the vector that points straight up out of the page with a length of 25 units. In this video, I gave a formula for A cross B in terms of components, and I also gave a way to think about A cross B geometrically. A cross B is perpendicular to A and B, with its direction given by the right-hand rule. In addition, the length of A cross B is equal to the length of A times the length of B times sine theta, where theta is the angle between 0 and 180 degrees between A and B. These facts about length and direction completely determine the vector A cross B. This video proves two facts about cross product and gives an informal justification of a third. It proves that the length of the cross product is given by this formula, and also proves that A cross B is perpendicular to both A and B. The video gives an informal justification of the fact that the direction of A cross B is given by the right-hand rule. First, let's prove the length formula. A cross B is defined in terms of components as the determinant of this matrix. Here, A1, A2, and A3 are the components of A, and B1, B2, B3 are the components of B. If I expand this out, like I did in the previous video, I get the following expression. Now, if I take the length of A cross B squared, I can get that by squaring each component and adding them up. So that looks like the following. Please pause the video and expand everything out algebraically. You should get the following. You can check that this mess can be rewritten as A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared minus A1B1 plus A2B2 plus A3B3 squared. To check that, you need to multiply all of this out and then cancel terms. Now this last line can be rewritten as the length of A squared times the length of B squared minus the dot product, A dot B squared. But we know the dot product can be written as the length of A times the length of B times cosine theta, where theta is the angle between A and B. So substituting that into my expression, I get this. And now I'm going to factor out the length of A squared times the length of B squared from each of my two terms. So that gives me 1 minus cosine squared theta. Notice that it's no problem to factor out the length of A squared times the length of B squared from this term, since the whole thing is squared. Finally, 1 minus cosine squared theta is the same thing as sine squared theta. Now the equation that we want follows directly by taking the square root of both sides, provided that sine of theta is positive, which it will be if theta is between 0 and pi. And that completes the proof of the length formula. Next, Let's prove that the vector a cross b is perpendicular to both a and b. We're going to use the convention that the 0 vector is perpendicular to every other vector. So that way, if a cross b happens to be the 0 vector, then a cross b will be perpendicular to a and perpendicular to b automatically. So now let's show that a cross b is perpendicular to a in other cases. It's going to be enough to look at the dot product, because if we can show that a cross b dotted with a is equal to 0, then we'll know that the length of a cross b times the length of a times cosine theta is 0, where theta is the angle between a and b. That follows from the formula for dot product in terms of lengths and angle. And if the product of these things is equal to 0, then either the length of a cross b is 0, or the length of a is 0, or cosine of theta is 0. Well, if the length of a vector is 0, then the vector itself is 0. So we have that either a cross b is 0, the 0 vector, or a is a 0 vector, or cosine theta is 0. Now, by our convention, the 0 vector is perpendicular to any other vector. So in these cases, we definitely have that a cross b is perpendicular to a. And in this other case, the more interesting case, cosine theta is 0 means that theta, the angle between the vectors, must be 90 degrees, and so the two vectors a cross b and a are indeed perpendicular. So it is indeed enough to show that the dot product is 0, and that's what we'll focus on now. To show that the dot product is 0, I'll write everything out in terms of components and do some algebra. First, a cross b is given by this expression, where a1, a2, and a3 are the components of a, and b1, b2, b3 are the components of b. Now, if we dot a cross b with a, we need to dot this expression with the vector of components a1, a2, a3. The formula for dot product gives this expression, and distributing out gives this expression. Now, the fun begins. This first term that has a1, a2, b3 in it cancels out with this term. And the second term, a1, a3, b2, cancels out with this one. Finally, this third term with a2, a3, b1 cancels out with this term. And so, since everything cancels out, the dot product is just 0, as we wanted to prove. A similar argument shows that a cross b dotted with b is equal to 0, and so a cross b is perpendicular to b as well. Finally, I'd like to give the idea behind the fact that the direction of a cross b is given by the right-hand rule. Certainly we can check this for a few easy vectors. For example, if a is the vector I and b is the vector j, then a cross b is given by this determinant. Expanding out, I get this, which simplifies to k. So in the case when a is I and b is j, the cross product is k and not negative k, so the right-hand rule is satisfied. Now, if a and b deviate slightly from I and j, then it makes sense that their cross product should only deviate slightly from k. After all, the components of the cross product are continuous functions of the components of the original vectors. So if a cross b is close to k, it must also satisfy the right-hand rule. It can't all of a sudden jump to the other side and satisfy a left-hand rule instead. But if I continue these small perturbations of a and b, I can get all possible pairs of vectors. And therefore, for all possible pairs of vectors a and b, the cross product has to satisfy the right-hand rule. This intuitive argument is the idea that lies behind a proof of this fact. In this video, I proved the length formula for cross product, and I proved the fact that A cross B is perpendicular to both A and B. I showed that the direction of A cross B is given by the right-hand rule in one example, where A was I and B was J, and I gave an intuitive argument for why the direction of A cross B should be given by the right-hand rule in general. This video relates the cross product of two vectors to the area of the parallelogram spanned by those two vectors. Suppose we want to compute the area of this parallelogram that's spanned by the vectors A and B who have an angle theta between them. Well, the area of the parallelogram is the length of the base times its height. Now the height, which I'll draw here, that height is given by the length of B times sine of theta. That's because sine of theta is opposite over hypotenuse, which is going to be h over the length of B, which means that h equals B sine theta. Also, the length of the base is just the length of vector A. Therefore, the area is the length of A times the length of B sine theta. Well, that's just the same thing as the magnitude of A cross B. So the area of a parallelogram is given by the magnitude of the cross product of the two vectors that span it. Let's use this formula to find the area of a triangle with vertices P, Q, and R, whose coordinates are given above. Now, a triangle is not the same thing as a parallelogram, but we can think of the triangle as half of a parallelogram. I'll label the vectors that span this parallelogram PQ for the vector from P to Q, and PR from the vector from P to R. So the area of triangle PQR is going to be 1/2 times the magnitude of PQ cross PR. Now I can use the coordinates of P and Q to get the components of vector PQ just by subtracting. So this is 4 minus 0, 2 minus 0, and 0 minus -3, which gives 4, 2, 3. Similarly, the components of PR can be found by subtracting the coordinates of R minus the coordinates of P. So that's 3 minus 0, 3 minus 0, 1 minus -3, or 3, 3, 4. Now let me take the cross product, PQ cross PR. So that's going to be I times 2 times 4 minus 3 times 3 minus J times 4 times 4 minus 3 times 3 plus K times 4 times 3 minus 3 times 2. That simplifies to I times -1 minus J times 7 plus K times 6. In other words, I have the vector -1, -7, 6 as my cross product. Now I'll take the magnitude of this vector. That's going to be the square root of -1 squared plus -7 squared plus 6 squared, or the square root of 86. And so the area of my triangle is going to be 1/2 the square root of 86. In this video, we found that the area of the parallelogram spanned by vectors A and B is given by the magnitude of the cross product A cross B. This video gives some properties of the cross product. Please pause the video and take a moment to think about these 6 properties. Which of these are true and which of these are false? Remember that true means it always has to be true, and false means it sometimes or always false. If you think that the property is true, try to give a proof or argument for why. And if you think it's false, try to come up with a counterexample. That is, an example that breaks the statement. The first statement is false. By definition, A cross B is a vector whose direction is given by the right-hand rule. The second statement is true. One way to see this is that the length of A cross A is given by the formula the length of A times the length of A times sine of theta, where theta is the angle between A and A. In other words, theta is the angle 0. Well, sine of 0 is 0, and therefore A cross A has length 0, which means that A cross A must be the 0 vector. The third statement is false. It's true that if A cross B is the 0 vector, then A is parallel to B. That's because the length of A cross B will be 0, which means that the length of A times the length of B times sine of theta is 0. For non-zero vectors A and B, that means that sine of theta is 0, so theta must be either 0 or 180 degrees, and the two vectors are parallel. But the two vectors don't have to be exactly equal. For example, we might have A to be I, the unit vector in the x direction, and B could be 3I, and when we take the cross product, we can work out that we still get the 0 vector. The fourth statement is true. We know that I cross J is a vector of length 1. That's because the length of I cross J is given by the length of I times the length of J times sine of the angle between them, which is 90 degrees. In other words, 1 times 1 times 1, or 1. We also know that the direction of I cross J is perpendicular to both I and J, and in a direction given by the right-hand rule, well, that has to be exactly in the k direction. So we have a unit vector in the k direction. This must be k. The fifth statement is false. A cross B is not equal to B cross A. It's the negative of B cross A. One way to see this is that the length of A cross B and B cross A is the same, since both are given by the magnitude of A times the magnitude of B times sine of the angle between them. But the direction of A cross B and B cross A is opposite, because when we apply the right-hand rule to A cross B, our thumb goes one direction, and if we do B first and then A with the right-hand rule, our thumb points exactly the opposite direction. This last property might be the trickiest to think about. It turns out this is also false. Here's a counterexample. Let's let the vector A be I, B be I also, and C be K. Then A cross B, quantity crossed with C, is going to be I crossed with K. Well, that's just going to be the 0 vector crossed with K, which is the 0 vector. On the other hand, if we do A cross quantity B cross C, that's going to be I cross quantity I cross K. If we think about the fact that I cross K is a unit vector and use the right-hand rule to find its direction, we see that I cross K is going to be negative J. So this is going to be I cross negative J, which is the same thing as minus K. So these two vectors, minus K versus 0, are not equal. And so this is a counterexample to this property So notice that this property is like an associative property. So this says that the cross product is not associative. Kind of a shocking fact. Here are some properties of cross product that are all true. First, U cross V is the negative of V cross U. We already saw this. You could think of this as an anti-commutative property. Commutative would mean that U cross V is the same as V cross U, but here it's the opposite. This next property says that when you have a scalar multiple of U, a scalar multiple of V, you can pull out those scalars and put them on the front. You can think of this as something like an associative property for scalars. Remember that the cross product just for 3 vectors is not associative, as we saw before. These last 2 properties are distributive properties. When we have U crossed with V plus W, we can distribute the U and get U cross V plus U cross W. Similarly, if you have U plus V crossed with a vector W, we can distribute the W, U cross W plus V cross W. Let's use these properties to find a unit vector orthogonal to both I plus j and I plus k. We know that if we take the vector I plus j and cross it with I plus k, that will be orthogonal or perpendicular to both I plus j and I plus k. We could work out this cross product in components, but if instead we use the distributive properties, this is the same thing as I plus j cross I plus j cross k. Now if we distribute again, that's the same thing as I cross I plus j cross I plus I cross k plus j cross k. We've basically FOILed out this cross product. Now we know that I cross I is just the 0 vector, since I is parallel to itself. J cross I, that's the negative of I cross j, so that's going to give us negative k. I cross j is k. I cross k, thinking about the right-hand rule, is going to give us negative j, and j cross k is going to give us I. So our vector that's going to be perpendicular to both of our given vectors is going to be I minus j minus k, in other words, 1, negative 1, negative 1. To make this a unit vector, we can just divide by its length, square root of 3, and here's an answer, a unit vector orthogonal to both of these vectors. Of course, the negative of this vector would also work. This video gave some properties of cross product that always hold, including distributive properties and the anti-commutative property. It also gave some examples of properties that didn't always hold. In particular, the associative property doesn't always hold for cross product. This video introduces equations for lines and planes in 3-dimensional space. Please pause the video for a moment and try to decide if the line through this pair of points is parallel to the line through that pair of points. I'm going to represent the first pair of points schematically as 2 points on the plane, even though they're really 2 points in space. Now the line between the pair of points goes in a direction parallel to the vector determined by subtracting coordinates. That is, the vector with components 2, 6, negative 4. Similarly, the line between the other pair of points goes in a direction parallel to this vector that I get by subtracting coordinates. So my 2 lines will be parallel if and only if my 2 vectors are parallel. In other words, if and only if v is a scalar multiple of w. In fact, it's easy to check that v is -2/5 times w, and so the two lines are indeed parallel. Now suppose I want the equation of a line through the origin that's parallel to the line through these 2 points. So that's a line in space that heads off in the direction of v. So if I place v like I have done with its tail end at the origin, then the point at the tip of v, so that's the point 2, 6, -4, will be on my line. So will the point halfway along v, that would be the point 1, 3, -2, and the point at the tip of 2v, that would be the point 4, 12, -8, will also be on my line. In fact, any point with coordinates 2t, 6t, -4t will be on my line. That would be the point at the tip of the vector t times v. In other words, the line through the origin that is parallel to v will consist of all points of the form x equals 2t, y equals 6t, and z equals -4t, where t is a real number. Notice that negative values of t correspond to points on this end of the line. Now that was the line through the origin that was parallel to the line through these 2 points. Next, let's find the equation of the actual line through these 2 points. This line will also be parallel to v, but it'll have to be shifted off the origin to go through these 2 points. For example, if I focus on this point, then I see that the line will have to be shifted to go over in the x direction by -4, down in the y direction by -6, and up in the z direction by 1. So it'll look something maybe like this. Algebraically, we can do that shifting by just subtracting 4 from the x values, subtracting 6 from the y values, and adding 1 to the z values. To summarize, if I want a line through the origin that goes parallel to a vector v, I just multiply my components of v by the variable t. And if I want a line parallel to v that goes through a particular point, I do the same thing and then add the coordinates of that point. Of course, I could have used the other point, and I would have gotten another set of equations that's in fact equivalent to the first set of equations. To see that these 2 systems of equations define the same line, we can just call the second variable s instead of t, and then make the substitution s equals t minus 1. In other words, plugging in t minus 1 for s here gives us the following, which after a little bit of algebra reduces to the first system of equations. These systems of equations are called parametric equations for the line. The parameter is t, and physically we can think of this as a particle moving along a line, t describing the time, and x, y, and z describing the position of that particle at time t. More generally, if we want to describe a line through a point x0, y0, z0 in the direction of the vector a, b, c, we can describe it with the parametric equations x equals at plus x0, y equals bt plus y0, and z equals ct plus z0. Remember, if x0, y0, z0 weren't there, then our equations would just describe a point at the tip of a vector t times our original vector. But by adding x0, y0, and z0, we've shifted that line over so that it'll go through the point x0, y0, z0. Now if we take our parametric equations and solve for t, we get t equals x minus x0 over a, t equals y minus y0 over b, and t equals z minus z0 over c. And now if we set these expressions for t equal to each other, we get x minus x0 over a equals y minus y0 over b equals z minus z0 over c. The equations in this format are called the symmetric equations for the line. Finally, we can describe the line with a vector equation. R is a vector that's a function of t whose components are given by at plus x naught, bt plus y naught, ct plus z naught. The vector equation is very similar to the parametric equations. Geometrically, we think of our line going through space, and a point on the line, whose coordinates are given by the parametric equations, can also be thought as the tip of a vector starting at the origin. So this we can think of as the vector r of t. Physically, as we think of a particle moving along the line over time, we can think of a vector with its tail at the origin sweeping along that line with its tip always on the line. We've looked at equations for lines. Now let's take a look at equations for planes. Suppose we want to find the equation of a plane through the point -3, 2, 0, and perpendicular to the vector with components 1, -2, 5. I'll call that perpendicular vector v. Now if I take any point x, y, z on my plane, then the vector from the given point to the point x, y, z has to be perpendicular to my vector v. In terms of dot product, that means the vector x minus -3, y minus 2, z minus 0, dotted with the vector v, is going to have to be 0. Rewriting, I get the equation 1 times x plus 3 minus 2 times y minus 2 plus 5 times z minus 0 is equal to 0. That's the equation of my plane. And more generally, the plane through the point x naught, y naught, z naught, perpendicular to a vector a, b, c, is going to have to be given by the equation a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0 for the very same reason. That reason being that the dot product of the two vectors has to be 0. It's possible to rewrite this equation as follows. Note that my variables here are x, y, and z, and all other letters stand for constants. In this video, we found 3 forms for the equation of a line and 2 forms for the equation of a plane. This video gives more examples of finding the equations of lines and planes. Let's start by finding the equation of a line through the point 3, -1, 2 that's perpendicular to the plane with this equation. Recall that the equation of a plane can be written in the form ax plus by plus cz equals d, where the 3 coefficients a, b, and c form a vector that's perpendicular to the plane. So for our plane, 4x minus 6y plus z equals 13, the vector 4, -6, 1 is perpendicular to this plane. Well, if we want a line that's perpendicular to the plane, then the line must be going in this direction. So I'll write the direction vector of the line is 4, -6, 1. And the point it goes through, or a point it goes through, is 3, -1, 2. So one way to write the equation for the line is to use parametric equations. X starts at the x value of 3, and every second it goes 4 units in the x direction, so we can write that as 3 plus 4t, where you think of t as time. Y starts at -1, and every second it goes -6 units in the y direction. And z starts at 2, and every second it goes 1 unit in the t direction. So here are parametric equations for our line. Of course, if we wanted to, we could also write the line using symmetric equations by isolating t in each equation and setting the t's equal to each other to get x minus 3 over 4 equals y plus 1 over 6 equals z minus 2. A third way of writing the equation for the line is using vector notation. xyz equals 3, -1, 2 plus 4, -6, 1 times t. The idea behind this vector notation is if I draw each of these vectors given here and put their tail at the origin, then the tips of these vectors will have x-coordinate given by 3 plus 4t, y-coordinate given by -1 minus 6t, and z-coordinate given by 2 plus 1t. So those x, y, and z coordinates of the tip of my arrows will be exactly the x, y, and z coordinates given by these equations. So those tips of the arrows will sweep out the line. As our next example, let's find the equation for the plane through these 3 points. Well, again, I know that I can write the general equation for a plane as ax plus by plus cz equals d, or I could write it in this form, a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, and c, again, is a vector perpendicular to the plane, and x naught, y naught, z naught is a point on the plane. So if we could just find this vector perpendicular to the plane, we'd be home free, because we could just write down this equation, because we've got plenty of points. We've got 3 points. We could pick one of them to plug in for x naught, y naught, z naught. We just need this normal vector. Well, I could find some vectors in the plane, and the key idea here is going to be taking the cross product. Once we find vectors in the plane, when we take the cross product, that automatically gives us a vector perpendicular to those vectors. So let's find the vectors in the plane. If I call this point P, this one Q, and this one R, I could take, for example, PQ and PR. PQ will have components 5, 3, 2 by subtracting coordinates, and PR will have components -4, -1, -5. Now I will get my normal vector n that's perpendicular to the plane by taking the cross product. I'll write out my matrix, and I get that my I component is going to be 3 times -5 minus -1 times 2, minus my j component, and here goes 5 times -5 minus -4 times 2, plus my k, and here goes 5 times -1 minus -4 times 3. That simplifies to I times -13 plus j times 17 plus k times 7, or the vector -13, 17, 7. Now I can write down the equation for my plane. I'll use this first point for my x naught, y naught, z naught, but you could use either of the other 2 points and you'll get an equivalent equation. So I write down -13 times x minus 3 plus 17 times y plus 1, because it's minus minus 1, plus 7 times z minus 2 equals 0. I can distribute things out and simplify to get -13x plus 39 plus 17y plus 17 plus 7z minus 14 equals 0, which gives me -13x plus 17y plus 7z equals -42. Either one of these 2 equations, this one or this one, are perfectly fine as final answers. One is in the form of this equation, and the other is in the form of that equation. And recall that the key idea that we used here was cross product. That's what allowed us to get a normal vector to the plane once we had 2 vectors within the plane. I want to make an analogy between lines in the plane and planes in space. What information is enough to determine the equation for a line in the plane? Well, typically we need a slope and an intercept, or just a slope and any one point will do. Or we could get the equation for a line in the plane just with any 2 points. First, we use the 2 points to get a slope, and then we use the slope and 1 point to write down the equation of the line. The situation for lines in 3-dimensional space is somewhat similar. We could, instead of the slope, doesn't really mean anything in 3D, instead we have a direction vector. So we could use a direction vector and 1 point. Or we could use any 2 points, because we can use them to get the direction vector. And then we're back to here. What about the equation of a plane in 3-dimensional space? Well, for the plane, we need the normal vector and a point. Kind of similar to how we need a direction vector and a point for a line in space or in the plane. But if we don't have that, we could just use 3 points, because we can use them to get 2 vectors in the plane, as we did in a previous example, and then take the cross product of these 2 vectors in the plane to get the normal vector. And then we're back to the first situation. There are other possibilities we can use to get the equation for a plane in 3-dimensional space also. For example, we could have a line in the plane and a point in the plane. One way, those also determine a plane, and one way to get the equation of the plane would be to use the line to get 2 points, and then we have 3 points, and we're in the previous situation. I should mention here that when we're talking about 3 points, they need to be not collinear. Otherwise, if they're collinear, that means all on a line, they won't determine a plane. And the point needs to not be on the line, so that that way the 3 points won't be collinear, and you'll determine a plane. So one other way you can get an equation of a plane sometimes is from 2 lines in the plane. And again, you could use this maybe to get 3 points. And then you're back to this situation. So anyway, anytime I'm asked to find the equation of a plane, I'm going to be looking around either for, maybe I already have a normal vector and a point, and if I don't, I'm going to be looking for some way to find 3 points. Once I have 3 points, I know I'm home free. I can just use them to make 2 vectors, take the cross product, and I've got my normal vector. So these are sort of the key situations, and I think of every other situation as just a variant in which you can ultimately find 3 points and then a normal vector. In this video, we did some examples of finding equations of lines and planes, and we reviewed the information that's needed to find an equation of a line or a plane. In this video, we'll work with parallel and perpendicular lines and planes. In this example, we're asked to determine whether these 2 planes are parallel, perpendicular, or neither. And if neither, find the angle between them. So 2 planes are going to be parallel if their normal vectors are parallel. They'll be perpendicular if the normal vectors are perpendicular. So let's look at the normal vectors for the 2 planes. We can read those off from the coefficients of x, y, and z in these 2 equations. So I'll write down n1, the first normal vector, is 1, 2, 2, and n2 is 2, negative 1, 2. To check if n1 and n2 are parallel, we can check to see if n2 is some constant multiple of n1. Well, for the x-coordinates of n2 to be a constant multiple of the x-coordinate of n1, that constant would have to be 2, but then the y-coordinate is not twice n1's y-coordinate. So the 2 vectors are not scalar multiples of each other, so therefore they're not parallel. So the planes are not parallel. Okay, so now let's check for perpendicularity. Are N1 and N2 perpendicular to each other? Well, to check for that, I can compute the dot product, N1 dot N2, and I get an answer of 2 minus 2 plus 4, which is 4, which is not 0. So the two normal vectors cannot be perpendicular. And so the two planes are not perpendicular. Now to find the angle between the planes, that's going to be the same as the angle between the normal vectors. It's like you've taken the angle between the planes and rotated everything 90 degrees to get the angle between the normal vectors. Now to get to the angle between two vectors, we can use dot product, because we know that N1 dot N2 is going to be the magnitude of N1, the magnitude of N2, times cosine of the angle between them. Therefore, cosine of the angle between them is given by the dot product divided by the two magnitudes. Continuing with the computation, we're getting the dot product 1, 2, 2 dot 2, negative 1, 2 divided by the square root 1 squared plus 2 squared plus 2 squared times the square root of 2 squared plus negative 1 squared plus 2 squared. That ends up as 4 over the square root of 9 times the square root of 9, or 4/9. Now I can figure out theta from the inverse cosine of 4/9, which turns out to be about 63.64 degrees. In this next example, we're asked to find the equation of a plane that's perpendicular to two planes and goes through a given point. I've tried to draw a schematic of two intersecting planes. Now the plane we're looking for, let's say call it Q. If plane Q is perpendicular to plane P1, then, as in the previous problem, the normal vector for Q has to be perpendicular to the normal vector for P1. Similarly, if Q is perpendicular to P2, then the normal vector for Q must be perpendicular to the normal vector of P2. So we're looking for the normal vector of this plane Q, and since it's perpendicular to both the normal vector of P1 and the normal vector of P2, we can find it by taking the cross product, NP1 cross NP2. Recall that we can read off the normal vectors for the planes by looking at the coefficients of x, y, z in these equations. So the normal vector for P1 will be 1, negative 2, 3. That's a negative sign carrying over from here. And the normal vector for P2 will be 1, 1, 0. The 0 because there's no z in the equation. So now I can take the cross product of those two vectors, and I get I times negative 2 times 0 minus 1 times 3 minus j times 1 times 0 minus 1 times 3 plus k times 1 times 1 minus 1 times negative 2. That simplifies to I times negative 3 minus j times negative 3 plus k times 3. So my normal vector for Q is going to be negative 3, 3, 3. Now I still need a point on the plane in order to write down the equation for the plane, but fortunately I've been given a point. So I can use this point and this normal vector to write down the equation of my plane Q. It will be negative 3 times x minus 5 plus 3 times y plus 3 plus 3 times z minus 1 equals 0. I notice I have a lot of 3's in this equation. If I divide everything by 3, I get a slightly simpler form of this equation, minus x minus 5 plus y plus 3 plus z minus 1 equals 0. If I like, I can distribute everything and bring my constants over to the right side to get minus x plus y plus z is equal to minus 7. I do want to mention that there are other ways to solve this problem. For example, we might have started by solving the two equations together to get an equation for the line of intersection. The direction vector of that line will also be a normal vector to the plane Q that's perpendicular to both of the other planes. I also want to emphasize that there isn't any unique normal vector to a plane, right? Any scalar multiple of the normal vector that we found would work just as well as a normal vector for our plane. In this example, we're asked to figure out whether the lines L1 and L2 are parallel, skew, or intersecting. Let's figure out whether they're parallel first. The lines are going to be parallel if and only if their direction vectors are parallel. The direction vector for L1 is 2, -1, 3. I can just read it off from the coefficients of t. The direction vector for L2 is 4, -2, 5. Well, D1 is going to be parallel to D2 if and only if D1 is a scalar multiple of D2. It looks like the x component of D1 is 1/2 of the x component of D2, and similarly, the y component is 1/2 of D2's y component, but that relationship doesn't hold for the z components. 3 is not half of 5. Therefore, this doesn't work. D1 is not a scalar multiple of D2, so the direction vectors and the lines are not parallel. Next, let's decide if L1 and L2 are intersecting. Normally, to find if two objects intersect, I solve the equations together. But there's a tricky little detail here. Right now, L1 and L2 are written in terms of the same parameter t. So if I solve these equations together, I'd be looking for a value of t, the same value of t that made my x coordinates, y coordinates, and z coordinates the same. That would be, since t we think of as the time parameter, you can think of particles traveling along those lines. If we found such a t, that would be a collision point where the two particles got to the same point at the same time. But we just need the paths to intersect. One could get there years ahead of the other particle. So the parameters don't need to be equal. Only the x, y, and z pieces need to be equal. And to give it the flexibility for that to happen, the first thing I'm going to do is change my second parameter. Instead of t, I'm just going to call it s. That way, now if I solve together, I might be finding a different value of s from the value of t that would still give me the same x, y, and z coordinates. That would be like the second particle arriving at that point at a different time than the first particle, but they'd still have the same x, y's, and z's. So once I've made that key change, now I'm going to solve my equations together. So I'm going to set 3 plus 2t to equal 1 plus 4s, 4 minus t to equal 3 minus 2s, and 1 plus 3t to equal 4 plus 5s. Let me start with these first two equations and see if I can eliminate a variable, say t. So I'm going to write down my first equation and my second equation. So if I multiply my second equation, the whole thing by 2, then the coefficients of t will be equal, and I can add or equal and opposite, I guess, and I can add the two equations together to cancel out my t's. So this becomes 8 minus 2t equals 6 minus 4s. Now I can add those together. I get 11. T's disappear as I wanted them to. On this side I get 7. Hey, the s's are disappearing too. So my equation just becomes 11 equals 7. Well, that's definitely a contradiction. And that shows that there is no solution. There's no value of s and value of t that work to get me the same even x and y coordinates. So therefore, there's no solution and there's no point of intersection. So my lines are not parallel, they are not intersecting, therefore L1 and L2 by definition are skew. Skew lines are lines that don't intersect and they're not parallel. That's possible in 3D. It wouldn't be possible on the plane. In the plane, two lines have to either be parallel or intersect. But in 3D, we could start with two intersecting lines and just shift one off the other and get two skew lines. And here's an example. This video was full of examples of planes and lines that were parallel, perpendicular, or neither. A couple of key ideas that you might want to take away from this video is, first of all, you can use the normal vectors for planes to find the angle between the planes, and in particular to check if those two planes are parallel or perpendicular. Another key and important detail is when checking for the intersection of two lines, if these lines are given in parametric form, use different parameters. For example, t for one line and s for the other, to check for an intersection point and not just a collision point, which is what you'd be solving for if you're using the same parameter. In this video, we'll find distances between points, lines, and planes using the idea of projection. As our first example, let's find the distance between the point 1, 2, 3, I'll call that point P, and the plane given by this equation. If we wanted to, we could look up a formula for distance between points and planes, but I'm going to work this problem out instead from concepts and first principles. The distance that I want is the shortest distance between P and a point on the plane. In other words, the length of a line segment from P that drops down to the plane and intersects it at a right angle. But the difficulty is I don't know which point that is that would be on the plane that would be closest to the given point. So instead what I'm going to do is I'm just going to take any point on the plane. So I'll call a point Q, and I'll just find any x, y, and z value that satisfy this plane equation. For example, the point 2, 0, 0 satisfies the plane equation. Now let me connect Q to P to get a vector QP that has components -1, 2, 3. The vector QP itself will be longer than I want, but if I project QP onto the normal vector for the plane, so I'll draw the projection here in red, then I'll just get the component of the vector QP that lies perpendicular in the perpendicular direction of the plane. That's going to be exactly the same length as this red line over here. It's going to give us the distance between the point and the plane. So the steps I'm going through were first to find any point, call it point Q, on the plane, and then to connect Q to P to get a vector QP, and then I'm going to project QP onto the normal vector N to the plane. And since I ultimately just want distance, a scalar, I can do a scalar projection. So the distance is the scalar projection of QP onto the plane's normal vector. In other words, a scalar projection of -1, 2, 3 onto the vector 5, 4, -3, since I can read the normal vector for the plane off from the coefficients of x, y, and z. Using the formula for scalar projection, this is the dot product, 5, 4, -3 dotted with -1, 2, 3, divided by the length of the vector that forms my floor, 5, 4, -3. Working out the dot product, I get -5 plus 8 minus 9 divided by the square root of 5 squared plus 4 squared plus -3 squared, and that simplifies to -6 over the square root of 50. Now you might worry that this is negative. Distance is supposed to be positive. The reason it's negative is just that my normal vector actually was on the opposite side of the plane, so a more accurate picture, the normal vector I picked out pointed that direction. And so when I do the scalar projection, remember it's assigned magnitude of the shadow. So because the vector QP and the normal vector were pointing pretty much in away from each other at an angle of more than 90 degrees, we're getting a negative answer for the scalar projection. Since I want my distance to be the positive length of the shadow rather than the signed length of the shadow, I can fix that pretty easily just by putting absolute values. So in fact, I should have had absolute values signs all the way along here. And my actual distance is positive 6 over the square root of 50. And that's my final answer. In our next example, we're asked to find the distance between two skew lines. Skew means that they're neither intersecting nor parallel. So one of them, say L1, might be going like this. And then L2 might be going, say, into and out of the page like this. It might be easier to imagine what's going on if I draw two parallel planes, one of which contains each line. Now we want the distance between these two lines, so that's the minimum distance between 2 points on the two lines. That it's the length of a line segment that's going to meet each line at a right angle. But since we don't know what these 2 points on these two lines that are closest together are, let's just take any 2 points, one on L1 and one on L2. For example, I could let P be the point 3, 4, 1. That's the point on L1 that I get by setting the parameter t to 0. And I could let Q be the point on L2, 1, 3, 4, that I get by setting s to 0, but any 2 points are fine. The next thing I'm going to do is connect those 2 points to make the vector PQ. I can get the components of the vector PQ by subtracting coordinates of my points, so that would be -2, -1, 3. But for the length between the lines, I don't want the length of the whole vector PQ. I just want the length of the piece of that vector that points in the perpendicular direction to both L1 and L2. So if you imagine that this is a normal vector that's going to be perpendicular both to L1 and to L2, I want to project PQ onto that normal vector. So first I need to find the normal vector, a vector that's perpendicular to both L1 and L2. Well, that's not too hard. I can use cross product. The direction vector for L1 is 2, -1, 3. I can just read that off from the coefficients of t in the equation for the line. And the direction vector for L2 is going to be 4, -2, 5. So my normal vector n that's perpendicular to both those lines is going to be the cross product of d1 and d2. Let me calculate that. So I set up my matrix. My I component is going to be -1 times 5 minus -2 times 3 minus j times 2 times 5 minus 4 times 3 plus k times 2 times -2 minus 4 times -1. That simplifies to I times 1 minus j times -2 plus k times 0. So that's the vector 1, 2, 0. Now I'm ready to do the scalar projection of my PQ, just any old vector between 2 points, onto this normal vector that's perpendicular to both L1 and L2. That'll give us the perpendicular component of PQ, which will be exactly the distance between the two lines, and also the distance between the two parallel planes that contain the two lines. So let me calculate scalar projection of PQ onto N. That's the scalar projection of PQ is -2, -1, 3 onto 1, 2, 0. So using my scalar projection formula, I do the dot product. -2, -1, 3 dotted with 1, 2, 0 divided by the length of the vector that's my floor. So that's square root of 1 squared plus 2 squared plus 0 squared. That simplifies to negative 4 over the square root of 5. Once again, I'm getting a negative number, but that just means that in the actual configuration, the PQ is at a larger than 90 degrees angle from the normal vector that I'd chosen. If I happen to choose the normal vector in the opposite direction, I would have gotten a positive number. To find the distance, we'll just take the absolute value and get 4 over the square root of 5 as our final answer. In this video, we did a couple examples of finding distances between two objects. The objects were points, lines, and planes. The key idea seemed to be to find any 2 points, one in each of the objects, create a vector between them, and then use scalar projection to find the component of this, the length of the component of this vector that lies perpendicular to both objects. This video is an introduction to vector functions and how they can be used to represent curves in space. A vector function, or vector-valued function, is a function whose domain is a set of real numbers and whose range is a set of vectors. If the range consists of vectors in 2 dimensions, then the vector-valued function can be written in the form r of t equals r1 of t, r2 of t, where r1 and r2, the components of the vector, are themselves real-valued functions. Or, if the vectors are in 3D, then we can write r of t with 3 component functions. If we think of the vectors as position vectors with their initial points at the origin, then the endpoints of the vectors r of t trace out a curve in R3, or in R2 if our vectors are in 2-dimensional vectors. Sometimes we place an arrow on the curve to indicate the direction of increasing t values. For example, in this picture, this point here might be r of 0, and this point r of, say, 1/2, and so on. Let's sketch the curve defined by the vector function with components t, sine of 5t, cosine of 5t. If we ignore the z component and just look at the x and y components, then it's like we're graphing x equals t, y equals sine of 5t. In other words, y equals sine of 5x. Ignoring the z component means we don't care about the height of our curve. It's as if the height were always 0 and we were just living in the xy plane. In fact, this graph corresponds to the projection of our curve onto the xy plane. Similarly, if we ignore the y component and just think about the x and z components, that's like we're graphing x equals t, z equals cosine of 5t, or in other words, z equals cosine of 5x. That's what we should see if we take the projection onto the xz plane. Finally, if we ignore the x component and just look at the y and z components, then we're graphing y equals sine of 5t, z equals cosine of 5t. Now, since sine squared of 5t plus cosine squared of 5t is always equal to 1, this is like saying y squared plus z squared equals 1, which means our graph should be the graph of a circle with radius 1. So the projection of our curve onto the yz plane should just be a circle. In fact, one way to think about this curve is to think of t as time and x, y, and z representing the position of a particle at that time. As t increases, the x-coordinate of the particle is increasing, and the y and z coordinates make it run around and around in circles in the yz direction. So this particle should trace out the path of a helix, otherwise known as a spiral or slinky shape. I'll paste in a better picture that I drew using the MatGrapher. And here are the graphs that I made by looking straight down on the xy plane, the xz plane, and the yz plane. The reason these don't look like perfect sine curves, cosine curves, and circles is because there's some perspective built into the MacGrapher. So it's not a perfect projection, it's a perspective drawing. Next, let's look at the vector value function given by this equation. Just like with real valued functions, we can talk about the domain, limits, and continuity. To find the domain of R of t, we need to figure out what values of t make sense to plug in here. In other words, what values of t give us real numbers for our components. Well, we know that t can't equal 1 because that would make us divide by 0 and not get a real number. In the second component, we also know that t plus 8 had better be greater than or equal to 0, since taking the square root of a negative number wouldn't give us a real number. In other words, t better be greater than or equal to negative 8. Looking at the third component, we know that we can't take the ln of a negative number, so we need that t has to be greater than 0. We can't take ln of 0 either. Also, we know that we can't divide by 0, so we need ln of t to not equal 0. In other words, t had better not equal 1. Putting this all together, we see that the domain is the set of all t values such that t is bigger than 0 and t is not equal to 1. Next, let's find the limit as t goes to 1 of r of t. We can find this by taking the limit separately of each component. Now the limit as t goes to 1 of t squared minus t over t minus 1, I can't evaluate that just by plugging in 1 for t since I have a 0 over 0 indeterminate form. But I can use various calculus 1 techniques. For example, I could factor the numerator, cancel with the denominator, and get the limit as t goes to 1 of t, which is just 1. Now for the second component, taking the limit as t goes to 1 of the square root of t plus 8, I can figure that out just by plugging in 1 for t, so that's just 3. And finally, for the third component, limit as t goes to 1 of sine of pi t over ln of t, that's also a 0 over 0 indeterminate form. I get zeros on the numerator and denominator if I plug in 1 for t. Let me evaluate this one using L'Hopital's rule. So I'll take the derivative of the numerator, that's pi times cosine of pi t. The derivative of the denominator is 1 over t, and simplify. And now I'm in a position where I can just plug in 1 for t and get 1 times pi times negative 1, or negative pi. Having evaluated the limits of all my components, I can now plug in and get a limit of 1i plus 3j minus pi k. Finally, let's talk about the continuity of r of t. We know it's not even defined for t values less than or equal to 0, but is it continuous on the interval from 0 to infinity? Well, no, because it's not defined at t equals 1 either. But it does have a limit as t goes to 1. We just evaluated it. Therefore, our curve has a removable discontinuity, otherwise known as a hole, when t equals 1. If we wanted to make the function continuous, it would be pretty easy to do just by plugging the hole, which we can describe using a piecewise definition. In this video, we plotted one vector-valued function that looked like a helix, and we analyzed another vector-valued function in terms of its domain, limits, and continuity. This video is about taking derivatives and integrals of vector-valued functions. In Calculus 1, we took the derivatives of real-valued functions, y equals f of x, and we found that f prime of x, evaluated at an x value a, gave us the slope of the tangent line at x equals a. We first evaluated derivatives by a limiting process, taking the slopes of secant lines in between a and a point close to a. In other words, algebraically, we define the derivative as the limit as h goes to 0 of f of a plus h minus f of a over h, where this ratio represented the slope of the secant line between the points a, f of a, and a plus h, f of a plus h. So how could we generalize this process to curves defined in 2 or 3 or even more dimensions by vector-valued functions? More specifically, suppose a particle is moving according to the vector equation r of t. How can we find a tangent vector that gives the direction and speed that the particle is traveling? For simplicity, I'm going to draw a diagram in 2 dimensions, even though this process will work for 3 or even more dimensions. Let me fix a t-value, t equals a, which will correspond, for example, to maybe this point right here. So now if I draw a vector whose initial point is at the origin, the tip of this vector is the vector r of a. Now I want to find the tangent vector at t equals a, which is going to be a vector pointing in maybe approximately this direction, assuming that the curve is being traversed in this direction as t increases. To find that tangent vector, I can use the same techniques that we used in Calculus 1. That is, I can look at a nearby point, r of a plus h, for some small number h. Here's the vector r of a plus h. And now I can look at the secant vector that goes in between r of a and r of a plus h. Notice that by vector arithmetic, the vector r of a plus the secant vector equals the vector r of a plus h. So therefore, the secant vector is equal to r of a plus h minus r of a. Now I could keep taking secant vectors in between closer and closer points, and in the limit, that would give me a vector that pointed in the right direction, but it would shrink down to 0 in size. Since I want my limiting vector to have the appropriate direction and length, instead of taking these direct secant vectors, I'm going to use rescaled secant vectors, whose length is always the average speed that the particle goes between these 2 points. To get that rescaled secant vector, I'll take the difference of my 2 position vectors and divide by the difference in time, which is h. This is very analogous to the Calc 1 calculation of derivatives, where we didn't just take the difference in y values on the numerator, which would have just gone to 0. We had to rescale it by taking a difference in x values also. Now to get the tangent vector, we just take the limit as h goes to 0 of these rescaled secant vectors. Now if we write our original r of t in components, then we can write out our limit in terms of components. And rewrite a little bit. Now taking the limit of a vector is the same thing as taking the limit of each component separately, which just gives us our familiar Calculus 1 derivatives for each component. Therefore, the tangent vector at x equals a can just be found by taking the derivatives of each component at x equals a separately. This holds for vectors in 3 or more dimensions as well as vectors in 2 dimensions. This quantity is called r prime of a, and it's also called the derivative of r of t at t equals a. To summarize, the derivative of the vector function r of t is the same thing as the tangent vector, and it's defined as dr dt, or r prime of t, as the limit as h goes to 0 of r of t plus h minus r of t over h. If r is given in components, this time I'm making it a 3-dimensional vector function, then r prime of t can be computed by taking the derivatives, the ordinary Calc 1 derivatives, of each component separately. The derivative of a vector function is a vector. Again, it's the same thing as the tangent vector. As with any vector, we can normalize the tangent vector to make it have length 1. That's called the unit tangent vector. It's denoted with a capital T, and we get it by taking r prime of t and dividing by the magnitude of r prime of t. Once we have a tangent vector, it's not too hard to find a tangent line. The tangent line is going to be the line that goes through the point r of A in the direction of the tangent vector. If the vector function r of t is given in components as above, then the point r of A can be described in terms of those components at A, and the tangent vector r prime of A can also be described in terms of the derivatives of those components at A. So the line through this point with this direction can be given with parametric equations x equals f of A plus t f prime of A, and y and z similarly. We can write the same thing more compactly if we want with a vector equation. I'll just call it w of t equals r of A plus t times r prime of A. This is exactly the same information. The components of w are just the x, y, and z coordinates of the line. Let's try an example with a vector function whose components are given by t squared, t cubed. To find r prime of 1, let's start by finding r prime of t. We do component-wise differentiation, so that's 2t, 3t squared. And so r prime of 1 we get by plugging in 1, and that's just 2, 3. We can plot the curve r of t by plotting a bunch of points. It's going to look something like this. You might also find it useful to convert it to Cartesian coordinates, since x is t squared and y equals t cubed. Solving for t and replacing, we get y equals x to the 3/2. Now at t equals 1, that's a point with x and y coordinates 1, 1, we have a tangent vector that gets over by 2 and up by 3, so that's going to be approximately this one right here. Notice that this vector does seem to be heading in the direction of the curve at this point. To find the unit tangent vector, we just take r prime and divide by its magnitude. So that's the vector 2, 3 divided by the square root of 13. Finally, to find the equation of the tangent line, we use the fact that the line goes through the point 1, 1, and we can write the equation for that line parametrically as x equals 1 plus 2t, y equals 1 plus 3t, using the direction vector r prime of 1, which is 2, 3. So now we've done a little work with derivatives of vector functions. Let's move on to integrals of vector functions. We took the derivatives of vector-valued functions by taking the derivative of each component separately. We'll do the same thing for the integrals of vector functions. In other words, the integral of a function whose components are f, g, and h can be found by integrating separately f of t dt, g of t dt, and h of t dt. Definite integrals also work just like you'd expect. For example, let's compute the integral from 1 to 2 of this vector-valued function. We know that we can do this by computing the integral of each component separately. Now the integral from 1 to 2 of 1 over t dt is ln absolute value of t evaluated between 2 and 1. That's ln2 minus ln1, or just ln2. For the second integral, the integral from 1 to 2 of e to the t dt, that's e to the t evaluated between 2 and 1, so that's e squared minus e. To compute the third integral, we can use integration by parts. Let's let u equal t, dv equal e to the t dt, then du is dt, and v is e to the t. By the integration by parts formula, we get u times v, so that's t e to the t, minus the integral of v du, that's e to the t dt. everything's still evaluated between 1 and 2. Since the integral of e to the t is just e to the t, we can evaluate this whole thing as 2e squared minus e squared minus e, which simplifies to e squared. Finally, we can put all this together to get our answer, which is just ln 2 times I plus e squared minus e times j plus e squared times k. In this video, we saw that we could take the derivative of a vector-valued function by taking the derivatives of each component separately. Similarly, the integral of a vector-valued function is the vector we get by taking the integral of each component separately. In this video, we'll calculate the length of curves given by parametric equations. As a warm-up, let's calculate the length of this curve graph below. Since it's piecewise linear, we can just calculate the length of each linear piece using the distance formula. For example, the length of the first segment is given by the square root of y2 minus y1 squared, that's 3 minus 2 squared, plus x2 minus x1 squared, that's 2 minus 1 squared, which gives us the square root of 2. Similarly, the second piece has length given by the square root of 5 minus 3 squared plus 3 minus 2 squared, which is the square root of 5. We can make similar calculations for the length of the third segment and the fourth segment. Adding these together, we get a total length of twice the square root of 5 plus the square root of 2 plus 2. We can use the same process to approximate the length of any curve by dividing it up into n small pieces, approximating each piece with a straight line, and using the distance formula to find the length of the line segments. If the curve is given by the parametric equations x equals f of t and y equals g of t, then we can write each of these points along the line in terms of f and g. For example, p of I minus 1 we can write as the x-coordinate f of t I minus 1 and the y-coordinate g of t I minus 1. And similarly, pi is going to be x-coordinate f of ti, y-coordinate g of ti. If we think of t as time, then this is just saying that t sub I is the time at which we get to point p sub I. Now the distance formula tells us that the length of the line segment from p sub I minus 1 to p sub I is going to be given by the square root of x2 minus x1 squared, that's f of t sub I minus f of t sub I minus 1 squared, plus y2 minus y1, that's g of t sub I minus g of t sub I minus 1 squared. Now the total length of the curve, which is called the arc length, is going to be approximately equal to the sum of the lengths of these segments. This is starting to look a bit like a Riemann sum, but it's missing the delta t, so I'll fix that by multiplying the numerator and the denominator by delta t. If I suck the delta t from the denominator inside the square root sign, it needs to become a delta t squared, and I get the following expression. If I break up my fractions, I can rewrite this. Now there's something kind of exciting going on. This quotient here looks a lot like a slope. In fact, it's exactly the expression for the slope of the secant line for the function f that we get if we were calculating the derivative of f with respect to t. And similarly, this expression in here is exactly the expression for the slope of the secant line we'd get if we were calculating the derivative of g with respect to t. Because these quotients here are approximately equal to f prime and g prime, or more rigorously because of the mean value theorem, I can replace my expression with f prime of ti star squared and g prime of ti star squared, where ti star is some time in the ith time interval. Now exact arc length is going to be the limit of this expression as the number of intervals goes to infinity. As usual, I can replace the limit of this Riemann sum with an integral, where the bounds of integration are the t values that get me from the start of the curve to the end of the curve. This arc length formula has an alternative form, which is the integral from a to b of the square root of dx dt squared plus dy dt squared dt. And these are my two versions of this very useful formula for arc length. Now let's use this formula to set up an integral to express the arc length of this Lissajous figure. Since dx dt is given by negative sine of t, and dy dt is given by 2 cosine of 2t, our arc length is given by the integral of the square root of sine of t squared plus 2 cosine of 2t squared dt. We do still need to figure out the bounds of integration in terms of t that'll make us wrap around this curve exactly one time. It's easy to check that when t equals 0, x is equal to 1 and y is equal to 0, so we're at this point right here. The next time that we get to this point, with an x-coordinate of 1, we need x equal cosine t to equal 1, so the next time will be when t equals 2 pi. Therefore, our bounds of integration are going to be from 0 to 2 pi. It's easy to set up this integral, but it would be very difficult to actually integrate it, and that's often the case with arc lengths. But we could use a calculator or computer to get a numerical approximation of about 9.4. In this video, we derived an equation for arc length. In previous videos, we looked at functions with one input variable and several output variables. We called these vector functions. In this video, we'll look instead at functions with several input variables and one output variable. These are called functions of several variables. Consider the function of two variables f of xy equals the square root of x times y. Notice that this function has two input variables, x and y, and when I plug in numbers for x and y, for example, 5 for x and 2 for y, I get the square root of 5 times 2, or the square root of 10, which is a real number. But not all input values for x and y give me a real number as output. For example, if I compute f of 5, negative 2, that gives me the square root of negative 10, which is not a real number. The domain of f is all values xy such that f of xy is a real number. In this example, since f involves the square root function, the domain of f will be all pairs x and y such that x times y is bigger than or equal to 0, since I can take the square root of a number that's bigger or equal to 0 and get a real number, but not the square root of a negative number. Now, x times y is greater than or equal to 0 if x and y are both positive, or if x and y are both negative, or if x or y is 0. If I graph this domain on the xy plane, it'll consist of the first quadrant, the third quadrant, and the x and y axes. To understand what the graph of the function might look like, it can be handy to look at its level curves. The level curves are the curves for which f of xy is a constant. For example, f of xy equals 1, or f of xy equals 0, or f of xy equals 5 are examples of level curves. If I use the formula for f of xy, this first level curve corresponds to square root of x times y equals 1, or in other words, x times y equals 1. I can graph this level curve on the xy plane. It looks like a hyperbola. The second level curve is where the square root of x times y equals 0. That corresponds to x times y equals 0, which is where x equals 0 or y equals 0. X equals 0 is the y-axis, and y equals 0 is the x-axis. So this level curve consists of two intersecting lines. The next level curve is where the square root of x times y is 5. That corresponds to x times y equals 25, which is also a hyperbola that goes through the point 5, 5, and negative 5, negative 5. If I think of f of xy as representing the height of a mountain at coordinates x, y, then these level curves correspond to lines of equal height, or contour lines. Let me label them with their heights. So my mountain is going up as I travel away from the origin in either direction. A function with two input variables can be represented by a graph in 3 dimensions by setting z equal to f of xy. In other words, for this example, we set z equal to the square root of xy, and we graph points of the form xyz that satisfy our equation. Remember, our graph of level curves told us that our function had height 0 along the x and y axis, and then increased in height as we went away from the origin in the first and third quadrant. I can try to translate that into a 3D graph. It might look something like this. I can get a better picture using graphing software. And here's another picture from a different angle. Notice that if I hold an x value constant and increase the y values, I get something that looks kind of like a square root curve. That agrees with our equation. If I hold x constant at, say, 5 and let y vary, then I get f of 5y is the square root of 5y, which looks like a square root curve, transformed a bit. Similarly, I can hold y fixed, say y equals 3, for example, and let x vary, and I also get a square root looking curve in this direction. That again agrees with our equation, so we're letting x vary, we're holding y at 3, we get the square root of 3x. This is a transformed square root curve in the plane y equals 3 that's parallel to the xz plane. In this video, we talked about the domain, the level curves, and the graph of the function f of xy equals the square root of xy. This video is about limits of functions of several variables. Recall limits from Calculus 1. Informally, we say that the limit as x goes to a of f of x is L if the y values, that is, the f of x values, get closer and closer to the same number L when x approaches a from either the left side or the right. Please pause the video for a moment and decide if the limit exists as x goes to 0 for each of these 4 functions. The limit does not exist for this function because there's no single number that the y values settle to. Instead, they wildly oscillate in between all numbers between 1 and negative 1 as x goes to 0. In this second picture, the limit doesn't exist either, at least not as a finite number. Since the y values increase without bound as x goes to 0, there's no finite number that these y values get closer and closer to. In this case, sometimes people say that the limit is infinity, but in any case, it doesn't exist as a finite number. In this third example, the limit does not exist because as we approach 0 from the left, the y values are equal to, and so approach -1, but as we approach 0 from the right, the y values are equal to 1. So the limits don't match, and therefore the limit doesn't exist. In this last case, the limit does exist. The limit as x goes to 0 of f of x is 0 because as the x values approach 0 from both the right side and the left side, the y values are heading towards 0 also. The issues that come up with limits in Calculus 1, things like limits going to infinity or limits being different when we approach 0 from different sides, these same issues can come up when we look at the limits of functions of several variables. For a function of two variables, informally, we say that the limit as the point xy approaches ab of f of xy is the number L if the z values, denoted by f of xy, approach the number L as xy approaches AB along any path whatsoever. So looking at the xy plane, we might have the point AB right here. There are lots of ways to approach that point AB. We could approach it from this direction or from that direction, or we could spiral around and approach it like that. And no matter what we do, the z values should be approaching that same number L. This is an informal definition. You'll see a more formal epsilon delta definition of limit in the book and in class. Sometimes it's possible to get an intuition about whether a limit exists by looking at the graph of the function. For each of these functions, try to decide if the limit as xy goes to 0, 0 of f of xy exists. The graph can help you decide, and the color on the graph is based on the height. So large z values are colored red, and smaller z values are colored blue. The green color is somewhere in between. For some of these functions, the function's value itself doesn't exist when x is 0 and y is 0. And that's why the graph turns out looking like it has a hole in it. Once you've thought about which functions have limits and which don't, please continue with the video and we'll go through each of these cases one at a time. For this function, my intuition tells me that the limit does not exist as xy goes to 0, 0. The reason is that the function is very high along the x-axis, but very low along the y-axis. So if I approach 0, 0 first along the x-axis and then along the y-axis, I'll be getting two different numbers for limits. Let's work this out mathematically. If I approach along the x-axis, then y is always 0. So I'll approach along points of the form t0, where t is going to 0. In other words, I'll be looking at the limit as t goes to 0 of t squared minus 0 squared over t squared plus 0 squared. I get this just by plugging in t for x and 0 for y in the expression for f. Now t squared over t squared is just 1, so the limit along the x-axis is 1. If I do the same sort of computation along the y-axis, that's where x is 0, I'm going to be approaching along points of the form 0t, where t is going to 0. In other words, I'll be looking at the limit as t goes to 0 of 0 squared minus t squared over 0 squared plus t squared. This simplifies to the limit of -1, which is -1. Since the limits are not the same as I approach on these two different paths, I know that the limit as xy goes to 0, 0 of my function does not exist. In this second example, my intuition tells me that the limit does exist. No matter what path I use in the xy plane to approach 0, 0, it looks like my z values are going to be going to the same value. Mathematically, we can evaluate this limit just by plugging in 0 for x and 0 for y. The justification for doing this is that we're really applying limit laws. Since the limit of my quotient is the quotient of limits, provided that the denominator is not limiting to 0, and the limit of sums is the sum of limits, and so on. Just like in Calculus 1, the limit laws allow us to break up our complicated limit into the limit of its pieces, which can then be simply evaluated by plugging in the x and y values. An alternative justification for why it's okay to plug in the numbers 0, 0 for x, y and stop there is because this function here is continuous at 0, 0, as it's a quotient of continuous functions where the denominator is not 0. And anytime you have a continuous function, you can just evaluate a limit by plugging in values. Mathematical justification aside, as a good rule of thumb, it's always a good idea to start evaluating limits just by plugging in values. And if nothing goes wrong, you can stop there. On this next example, however, we can't get away with just plugging in 0, 0 for x, y in order to evaluate the limit. Because if we do, we get a 0 over 0 indeterminate form. In fact, it appears that the limit doesn't exist as x, y goes to 0, 0, since it appears that the z values are increasing without bound, heading towards infinity, as we approach 0, 0 from this direction, and decreasing without bound, heading towards negative infinity, as we approach 0, 0 from that direction. We can work this out mathematically. First, let's approach 0, 0 on the x-axis from the positive x values. That means we're going to be approaching along points of the form t0, where t is bigger than 0 and t is approaching 0. In this case, we're taking the limit as t goes to 0 of t over t squared plus 0 squared. So that's the limit as t goes to 0. That's from the positive side, since we're assuming t is bigger than 0, of t over t squared. That's the limit of 1 over t, and that's going to be heading towards positive infinity, since we're getting numbers that are larger and larger in magnitude and positive in sign, since t is positive. Similarly, if we approach 0, 0 on the x-axis from the negative x values, then we'll be approaching along points of the form t0, where t is less than 0 and heading towards 0. In this case, the limit is going to be the limit as t goes to 0 from the minus side of t over t squared plus 0 squared, which is the limit as t goes to 0 from the minus side of 1 over t, which is negative infinity, since those fractions are always going to be negative. So we can see that the limit does not exist, just like we predicted from the graph. In this last example, it looks from the picture like the limit as xy goes to 0, 0 of our function might exist, because everything seems to be settling down in green territory as we head towards 0 from any direction. We can build up some evidence that the limit exists by approaching along different paths. For example, we might want to approach along the x-axis. That'll be points of the form t0 as t goes to 0, and we can evaluate that limit and get 0. Similarly, if we approach along the y-axis, points of the form 0t, we also get a limit of 0. If we approach along the line y equals x, that's points of the form tt, we still get a limit of 0. So we're building up a little evidence that the limit might be 0, but this is nowhere near a proof, since we haven't approached along all possible paths, and in fact we can't approach along all possible paths, since there are infinitely many of them, and they could wiggle around and do all crazy sorts of stuff before getting to the point 0, 0. One trick for justifying that the limit is 0 is turning this problem into a problem in polar coordinates. So if we set x equal to r cosine theta and y equal to r sine theta, then looking at the limit as xy goes to 0, 0 is equivalent to looking at the limit as r goes to 0 of r cosine theta cubed over r cosine theta squared plus r sine theta. squared. We can simplify this a little. And since cosine squared plus sine squared is 1 and some of the r's cancel, we can simplify this further to the limit as r goes to 0 of r cosine cubed theta. Now this is looking promising. Cosine is bounded between -1 and 1, so cosine cubed is also bounded between -1 and 1. Therefore, as r goes to 0, this whole quantity is going to have to go to 0. More formally, we can apply the squeeze theorem. We have the inequality cosine cubed theta is between 1 and -1, implies that negative r is less than or equal to r cosine cubed theta is less than or equal to r. Since the limit as r goes to 0 of negative r is 0, and the limit as r goes to 0 of r equals 0, by the squeeze theorem, the limit as r goes to 0 of the function in between also has to be 0. Therefore, our limit is 0. In this video, we worked out a few examples where limits did and did not exist for functions of several variables. The main trick that we used to show that limits do not exist was to find two different paths for which we get different limits. This is analogous to the Calculus 1 example where we might have limits that are different values when we approach from different sides. It's just now we have many different paths by which we can approach a single point. It can be a little trickier to show that limits do exist, since it's not possible to approach from every single path. Instead, the techniques we used were to use the limit laws or the continuity of the function and just plug in values. Another approach is to use polar coordinates, which can reduce the problem to a Calculus 1 kind of problem where we just have one variable, r, heading towards 0 instead of 2. In this video, I want to prove the fact that the absolute value of sine x is always less than or equal to x. Notice that if x is bigger than 1 or x is less than -1, then the absolute value of x is bigger than 1, and sine of x always has absolute value less than 1, so the formula is proved in that case for sure. So we really just need to focus on showing that the absolute value of sine x is less than or equal to the absolute value of x for x values with absolute value less than 1. To do this, let's consider the function f of x, which is sine x minus x. Notice that f of 0 is sine of 0 minus 0, so that's 0, and also f prime of x is cosine of x minus 1, which is always going to be less than or equal to 1 minus 1, or 0, since cosine of x is always less than or equal to 1. So in other words, we have a function that's 0 at the origin, and it's always either flat or decreasing. So informally, it's going to have to look something like this. In other words, it's going to have f of x be bigger than or equal to 0 for x negative, and f of x is going to be less than or equal to 0 for x positive. So let's consider the case where x is positive and less than 1 first, and then we'll consider the case where x is negative and bigger than -1 next, since we've already taken care of x values that are large in magnitude, so we don't have to worry about that. Okay, so if x is positive and less than 1, then notice that sine of x is also positive because x is between 0 and pi over 2. So we have from here, we have that f of x is less than or equal to 0, so that means that sine of x minus x is less than or equal to 0, so sine of x is less than or equal to x. But since sine of x is positive, that's the same thing as the absolute value of sine of x, and since x is positive, that's the same thing as the absolute value of x, so we have that the absolute value of sine x is less than or equal to the absolute value of x as we wanted. So now we just have to consider the possibility that x is negative, negative, but no more negative than -1. So in this case, we know that sine of x is going to be negative because x is between -pi/2 and 0. Okay, so since f of x is bigger than 0 in this case, we have sine x minus x is bigger than or equal to 0, so sine of x is bigger than or equal to x. But in this case, since x is negative, x is the same thing as negative the absolute value of x. And since sine x is negative, that's the same thing as negative the absolute value of sine x. And so we have that negative absolute value of sine x is greater than or equal to negative absolute value of x. And if I multiply both sides of that equation by -1, that reverses the inequality sign. Ta-da! We have exactly the equality I want. So we've looked at basically this case where x is big in magnitude, the case where x is between 0 and 1, and the case where x is between -1 and 0. For all those cases, we have this inequality holds, and that is the end of the proof. In the review session, we looked at the limit as xy goes to 0, 0 of sine of xy squared over x squared plus y squared. I'd like to prove that this limit is equal to 0. I'll try to do that in two different ways, using polar coordinates and using epsilon delta. To do both of these ways, I need to use the fact that sine of w for any real number w has absolute value less than or equal to the absolute value of w, which I've proved in a separate video. So first, let's do a proof using polar coordinates. So let's let x be equal to r cosine theta and y equal to r sine theta, and we'll look at the limit as r goes to 0 of sine of r cosine theta, r squared sine squared theta over r squared cosine squared theta plus r squared sine squared theta. I've just plugged in for x and y. So that's the same thing as the limit as r goes to 0 of sine of r cubed cosine theta sine squared theta divided by, or just r squared. Okay, so now I want to use the fact that the sine of, the absolute value of the sine of w is always less than or equal to the absolute value of w. So we know that sine of r cubed cosine theta sine squared theta, in particular, the absolute value of that is less than or equal to the absolute value of r cubed cosine theta sine squared theta, and that is less than or equal to the radius cubed, since the absolute value of cosine theta sine squared theta is always got to be less than 1. In other words, sine of r cubed cosine theta sine squared theta has got to be between r cubed and negative r cubed. That's just another way of writing this absolute value inequality. Okay, so now if we divide all three sides of this equation by the positive number r squared, we get that negative r is less than or equal to our quantity of interest. So I'll copy here, which is less than or equal to r. Now we can apply the squeeze theorem. So the squeeze theorem, we know that the limit as r goes to 0 of negative r has got to be 0, and the limit as r goes to 0 of r has got to be 0, and therefore, by the squeeze theorem, the limit as r goes to 0 of this middle thing has got to also equal 0. And that completes our proof using polar coordinates. Now I'm going to try to erase all this and do the same proof using epsilons and deltas. Okay, so to do a proof using epsilons and deltas, we need to start with an epsilon greater than 0, and then find a delta greater than 0 such that whenever our point is within delta distance of 0, since that's where we're going to, our function value, sine x y squared over x squared plus y squared, is going to be within epsilon of the hypothesized limit of 0. Now for this particular example, we're just going to use delta equal to let's say epsilon over 2. I think we could really actually get by with epsilon, but we'll just use epsilon over 2 just to make it look a little bit better and give us a little margin of error if we need it. Okay, so we want to show that if square root of x squared plus y squared is less than epsilon over 2, then this absolute value quantity is less than epsilon. I just dropped the 0 here, but otherwise it's just the same thing as this. Okay, so let's use our fabulous fact here and say we know that the sine of xy squared absolute value is less than xy squared's absolute value. So if we divide that by x squared plus y squared on both sides, we get this inequality, which is exactly what we're looking for. Let's write it with a single absolute value sign to make it look even more like what we're looking for. Okay, so this is just the absolute value of x times the absolute value of y squared over the absolute value of x squared plus y squared. I just split up the absolute values over the product here. And actually, I mean, I really just need the absolute value on the x, right? Because everything else in sight is already positive. So now I know that y squared is less than or equal to x squared plus y squared, right? Because adding on an x squared is only going to make y squared bigger unless x happens to be 0, in which case they're equal. So that part's definitely true. And now we also know that the absolute value of x, which is the same thing as the square root of x squared, is going to be less than or equal to the square root of x squared plus y squared. And that's just because x squared is less than or equal to x squared plus y squared by the same reasoning. So if you take the square root of both sides, both of these things are positive, you'll still have that kind of inequality. Okay, so that means that if I go back up here, we have that this is going to be less than or equal to the square root of x squared plus y squared times x squared plus y squared over x squared plus y squared. Cancel out these terms here, and I get this is less than or equal to the square root of x squared plus y squared, which by assumption, we're assuming this is less than epsilon over 2, so it's definitely less than epsilon. So in other words, as long as this is less than epsilon over 2, the thing that we're interested in is also less than epsilon over 2, and it's definitely less than epsilon. So that finishes the epsilon delta proof. Notice that this proof, like the one we did in polar coordinates, they both rely on this fact about the absolute value of sine of something being less than the absolute value of that thing itself. This video is about partial derivatives. Let's start with a numerical example. In this example, the wave height h given in this table is a function of the wind speed v in knots and the duration t in hours that the wind has been blowing at this speed. If we want to compute f of 40/20, that means the wind speed is 40 knots and it's been blowing at that speed for 20 hours. We read down in the table and get 28. I'm not sure exactly what the units are for h here, but we'll just assume that it's 28 feet. Now, if we fix the duration at t equals 20 hours, we can look at f of v20 and think of this just as a function of v. We'll call it g of v. So we can ask, what's the approximate value of the derivative dg dv and when v equals 40? Fixing the duration at 20 hours means we're reading down this column. So we want the rate of change of the numbers in this column as v varies. So for example, we can look at these two numbers and look at delta g delta v, which is 40 minus 28 over 50 minus 40, where the 50 minus 40 comes from the change in v. That amounts to 1.2 feet per knot. If instead we look at v values just less than 40, then we're looking at these two numbers, and we can calculate delta g delta v as 28 minus 17 over 40 minus 30, which gives us 1.1 feet per knot. The average of these two numbers is 1.15 feet per knot, and that gives us our best estimate of the rate of change of g, or in other words, the rate of change of f in the v direction when we hold t fixed at 20 hours. In the next problem, we're asked to do the same thing, but this time we're going to fix the wind speed at 40 knots. That means we're looking across this row. And now we want to think of f with the wind speed fixed just as a function of t. We'll call that k of t, and find dk dt, which we can approximate by the change in k over the change in t. If we use these two numbers here, we get the change in k is 31 minus 28, and this corresponding change in t is 30 minus 20. This calculates to 0.3 feet per hour. Or we can use these two numbers and get 28 minus 25 divided by 20 minus 15, which gives us 0.6 feet per hour. Taking the average, we get 0.45 feet per hour as our best estimate of the rate of change of f in the t direction when we fix v at 40. Holding one variable constant and taking the rate of change with respect to the other variable is exactly the idea behind partial derivatives. For a function of two variables, f of x, y, defined near the point AB, we can define the partial derivatives of f at the point AB as follows. When we write f sub x AB, that means we hold y fixed at b and let x vary, and compute the derivative of f of xb with respect to x when x equals a. In other words, we're computing d dx of f of xb thought of as a function of x at x equals a. When we write f sub y of ab, that means we hold x fixed at a and let y vary, and then we compute the derivative d dy of this function of y, f of ay, when y equals b. In terms of the limit definitions of derivatives, we have f sub x of ab is the limit as h goes to 0 of f of a plus h b minus f of a b over h. That's because we're letting the x variable vary and holding the y variable constant at b. If we want to do f sub y of ab, that's the limit as h goes to 0 of f of a b plus h minus f of ab over h, because now we're holding x constant at a and letting y vary. Geometrically, when we fix y constant at b and let x vary, that's like intersecting our surface z equals f of xy, drawn here, with the plane y equals b that's parallel to the xz plane. That intersection gives us a curve, which I'll draw here in purple. When we take the partial derivative in the x direction, by definition, that's taking d dx of that curve. And so it means we're taking the slope of the tangent line to that curve at the point where x equals a and y equals b. If instead we're interested in taking the partial derivative in the y direction, that's like taking the derivative d dy of the function where we hold x constant at a and let y vary. So that's the curve that we get by intersecting our surface with the plane where x is fixed at a. In other words, we're taking the derivative of that curve, which is the slope of the tangent line to that curve. To repeat, the partial derivative in the x direction is the slope of the tangent line we get by intersecting with a plane where y is fixed. The partial derivative in the y direction is the slope of the tangent line that we get when we intersect our surface with a plane where x is fixed. Fortunately, computing partial derivatives is pretty straightforward. If we want to compute f sub x, we just think of x as our variable, and we hold all other variables constant. So for this function, f of xy equals x over y, if we want to compute f sub x at any xy value, we think of x as our variable, y as our constant, and so that's just 1 over y times 1, or 1 over y. If we want to compute f sub y at any value xy, we think of y as our variable, and x as our constant. Since x over y is the same thing as x times y inverse, we can use the constant multiplication rule to keep the x on the side, and the power rule to bring down the -1 and write this as y to the -2. This simplifies to minus x over y squared. So f sub x 1, 2, by plugging in 1 for x, 2 for y, I get 1/2, and f sub y at 1, 2 is -1/4. Let's see if this checks out with our geometric intuition. Here, I've graphed our surface, z equals x over y in green, and I've intersected it with the plane y equals 2. So this curve right here is holding y constant at 2, and as that happens, as we increase in the x direction going this way, our slope does appear to be a positive number. It's tilting up. In this second oddly colored picture, I've taken the same surface and now intersected it with the plane x equals 1. So I'm holding x fixed at 1 and varying y. And then if I go in the positive y direction, that would be going this way, it looks like my surface is tilting downwards with a plausible slope of -1/4 as the equations predicted. You'll find that there are many different notations for partial derivatives, including the one that we used, this partial symbol with the curly d's. We can also talk about if z equals f of xy, then we sometimes talk about partial z partial x. We can also write f with a subscript of 1 to denote the fact that we're taking the derivative in the direction of the first variable x, or capital D sub 1, or capital D sub f. Of course, there are other corresponding notations for taking derivatives in the y direction. Partial derivatives can also be taken for functions of 3 or more variables. For example, if we have a function of 4 variables, f of x, y, z, and w, then we can take the derivative in the z direction, that's the third direction, and that means that we hold x, y, w constant, and we take dz of f of 3, 4, z, 7, evaluated when z is 2. In this video, we computed partial derivatives by thinking of holding all variables constant except for the specified variable, in this case x. This video is about the chain rule for functions of several variables. Remember the chain rule for functions of one variable. If y is a differentiable function of x, and x is itself a differentiable function of the variable t, then we can compute dy dt as dy dx times dx dt. A similar rule holds for functions of several variables. If z is a differentiable function of x and x and y themselves are differentiable functions of t, then we can write dz dt as partial of z with respect to x times dx dt plus partial of z with respect to y times dy dt. A useful way to remember this formula is to draw a tree of variables. Z is a function of x and y. X and y are both functions of t. To get the formula for dz dt, we follow each branch of the tree that terminates in the t variable. That is, we multiply dz dx by dx dt and add dz dy times dy dt. Notice that the partial symbol is used for variables that depend on more than one other variable, and the regular derivative sign is used for a variable that just depends on a single variable. Graphically, we can think of z as the height of a function of x and y. If we think of t as time, then we can think of taking a path through time along the xy plane. dz dt is telling us how our height changes over time. Partial z partial x and partial z partial y tell us how our height changes with respect to our x and y motion, and dx dt and dy dt are telling us how our x and y variables change with respect to time. Let's use the chain rule in an example. Here, w is a function of three variables, x, y, and z, and x, y, and z are all functions of t. Although we've only seen a chain rule for functions of two variables so far, the same thing works for functions of three variables. If we draw a tree diagram with w as a function of x, y, and z, and each of these variables as functions of t, and we write the derivatives on the branches, then we can just multiply down each branch that ends in t and add up our results. Please pause the video and write out the formula for yourself. You should get the following. To complete the problem, we need to calculate some derivatives. Partial w partial x is cosine of 4y squared z. Partial w partial y is negative x sine 4y squared z times 8yz. Partial w partial z is negative x sine 4y squared z times 4y squared. We also have that dx dt is 2t, dy dt is negative 1, and dz dt is 2. Putting this all together, we get an expression for dw dt. I'll simplify this a little. Now I could rewrite this further by plugging in for x, y, and z their expressions in terms of t. Then I'd have an expression for partial w partial t that was entirely in terms of the variable t. This might look a little nicer, but in general, it's not necessary to do this sort of substitution. There's also a version of the chain rule when z is a differentiable function of more than one variable, here x and y, and those variables, x and y, are themselves differentiable functions of more than one variable, here s and t. Again, I can use a tree diagram to find the formulas. Z is a function of x and y are both functions of s and t. I'll write the partial derivatives along the branches. Now to find dz ds, I just need to follow the branches of the tree that end in the variable s, here and here. That gives me the formula partial z partial s is partial z partial x times partial x partial s plus partial z partial y partial s. A similar formula for partial z partial t can be found by following the branches that end in the variable t. Notice that this last formula is really almost exactly the same as the formula on a previous page when x and y were just functions of t. And this makes sense because calculating partial z partial t is like holding s as a constant and just thinking of x and y as functions of t. As an example, let's find partial z partial s and partial z partial t in this situation. I'll start by drawing my tree diagram, which gives me the following formulas. Next, I compute my partial derivatives. Now I put it all together to compute dz ds and partial z partial t. This video was about computing partial derivatives using the chain rule and with the aid of a tree diagram. This video gives a justification of the chain rule for functions of several variables. We'll focus on one version of the chain rule in which z is a function of the variables x and y are both functions of t. This version of the chain rule says that dz dt is equal to partial z partial x times dx dt plus partial z partial y times dy dt. We can give an informal justification of the chain rule using the idea of a differential. Recall that the actual change in height of our function, delta z, is approximately equal to the change in height of the tangent plane, or the differential dz. In fact, if our function is differentiable, which we're assuming it is, then we can write delta z as equal to dz plus some epsilon, where epsilon over the square root of delta x squared plus delta y squared goes to 0 as delta x, delta y goes to 0, 0. I can rewrite this by expanding out the differential. That's f sub x delta x plus f sub y delta y. Now I'll divide all my terms by delta t, and from calculus 1 I can write dz dt is the limit as delta t goes to 0 of delta z delta t. So that's the limit of the expression above. Now the limit of delta x delta t is just dx dt, and the limit of delta y delta t is dy dt. So we're left with having to compute the limit as delta t goes to 0 of epsilon over delta t. Since I know that epsilon over the square root of delta x squared plus delta y squared is going to be heading towards 0, I'm going to multiply the numerator and the denominator of this expression by delta x squared plus delta y squared. I'll rearrange my limit, and now I'll pull the delta t inside the square root sign. As delta t goes to 0, this expression is going to 0 by the assumption that f is differentiable, and this expression is just going to the square root of dx dt squared plus dy dt squared. This is an expression having to do with arc length, but the important thing for us is that it has a finite value. If we have something that's going to 0 times something that's going to a finite value, that's just 0. And therefore, our limit, our dz dt, is just f sub x dx dt plus f sub y dy dt as wanted. This video gives a justification of the chain rule using the idea of the differential. Previously, we've looked at derivatives in the x direction and in the y direction. In this video, we'll look at derivatives in other directions. These are called directional derivatives. In this figure, lines of equal temperature are drawn on this map of Australia. The distances on the map are given by this scale. Let's assume that these temperatures are given in degrees Celsius. So the temperature at Dubbo is somewhere between 30 and 27 degrees Celsius, maybe about 28 degrees, for example. As we move from Dubbo towards Sydney, the temperature is decreasing to 27, here it's 24, and so on. If we want to find the approximate rate of change of the temperature function, f of xy, at Dubbo, going in the direction of Sydney, we can approximate it with the average rate of change. The temperature at Dubbo is about 28 degrees. Temperature at Sydney is somewhere between 24 and 21. Looks like it's closer towards the 24 line, so let's assume it's maybe 23. So the change in temperature, delta capital T, is given by 23 minus 28, or -5. But it happens over a distance of what looks like maybe about 300 kilometers. It looks like about the same distance as the scale here. So the change in distance, I'll call that delta D, is about 300 kilometers. So the average rate of change is going to be about -5 over 300 degrees per kilometer. That's about -0.0167 degrees per kilometer. Now that's the average rate of change. It gives us an approximation of the exact rate of change at Dubbo in the direction of Sydney. We could get a slightly better approximation by doing another average rate of change over a smaller distance. So if I use that red arrow and calculate the change in temperature, that's going to be about 27 minus 28, or about -1 degree. And the corresponding distance, delta d, is going to be about 50 kilometers based on the scale. So then our delta t, delta d will be about -1 over 50, or about -0.02 degrees per kilometer. Since we only have limited information about the temperature function, given by a few different contour lines, that's probably about as accurate as we could get. But for a function where we have full information, because we have a formula for the function, we could get more and more accurate estimates of the rate of change by taking smaller and smaller arrows in this direction and calculating the same change in the function divided by the change in distance. That limiting process gives us what's called the directional derivative. So the directional derivative of a function at a point x0, y0 in the direction of a unit vector, u, with components a and b, can be found by starting at the point x0, y0 and heading in the direction of the unit vector u, but traveling shorter and shorter distances along that unit vector and calculating delta f over delta d, that's the change in function over the distance, for all those shorter and shorter vectors. I'll write that as the limit as the distance goes to 0 of delta f over delta d. Now to calculate delta f, I'm going to need to figure out f's value at the terminal and initial point of each one of these vectors. Delta d, the change in distance, is just the length of the vector. Now each of these vectors goes along in the direction of u, so it can be written as a rescaled version of u. It can be written as t times u. And since u is a unit vector, by assumption, the length of t times u is just t. And since this vector starts at the initial point x0, y0, it will end at the terminal point x0 plus ta, y0 plus tb, since a and b are the components of u. Therefore, we can rewrite this limit as the limit as t goes to 0, since t is that change in distance, that length of the vector, of f of x0 plus ta, y0 plus tb, minus f of the initial point, x0, y0, divided by the length of the vector t. This limit gives the definition of the directional derivative, provided the limit exists. Please note the notation for directional derivative. It's d sub u of f at x0, y0. There's an equivalent way to write the directional derivative of f at x0, y0 in the direction of the unit vector u. It can also be written as the ordinary calculus 1 derivative d dt of f of x0 plus at, y0 plus bt, evaluated at t equals 0. Notice that we're thinking of this expression as a function of t. The reason that this definition is equivalent to the previous one follows from the ordinary calculus 1 definition of derivative. Recall that d dt of a function g of t at t equals a is given by the limit as h goes to 0 of g of a plus h minus g of a all over h. Let's apply this definition to our function. For us, since we're evaluating at t equals 0, our a is 0, so we just need to evaluate our function at 0 plus h, that is, evaluate our function at h minus our function evaluated at 0. So we have the limit as h goes to 0, our function evaluated at h, minus our function evaluated at 0. When I plug in 0 for t, I get f of x0, y0, divided by h. If you look back at the previous slide, this expression here is the exact same expression as our original definition of directional derivative, just with h in the place of t. When we write the directional derivative in this form, we can use the chain rule to gain some more insight into what it means. In the expression f of x0 plus at, y0 plus bt, I'm going to call x naught plus at our x of t, y naught plus bt our y of t, and I'll call the entire expression z. Then we have z is a function of x and x and y are both functions of t. From above, our directional derivative is d dt of this whole expression at t equals 0. In other words, our directional derivative is equal to dz dt at t equals 0. By the chain rule, this is the same thing as partial z partial x times dx dt plus partial z partial y times dy dt. Now, dx dt is just a. That's because x is x naught plus at, and x naught and a are constants, t is our variable. Similarly, dy dt is just b. So we can rewrite dx dt as a and dy dt as b. But dz dx, that's just the derivative of f with respect to x. So that can be written as f sub x. Similarly, dz dy can be written as f sub y. We now have another expression for the directional derivative, and we've proved this theorem. For the unit vector u with components a and b, the directional derivative in the direction of u is given by f sub x times a plus f sub y times b. Notice that f sub x and f sub y are evaluated at the point x naught, y naught. That follows from the chain rule. Since we're evaluating dz dt at t equals 0, we need to evaluate f sub x and f sub y at x of 0 and y of 0. But x of 0 and y of 0 is what we get when we plug in 0 for t, so that's just x naught, y naught. So far, we've talked about directional derivatives in the direction of unit vectors. If we have a vector v that's not a unit vector, then the directional derivative in the direction of v is defined as the directional derivative in the direction of u, where u is the unit vector in the direction of v. Note that we do not get the right answer if we just take f sub x times c plus f sub y times d, where c and d are the components of the original vector v. We have to rescale first before we write down that component expression. In this example, we want to find the directional derivative of f of xy equals x cosine of y at the point where x is 2 and y is 0 in the direction of this vector v with components 3 and 4. Since v is not a unit vector, I'm going to start by finding the unit vector that's in the direction of v. Since the length of v is the square root of 3 squared plus 4 squared, that's 5, my unit vector is 1/5 of the vector with components 3, 4. In other words, 3/5, 4/5. So I'm looking for d sub u of f, which is f sub x times 3/5 plus f sub y times 4/5. F sub x is equal to cosine of y, and f sub y is equal to x times negative sine y. That's negative x sine y. At the point 2, 0, f sub x is equal to cosine of 0, that's 1, and f sub y is equal to negative 2 sine of 0, that's 0. Therefore, the directional derivative is 1 times 3/5 plus 0 times 4/5, or just 3/5. In this video, we defined the directional derivative of f in the direction of the unit vector u in 3 different ways. First, as the limit, as t goes to 0, of f of x naught plus ta, y naught plus tb, minus f of x naught, y naught, all over t. That definition came from the idea of looking at average rates of change along vectors of the form t times u for smaller and smaller values of t. The second definition of directional derivative was the calculus 1 derivative of the function of t given by f of x naught plus at, y naught plus bt at t equals 0. And the third definition of directional derivative, which is the simplest and most useful, is f sub x times a plus f sub y times b. Here a and b are the components of the unit vector, and f sub x and f sub y are evaluated at x naught, y naught. This video works out the equation for the tangent plane to a surface. In Calculus 1, one way to think of the tangent line to a curve at a point is that the tangent line is the line that best approximates the curve at that point. It heads in the same direction as the curve. Usually, the tangent line lies on one side or the other of the curve at that point, but sometimes the tangent line can cut clear through the curve. Going up a dimension, we're going to talk about tangent planes to surfaces. The tangent plane to a surface at a given point, we can think of that as the plane that best approximates the surface at that point. We can also think of the tangent plane as the plane that goes in the same direction as the surface at that point. But it's a little more confusing to think about the direction of a plane, since a plane has many lines in it that all go in different directions. So it's easier to think about the perpendicular or normal direction to the plane. You can think of a tangent plane as the plane that has the same normal vector as the surface at that point. In this animation, I'm starting with a plane that doesn't approximate the surface very well, but gradually modifying it to get a good approximating plane, the tangent plane. Like with tangent lines, tangent planes usually lie on one side of the surface or the other at the point. But sometimes the tangent plane cuts right through the surface. Let's find the tangent plane to the surface z equals y squared minus x squared at the point 1, 2, 3, shown here. Intuitively, it makes sense that the tangent plane should contain tangent lines for curves on the surface that go through that point. And we'll use that intuition to build up an equation for the tangent plane. In this figure, this is the x-axis, and the z-axis is up here, so the y-axis is hidden in the back where we can't see it. The red curve corresponds to fixing x at 1 and letting y vary. Since z is equal to y squared minus x squared, if we fix x at 1, we have that z is equal to y squared minus 1. This is a curve within the vertical plane given by x equals 1. The tangent line to this curve should have slope given by dz dy at y equal 2, since we're focusing on the point here where y is 2. Since dz dy is equal to 2y, if we evaluate that at y equals 2, we get 4. That slope of 4 means as we go over by 1 unit in the y direction, our tangent line should be going up by 4 units in the z direction. Of course, that tangent vector is not going to move at all in the x direction since we're fixing x equals 1. Therefore, the tangent vector, I'll call it v, should have components 0 in the x direction, 1 in the y direction, and 4 in the z direction. I'll draw v on the picture here in orange. Moving on to the blue curve, that's the curve we get when we fix y constant and vary x. So y is going to be fixed at 2. And the blue curve corresponds to the curve where the plane y equals 2 intersects the graph of our surface. Please pause the video and do a similar computation to this one to find the tangent vector to the blue curve. Since z is equal to y squared minus x squared and y is fixed at 2, we know that the blue curve has the equation z equals 2 squared minus x squared. In other words, z equals 4 minus x squared. The slope of the tangent vector to the blue curve should be given by dz dx at x equals 1, since I'm varying x and keeping y constant, and I'm looking at the point with these coordinates, so x is 1. dz dx is equal to negative 2x, and evaluating that at x equals 1 gives a slope of negative 2. Therefore, the tangent vector in the direction of the blue curve should be given by going over 1 unit in the x direction, not moving at all in the y direction, and going down 2 units in the z direction. That's not readily apparent from the picture, where it looks like the tangent vectors may be more flat, but it's at least plausible that the tangent vector is heading downwards at that point. Now that I've found 2 vectors that should lie in the tangent plane, it's easy to find the normal vector to the tangent plane, just by taking the cross product of these 2 vectors. So I'll write n for normal vector is equal to v cross w, and compute that cross product. Expanding out, I get I times negative 2 minus j times negative 4 plus k times negative 1. In other words, my normal vector is the vector negative 2, 4, negative 1. Now that I have the normal vector to the plane and a point in the plane, it's easy to write down the equation for the plane. That will be negative 2 times x minus 1 plus 4 times y minus 2 minus 1 times z minus 3 equals 0. This equation can also be written as negative 2x plus 4y minus z is equal to 3. Here is a computer rendering of the tangent plane. Now that we've worked out one example, we can use the same steps to find the general formula for the tangent plane of a general surface z equals f of xy at a general point x naught, y naught, z naught. First, we can let x stay fixed at x naught and vary y to look at this red curve and find its tangent vector, and then we can hold y fixed at y naught to look at this curve and find its tangent vector. The red curve is given by z equals f of x naught y, and so the tangent line to that curve has slope given by dz dy at y equals y naught. That's the same thing as f sub y of x naught y at y equals y naught, or in other words, f sub y of x naught y naught. Now when we look at the blue curve, we're looking at the curve given by z equals f of x y naught. For this blue curve, we're fixing y and varying x, so it will have a tangent line with slope dz dx at x equals x naught, that is, f sub x of x y naught at x equals x naught, or in other words, f sub x at x naught y naught. The tangent vector for the red curve, I'll call it v, it's not going anywhere in the x direction. X is fixed at x naught, so its component in the x direction is 0. As we go over 1 unit in the y direction, we're going up by the slope. In other words, we're going up by f sub y, x naught, y naught, in the z direction. Similarly, we can find the vector w that's tangent to the blue curve by noticing that as we go over 1 in the x direction, y is not changing, but z is going up by the slope f sub x of x naught, y naught. As before, we can find the normal vector to the tangent plane by taking the cross product of our 2 tangent vectors. Writing this out in components, I get this, and expanding the determinant, I get f sub x at x naught, y naught times I minus negative f sub y at x naught, y naught times j plus negative k. That can be rewritten as the vector with components f sub x, f sub y, and negative 1. Since the tangent plane goes through the point x naught, y naught, z naught, I can now write down the equation of my tangent plane. This equation is more typically written by moving the z minus z naught to the other side and getting z minus z naught is equal to f sub x times x minus x naught plus f sub y times y minus y naught. Notice that f sub x and f sub y are evaluated at x naught, y naught. Notice that this formula is very analogous to the formula for a tangent line for a function of one variable. The formula for the tangent line goes y minus y naught is equal to f prime at x naught times x minus x naught. So the slope of the tangent line, f prime, plays the role of, say, f sub x in this formula. Usually, the tangent plane to a surface at a point is a good approximation of the surface near that point. We'll see in the book and in class a few examples where things can go wrong, but for now, we'll just assume that the tangent plane is a good approximation to the surface for all the surfaces that we consider. With that assumption, let's find the tangent plane for the surface z equals f of xy at the point where x and y are both 1, where the function f is given by this formula. Then we'll use the tangent plane to approximate f's value near the point 1, 1. I'll write down our formula for the tangent plane from the previous page. We know that x naught is equal to 1, y naught is equal to 1, and z naught can be found by plugging 1 and 1 into our formula for f. So that's f of 1, 1, which is 1 minus 1 times cosine of pi, which is 2. By taking partial derivatives of our function, we can work out that f sub x is equal to negative y cosine of pi y. So f sub x at the point x naught, y naught, that's f sub x at 1, 1, is equal to negative cosine of pi, which is 1. Similarly, we can work out f sub y as equal to negative x cosine of pi y plus pi xy sine of pi y, using the product rule. Therefore, f sub y at 1, 1 is equal to 1. Substituting all this information into my general formula for the tangent plane gives me that z minus 2 is equal to 1 times x minus 1 plus 1 times y minus 1. This simplifies to z equals x plus y. So this is the equation for my tangent plane at the point where x and y are both 1. Now to approximate f's value at this x and y coordinate that are both near 1, instead of plugging them into f itself and getting an exact answer, I can plug these numbers into the equation for my tangent plane, since my tangent plane is approximating my surface. That means that f of 1.02 0.97 is going to be approximately 1.02 plus 0.97, which is 1.99. In fact, if I do work out the exact answer by plugging in these numbers into the exact formula for f, I get that this expression is actually equal to about 1.985. So we can see that these two numbers are indeed close. In this video, we worked out the equation for the tangent plane to a surface at a point. The tangent plane shares a normal vector with the surface at that point and goes through that point. In most cases, we can think of the tangent plane as being a good approximation to the surface near the point. This video is about local max and min values for functions of two variables and their relationship to critical points. Recall that for a function f of x of one variable, we say that f has a local maximum at x equals a if f of a is bigger than or equal to f of x for all x near a, where near a means more precisely in an open interval around a. We say that f has a local minimum at x equals a if f of a is less than or equal to f of x for all x near a. So in this example, our function has a local maximum at x equals 1 and a local minimum at x equals 3. The definitions for functions of two variables are entirely analogous. So we say that f of xy has a local maximum at ab if f of ab is greater than or equal to f of xy for all points xy near ab. where near AB means in an open disk centered at AB. We say that f of xy has a local minimum at AB if f of AB is less than or equal to f of xy for all points xy near AB. In this example, I've graphed the function z equals f of xy, where f of xy is cosine of x plus cosine of y. Points on the graph are color-coded so that points with large z values are colored red and points with small z values are colored blue. We can see that this function has a local maximum at this peak that's colored red and local minimums at all of these valleys that are colored blue. The local maximum is at the point where x is 0 and y is 0, and this particular local min occurs at the point where x is pi and y is pi. Let me mention a bit of terminology. When we talk about a local max or min point, we mean the x, y, and z coordinates where the function has a local max or min, or sometimes just the x and y coordinates. However, when we talk about a local max or min value, then we're just talking about the z value, a single number. So in this example, since when I plug in 0 and 0 for x and y, I get a z value of 2, I can talk about the local maximum point of 0, 0, 2, or the local maximum value of 2. Recall that for a function f of x of one variable, a critical number is a number a in the domain of the function such that either f prime of a equals 0 or f prime of a does not exist. In this figure, 2 is a critical number because f prime of 2 is 0, and we also have critical numbers at about 4.5 and about 5.5 because f prime of 4.5 is 0 and f prime of 5.5 does not exist. Recall that for a function f of x of one variable, max and min points are related to critical numbers. If f of x has a local max or min at x equals a, then x is necessarily a critical number. That is, the derivative at x equals a has to either be 0 or not exist. However, if a is a critical number, then f of x may or may not have a maximum or minimum at a. For example, when we look at the graph of y equals x cubed, there is a critical number at x equals 0, since the derivative of x cubed is 3x squared, and 3x squared is 0 when x is 0. But there is no local max or min at x equals 0. So that shows that if a is a critical number, f of x may not have a local max or min at a. The situation is very similar for functions of two variables. If f of xy is a function of two variables, the point AB is called a critical point if either the partial derivatives f sub x at AB and f sub y at AB are both 0, or f sub x at AB or f sub y at AB do not exist. Max and min points are related to critical points in the same way as before. Please pause the video and circle the correct phrase to complete each of these sentences. If f of xy has a local max or local min at AB, then AB must be a critical point. But if AB is a critical point, then f of xy may or may not have a maximum or minimum at AB. Let's look at the figure to gain some understanding of why the first statement is true. If f has a local max or min at a point, for example, this local min here, then if we intersect the surface, with a vertical plane that goes parallel to the xz plane, that gives us a curve that goes in the x direction, and that curve has a local min here. Therefore, from calculus 1, this curve will have to have a first derivative that's 0 or does not exist. But that first derivative is just f sub x at a, b. Similarly, if we intersect our surface with a vertical plane parallel to the yz plane that goes through that point, then we get a curve that goes through the point in the y direction, and it will have a local minimum here. So by calculus 1, its derivative will be 0 or won't exist. But its derivative is just f sub y at ab. So each of f sub x and f sub y will either be 0 or won't exist, which means that either they're both 0 or at least one of them doesn't exist. Now to see why the second statement is true, notice that critical points for this graph occur not only at this red peak and at these blue valleys where there are local max and mins, but also at this point here. This point is called a saddle point. A saddle point is a place where f sub x and f sub y are both 0, yet there's no local max or min because the surface curves upwards in one direction and curves downwards in the other. So if you have a critical point, it may not be a local max or min because it might be a saddle, or it might be some other oddball feature, like this one. In this video, we saw that local max and min values always occur at critical points. But not all critical points correspond to local max and min values. This video is about the second derivatives test for functions of two variables. The second derivatives test helps us predict where a function has local maximum points, local minimum points, and saddle points. In calculus 1, we had a second derivative test for functions of one variable. Suppose we have a function f of x, and its second derivative is continuous in an open interval around the x value of a. Suppose also that f prime of a is 0, in other words, a is a critical number. Then, if the second derivative at a is positive, f has a local minimum at a. It's concave up. If f double prime is less than 0, then f has a local max at a. It's concave down. The second derivatives test for functions of two variables is somewhat analogous, but instead of relying only on a single second derivative, we now have several second derivatives to consider. We have f sub xx, f sub yy, f sub xy, and f sub yx. We'll need to refer to an expression involving all of these second derivatives called the discriminant. The discriminant at a point ab is given by the determinant of the expression f sub xx, f sub xy, f sub yx, f sub yy, all evaluated at the point ab. In other words, that's f sub xx, f sub yy, minus f sub yx, f sub xy, evaluated at ab. In most situations, this can be rewritten as f sub xx, f sub yy, minus f sub xy squared, since f sub yx is the same thing as f sub xy as long as these partial derivatives are continuous near the point ab. Now I can state the second derivatives test. Suppose that the second partial derivatives of f exist and are continuous in a disk around the point ab. Suppose also that the first partials, f sub x and f sub y, are 0 at the point ab. So we know that ab is a critical point. If the discriminant is positive and the second partial f sub xx is also positive, then f has a local min at the point ab. If the discriminant at ab is positive, but f sub xx is less than 0, then f has a local max at the point ab. If the discriminant is negative, then f has a saddle at ab. And if the discriminant is 0, then the second derivatives test is inconclusive. The function could have a local minimum or a local maximum or a saddle or none of these features. Although I won't prove the second derivatives test in this video, I do want to talk for a minute about why it's plausible. First of all, suppose that the discriminant is positive and f sub xx is greater than 0. You might ask, what's special about f sub xx? Why not f sub yy? Well, if you look at this expression, if f sub xx is positive and the whole discriminant is positive, then f sub yy will have to be positive also, since otherwise we'll end up with a negative discriminant. F sub xx being positive is like saying our function is concave up as we go in the x direction, and f sub yy being positive is like saying it's concave up when we go in the y direction. So it's plausible that our function is concave up in every direction and has a local minimum. If we look at the second case, the discriminant is positive and f sub xx is negative, then f sub yy will have to be negative also in order for the whole discriminant to be positive. So f sub xx being negative is like saying we're concave down as we go in the x direction, and f sub yy being negative is like saying we're concave down in the y direction. It's plausible that we're concave down in every direction and have a local max. The discriminant being negative doesn't guarantee that f sub xx and f sub yy will have opposite signs, but in the case that they do, at least, it makes sense that we'll have a saddle, because we'll be going concave up in one direction and concave down in the other. To see that the second derivatives test is inconclusive when the discriminant is 0, I encourage you to try plotting on some graphing software graphs of f of xy equals x to the fourth minus y to the fourth, g of xy equals x to the fourth plus y to the fourth, and h of xy equals negative x to the fourth minus y to the fourth. You can check that the discriminant at the point 0, 0 is 0 for all three of these functions, yet one of them has a saddle, one has a local minimum, and one has a local maximum. As a final comment, I want to point out that if you look through all of these cases carefully, you'll see there's one case that's missing. What about the situation when the discriminant is positive, but f sub xx is equal to 0? Well, if you look at the expression for the discriminant, that case is not possible. If f sub xx is equal to 0, then the discriminant has to be either negative or 0. So we really have considered all the cases. Now let's use the second derivatives test in an example. To find the local maxes and mins for this function, we first need to find the critical points, since maxes and mins can only occur at critical points. To find the critical points, we take the partial derivatives, f sub x is equal to 2x plus 2xy, and f sub y is equal to 2y plus x squared. We set those equal to 0 and solve the system of equations for x and y. The first equation can be factored to give 0 equals 2x times 1 plus y, so we know that either x is 0 or y is negative 1. Plugging those values into the second equation, if x is 0, then y has to be 0 also, so that gives us one critical point. If y is negative 1, then 0 equals negative 2 plus x squared means that x squared is 2, so x is plus or minus the square root of 2. That gives us two critical points. So the critical points are the points 0, 0, square root of 2, negative 1, and negative square root of 2, negative 1. Notice that there are no places where f sub x or f sub y do not exist, so this is all of our critical points. Now for each critical point, we need to decide if it's a local max, a local min, a saddle, or maybe none of the above. That's where the second derivatives test is helpful. To apply the second derivatives test, we need to find the discriminant. So we need to find the second partials. F sub xx is going to be 2 plus 2y. F sub xy and f sub yx are both going to be 2x, and f sub yy is going to be 2. We find the discriminant by taking the determinant of f sub xx, f sub xy, f sub yx, f sub yy. So that's the determinant of this expression, which is equal to 4 plus 4y minus 4x squared. Now, at the first critical point, the discriminant at 0, 0 is equal to 4. That's positive, and f sub xx at 0, 0 is 2, so that's also positive. So that means we're in the local min situation. At the next critical point, square root of 2, negative 1, the discriminant, by plugging in, I get 4 minus 4 minus 4 times 2, so that's equal to negative 8, which is less than 0, so we have a saddle. And finally, at the third critical point, the negative square root of 2, negative 1, we get, again, negative 8, so we have another saddle. The second derivatives test uses the discriminant to help determine the features of a graph at critical points, according to the following rules. If the discriminant is positive and f sub xx is positive at the critical point, then we have a local min. If the discriminant is positive and f sub xx is negative at the critical point, then we have a local max. If the discriminant is less than 0, then we have a saddle, and if the discriminant is equal to 0, then the test is inconclusive. This video gives a proof of the second derivatives test for distinguishing when critical points are local maximums, local minimums, or saddles. The second derivatives test applies to functions whose second partial derivatives exist and are continuous in a region around the point of interest x0, y0. That condition is so that we can apply Clairaut's theorem to say that the second mixed partials, f sub xy and f sub yx, are equal. Assuming that condition, let's suppose we have a critical point, a point x0, y0, such that the derivative in the x direction and the derivative in the y direction are both 0. We calculate the discriminant d, which is the determinant of f sub xx, f sub xy, f sub yx, and f sub yy. In other words, f sub xx, f sub yy, minus f sub xy, f sub yx, or, in other words, f sub xx, f sub yy, minus f sub xy squared, using Clairaut's theorem to write the mixed partials as equal to each other. So this is the discriminant. It's called the discriminant because it's going to help us distinguish or discriminate between what kind of feature our graph has at the critical point. If the discriminant is positive and the second partial f sub xx is also positive, then f has a local minimum at x0, y0. The condition that f sub xx is positive should remind you of the calculus 1 condition if f double prime of x0 is positive at a critical point for a calculus 1 function of one variable, then that corresponds to a local minimum. If the discriminant is once again positive, but f sub xx at the critical point is less than 0, then f has a local maximum at that critical point. Again, this should remind you of calculus 1, where if f double prime of x0 is less than 0 at a critical point, we have a local maximum. If the discriminant is less than 0, however, we have a situation that can't happen in calculus 1. We have a saddle point at x0, y0. A saddle point is neither a local maximum nor a local minimum, but it looks like a local maximum along one curve of approach, and it looks like a local minimum along another curve of approach. It can happen that the discriminant d is equal to 0 at x0, y0. If this happens, then the second derivatives test is inconclusive. No conclusion can be drawn. Please note that when applying the second derivatives test, we evaluate the discriminant at the critical point x0, y0. To prove the second derivatives test, I'm going to focus on the directional derivative of the directional derivative of f at the point x0, y0, where u is any unit vector. This is similar to looking at f sub xx or f sub yy, except we're going in an arbitrary direction, u. It's helpful to look at these directional derivatives of directional derivatives, because if d sub u of f at x0, y0 is always positive, then our surface will be concave up in every direction. And so it has to have a local min at x0, y0. If, on the other hand, d sub u of f is always negative, then the surface will be concave down in every direction, so there has to be a local max. Finally, if d sub u of f is sometimes positive and sometimes negative, then the surface will be concave up in one direction and concave down in another direction, and so it will look like a saddle. So let's calculate d sub u of f, where u is some unit vector hk. If we start by computing d sub u of f, that's the gradient of f dotted with u, so it's the vector f sub x, f sub y dotted with hk, or f sub x h plus f sub y k. Now we take the directional derivative of that quantity. So that means we take the gradient of that quantity dotted with u, or in other words, the derivative in the x direction of the quantity and the derivative in the y direction of the quantity dotted with hk. Since h and k are constants, this means we just do f sub xx times h plus f sub yx times k, and for the directional derivative in the y direction, I get f sub xy h plus f sub yyk. So now I'll just take the dot product, and I'll rewrite this by distributing, so I get f sub xx h squared plus f sub yx hk plus f sub xy hk plus f sub yy k squared. Now by Clairaut's theorem, the mixed partials are equal, so this simplifies to f sub xx h squared plus 2 f sub xy hk plus f sub yy k squared. That's my directional derivative of my directional derivative of f. Now this expression is reminding me a lot of a quadratic equation. So let me save this expression and get rid of some of the other intermediate work. And now I'm going to consider the related quadratic function g of t, which is f sub xx t squared plus 2 f sub xy t plus f sub yy. Or I could write this as g of t is a t squared plus bt plus c, where a is f sub xx, b is 2 f sub xy, and c is f sub yy. All of these second partials are considered to be evaluated at x0, y0. After we consider this regular quadratic in one variable t, we'll see how it relates back to this expression that we started with. Now you're probably familiar with the fact that a quadratic function has its own discriminant. What's kind of interesting is that the discriminant for this quadratic equation, in other words, the expression b squared minus 4ac, is actually intimately connected with the discriminant d for functions of two variables. That's because b squared minus 4ac is equal to 2 f sub xy squared minus 4 f sub xx f sub yy, which is 4 f sub xy squared minus 4 f sub x f sub yy, which is exactly negative 4 times our discriminant d. So now, if d is bigger than 0 and f sub xx is also bigger than 0, then we know that b squared minus 4ac is going to be less than 0 since it's negative 4 times d. And we still have f sub xx is bigger than 0. That means that our quadratic equation has no real solutions. In other words, our function lies all the way above the x-axis or all the way below the x-axis. But since f sub xx is also known as a, is the leading coefficient, and that's positive, we know that we actually lie above the x-axis. So g of t is positive for all values of t. So in particular, if we look at g of h over k for k not equal to 0, we know that that expression has to be bigger than 0. And so k squared g of h over k also has to be greater than 0 since we just multiplied by k squared, a positive number. Simplifying and replacing a, b, and c with their values in terms of the second partials, we get that a h squared plus b hk plus c k squared is bigger than 0, or in other words, f sub xx h squared plus 2 f sub xy hk plus f sub yy k squared is greater than 0 for all hk as long as k is not 0. And in fact, even if k is 0, then those terms will drop out and we'll just have f sub xx h squared, which has got to be positive because we're assuming f sub xx is positive. So in fact, this expression is bigger than 0 no matter what h and k is. And so we're in this situation here where this d sub u of d sub u is always positive and we have a local minimum. So we've just proved the first case of the discriminant test. The case when the discriminant is positive and f sub xx is also positive. The case when the discriminant is positive and f sub xx is negative is very, very similar. In fact, we can just switch this inequality to a less than sign and this inequality to a less than sign, and then we know since our leading coefficient a is negative, we're in the situation where the graph of the parabola has no real zeros but is pointing downwards like this. So we know that our g of any t is going to be less than 0, and so g of h over k is less than 0, and doing the same calculation, we just get the conclusion that our d sub u of d sub u is always negative. So we're in this second situation that corresponds to a local maximum. Finally, let's clear this all out and look at the situation when d is actually less than 0. So if d is less than 0, that means that for the quadratic equation, b squared minus 4ac is bigger than 0 because remember, b squared minus 4ac is negative 4 times d. So if we're graphing our parabola g of t, that means our parabola is actually going to intersect the x-axis, either look like that or maybe pointing up, something like that. In any case, we're going to have two real roots and we're going to have some t value for which g of t is negative and another t value for which g of t is positive. So I'll write that down. Now we can use these values of t1 and t2 to find unit vectors u1 with components h1, k1 for which d sub u is less than 0 and a unit vector u2 for which du sub 2 is greater than 0. Basically, we want t1 to be h1 over k1. But if we just make h1 equal t1 and k1 equal 1, sort of the standard thing to try, then that won't be a unit vector. So we have to normalize and let h1 be t1 over the square root of 1 plus t1 squared, and k1 be 1 over the square root of 1 plus t1 squared. If we do that and then plug h1 over k1 into g, and then multiply this by k1 squared on both sides, and simplify using the fact that a, b, and c are related to the second partials, then we get exactly that this k1 squared g of h1 over k1 is equal to f sub xx h1 squared plus 2 f sub xy h1 k1 plus f sub yy k1 squared. And so since we know that g of our t1 and h1 over k1 equals t1, since we know this is, what do we say, negative, then k1 squared times is negative. So our d sub uu is negative for that value of h1 and k1. And we can similarly find an h2, k2, for which the directional derivative is positive, just using the same construction with t2 instead of t1. And so therefore, we have finally made it to this last case where we have sometimes the second directional derivative is negative and sometimes it's positive, and therefore we must have a saddle. So that concludes the proof of the second derivatives test. So in this video, we proved the second derivatives test, which tells us how the discriminant helps us discriminate between whether we have a local max, a local min, or a saddle at a critical point. And the really cool thing about the proof is that this discriminant here is actually related to the discriminant for quadratic equations that tells us how many zeros a parabola has. Lagrange multipliers are a handy way for finding maximum and minimum values of a function under a constraint condition. Sometimes this is called a method of constrained optimization. Let's start by looking at an example. We want to find the rectangle of largest area that can be inscribed in the ellipse with this equation. Let me draw the ellipse. It looks something like this. And we want to consider inscribed rectangles whose sides are parallel to the x and y axes. So a rectangle might look something like this. And we want to find such a rectangle with maximum possible area. As we're considering various inscribed rectangles, a nice way to keep track of which rectangle we're talking about is by specifying the coordinates of the upper right corner, which I'll call coordinates xy. Now the area of my rectangle will be the base times the height, so that's going to be 2x times 2y, or 4xy. That's the function that I want to maximize. I'll call it f of xy equals 4xy. But because the rectangle is required to be inscribed in the ellipse, x and y are constrained to lie on the curve given by this equation. So if I let g of xy equal x squared over 4 plus y squared over 9, then my constraint condition is that g of xy has to equal 1, so that the point will lie on this curve. Let's look at the problem graphically. This blue surface is the graph of z equals 4xy. So we want to find the maximum z value on this blue surface. But we're also subject to the constraint that we need to lie on the magenta surface given by this equation. So we want the highest point on the blue surface that's also on the magenta surface. One of those points is right there. Now let's look at a two-dimensional picture of the same thing. In this picture, the light blue curves represent the level curves of our function f. That is, the curves of constant height for our blue surface. And the magenta ellipse, that's our original ellipse. In other words, it's the graph of g of xy equals 1, or constraint condition, in 2 dimensions. Now when I look at this picture, I immediately think of taking a hike. The magenta curve is like my trail projected onto the xy plane, and the blue curves are like the contour lines of my mountain. So the maximization question is asking me, where on my trail will I reach the highest point on my hike? Not the highest point on the entire mountain. That might be way over here somewhere, if there even is a maximum. But I'm just looking for the maximum constrained to walking on this trail. Please pause the video for a moment and think about where that highest point on the trail might be. Could it be, for example, right here or right here? I claim the highest point on the trail could not be at this point right here, because at this point the trail crosses a contour line. So by continuing on the trail in one direction, you have to go higher, and the other direction you have to go lower. By picking the higher direction, you're guaranteed to find a higher point on the trail, so this cannot be the maximum height point on the trail. Even this point here, even though it doesn't have a contoured line drawn through it, it seems plausible from the location of the other contour lines that there is going to be a contour line that crosses the trail here. So it's not plausible that this could be the highest point on the trail. So the only way a point on the trail could be the highest point is if there's no contour line, no level curve crossing through it. In other words, the level curve at that point has to be tangent to the trail. It looks to me like a point right here might have a level curve tangent to it. So that point right here is likely to be a highest or lowest point on the trail. So the key idea here is that the max and min points on the constraint curve can only occur where the level curves of f are tangent to the constraint curve, g of xy equals 1. But the constraint curve is itself a level curve of the constraint function g of xy, since it's where g of xy has height 1. Therefore, we need to find points where the level curves of f and g are tangent to each other. Since the level curves of f are perpendicular to the gradient of f, and the level curves of g are perpendicular to the gradient of g, we're looking for places where the gradient of f and the gradient of g are parallel to each other. So we want the gradient of f to be parallel to the gradient of g, or in other words, the gradient of f should be a multiple of the gradient of g for some number lambda. If we look at all these candidate points on the level curve, together with the places where gradient of f or gradient of g don't exist, or are 0, then we'll find all the candidate points where the maximum or minimum point on the trail might be. This is the theory behind Lagrange multipliers. Written out in more technical language, the theory of Lagrange multipliers is as follows. To find the maximum and minimum values of a function f of xy, subject to the constraint g of xy equals k for some number k, assuming that these values, extreme values, exist and that the gradient of g is not 0 on the constraint curve, we need to, first of all, find all points x0, y0 such that the gradient of f is parallel to the gradient of g, that is, where the gradient of f is a constant multiple of the gradient of g, and compare the size of our function at all these candidate points. In practice, we set up the following equations. First, we need that f sub x is equal to lambda g sub x. Second, that f sub y is equal to lambda of g sub y. This is just unpacking the equation that the gradient of f is equal to lambda times the gradient of g, since the gradient of f is the vector with components f sub x, f sub y, and the gradient of g is the vector with components g sub x, g sub y. Since we're only interested in points with this property on the constraint curve, we also need to use the third equation that gives the constraint condition. So in practice, we write down these three equations and then solve the system of equations for x, y, and lambda. In the end, we don't really care what lambda is, but the values of x and y that solve the equations, we can then plug into f and compare the size to find maximum and minimum values. For this method to work, the constraint function g must be smooth in the sense of having continuous first partials. Otherwise, we must also check any cusps or corners on our constraint curve G, where G sub x or G sub y don't exist or have discontinuities. Let's get back to our original example. Remember that our maximization function for area was 4xy, where x and y represent the coordinates of the upper right corner of our rectangle. And our constraint condition was given by g of xy equals 1, where g of xy is x squared over 4 plus y squared over 9. We need to set up the three equations. So let's find f sub x, that's 4y, f sub y, that's 4x, g sub x, that's 2x over 4, or x over 2, and g sub y, which is 2y over 9. Our three equations are now 4y equals lambda times x over 2. 4x is lambda times 2y over 9. And x squared over 4 plus y squared over 9 equals 1. There are many different ways to solve systems of equations like this. One way is to solve for lambda in the first two equations, being careful to consider separately the case when we've divided by 0. Now, setting lambdas equal to each other, we get 8y over x equals 18x over y, or x equals 0 or y equals 0. This equation simplifies to y squared equals 9/4 x squared. And if I now plug back into my third equation, I get that x squared over 4 plus 9/4 x squared over 9 is equal to 1. That simplifies to x squared over 4 plus x squared over 4 equals 1. So x squared over 2 is 1. So x squared is 2, and x is plus or minus the square root of 2. Plugging back into equation 3 again and doing some minor arithmetic gives us that y squared is equal to 9/2. So y is plus or minus 3 over square root of 2. This gives us 4 possible candidate points where the gradient of f and the gradient of g are parallel on the constraint curve. And those candidate points are square root of 2, 3 over square root of 2, minus square root of 2, 3 over square root of 2, square root of 2 minus 3 over square root of 2, and minus square root of 2, minus 3 over square root of 2. Since our original problem had to do with a rectangle whose upper right corner was in the first quadrant, the candidate points with negative x or y coordinates don't make sense. So that remains our candidate point for the maximum value. Now we sort of ignored this extra special case where x is 0 or y is 0. So let's make sure we consider that possibility. Notice that if x is 0, then looking at the first equation, y also has to be 0. And similarly, if y is 0, then looking at the second equation, we know that x is 0. But we can't have both x and y be 0 because that violates the third equation. So in fact, this is not a possibility. And the square root of 2, 3 over the square root of 2, is our only candidate point for the maximum area. To finish the problem, I'd like to find that area, and we can do that by plugging our candidate point into our function f that we're trying to maximize. So the area is going to be 4 times the square root of 2 times 3 over the square root of 2. That's an area of 12 units. In this video, we developed Lagrange multipliers. The key idea behind Lagrange multipliers is that if we want to maximize or minimize a function f subject to a constraint given by a function g, then we need to look for where the level curves of f are tangent to the constraint curve g. This happens when the gradient of f is a constant multiple of the gradient of g. This video defines integrals of functions of two variables as a limit of Riemann sums. In Calculus 1, we define the integral of a function of one variable over an interval ab as a limit of Riemann sums. We thought of the integral as representing the area under the function and above the y-axis between x equals a and x equals b. And we estimated the area by drawing a bunch of rectangles, say n rectangles for some number n, and estimating the area of each rectangle. So the area of rectangle number I, where I is some number like 1, 2, 3, etc., that's going to be equal to its base times its height. We are assuming all the rectangles have the same width, so we call that width delta x, and that's the base of our rectangle. But the height of each rectangle is different. And to find the height, we pick a sample point. For rectangle number I, we call the sample point x sub I star. It's some point on the x-axis in that little subinterval number I. And then we find the height of the rectangle by evaluating f on the sample point x sub I star. So the height is f of x sub I star. Now the total area is approximately the area of all the rectangles, so that's going to be the sum from I equals 1 to n, since there are n rectangles, of delta x times f of x sub I star. This is our Riemann sum. Finally, the actual area, the thing that's represented by this integral sign, we defined as the limit as the number of rectangles n goes to infinity of the area of the rectangles. This was our definition of the integral. Notice that notation-wise, as we pass from a limit of Riemann sums to the integral notation, our x sub I star becomes our x, and our delta x, the width of our rectangles, becomes our dx. We can use a similar method of Riemann sums to define the double integral of a function of two variables over a rectangular region where the x values go from a to b and the y values go from c to d, as drawn here. We start by dividing up the interval from a to b into, say, m little subintervals, each of width delta x. Next, we divide the interval from c to d into, say, n subintervals, each of width delta y. That gives us a total of m times n subrectangles. A typical subrectangle is shaded in here. For each subrectangle, we build a tall rectangular prism above that subrectangle whose height is given by the function evaluated at some sample point inside the subrectangle. This figure shows the collection of all these tall rectangular prisms. To estimate the double integral, which we think of as the volume under this surface and above this large rectangle, we calculate the volume of all the rectangular prisms and add them up, and then take a limit as m and n go to infinity. I can write this in mathematical notation as the limit as m and n go to infinity of the sum from I equals 1 to m and from j equals 1 to n of the volume of the rectangular prism with index numbers I and j. Remember that m is the number of subintervals in the x direction, and n is the number of subintervals in the y direction. So I is counting through in the x direction, and j is counting through in the y direction. Now, the volume of one of these little rectangular prisms is going to be the area of its base times its height. Now, the area of the base, that's the area of the little subrectangle. Sometimes we call that delta A, and we can also alternatively call it delta x times delta y, since delta x is the width in the x direction and delta y is the width in the y direction. Now the height is given by f evaluated at a sample point. So we need a notation for referring to sample points. I'm going to redraw this large rectangle with its subrectangles on a copy of the xy plane down here. Now if I want a sample point for the rectangle that's, say, 3 rectangles over and 2 rectangles up, so a sample point right in here, I can do this by first choosing an x value in the third subinterval on the x-axis. Here, I'll call that x sub 3 star, and then choosing a y value in the second subinterval. Here, I'll call that y sub 2 star. Now for the sample point that I want here, I can use x sub 3 star, y sub 2 star. Similarly, if I want a sample point way up here, now that's 5 rectangles over in the x direction and 6 up in the y direction, I can pick a sample point in the 5th subinterval here and the 6th subinterval here and call that sample point x sub 5 star, y sub 6 star. Using that notation, if I'm looking at the height for the subrectangle that's number I in the x direction and number j in the y direction, then I can call that sample point x sub I star, y sub j star. And to find the height, I just evaluate my function on that sample point. Now I'm ready to rewrite my limit expression that represents my double integral. It's going to be the limit as m and n go to infinity of the sum from I equals 1 to m, j equals 1 to n of f of x sub I star, y sub j star times delta a. Or I can rewrite delta a as delta x times delta y and get the following. This is the Riemann sum definition of the double integral. Once again, the x sub I star and y sub j star become the x and y in the integral notation, and the delta a becomes our dA. Now let's use this Riemann sum definition to estimate this double integral, where our rectangle, given here, is the rectangle where x goes in between 0 and 2, and y goes from 0 to 1. We're asked to use m equals 2 and n equals 2, so that means we want 2 rectangles in the x direction and 2 in the y direction for a total of 4 subrectangles. First, let's use sample points in the upper right corners. That means our sample points will be here, 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 and here. Those points have coordinates 1, 1/2, 2, 1/2, 1, 1, and 2, 1. We get the corresponding heights by plugging those sample points into our equation for our function. The corresponding heights are e to the minus 1/2, 2e to the minus 1, e to the minus 1, and 2e to the minus 2. Since the area of our subrectangles, delta A, is 1 times 1/2, just by taking base times height, so that's equal to 1/2, we can compute the Riemann sum by adding up the product of our heights times our delta A. This is a little easier to compute if we actually factor out our delta A, that 1/2. This adds up to a decimal approximation of about 0.99. We can do the same process using the midpoint rule by using sample points exactly in the middle of each of these subrectangles. So our sample points will be the following, and here are the corresponding heights. The area of the subrectangle delta A is still 1/2, and this time the Riemann sum works out to about 1.15. Now we could continue computing Riemann sums using larger numbers of subrectangles to get more accurate answers. But there are much easier ways of computing double integrals than using the Riemann sum definition, and we'll see how to do that in the next video. In this video, we worked out the Riemann sum definition of a double integral over a rectangle, and we used it in an example. This video is about calculating double integrals by thinking of them as repeated or iterated single integrals. First integrating in one direction, say the x direction, and then in the y direction. To see how and why this works, we'll need to think in terms of volume. Suppose we want to calculate the double integral of f of xy dA over a rectangle R. If this top surface is our graph of z equals f of xy, then we think about this double integral as representing the volume under this surface and above the rectangle, where the rectangle goes in the x direction from A to B and in the y direction from C to D. To compute this volume, we can think of slicing the volume using planes that are parallel to the YZ plane, and then adding up or integrating the areas of these cross-sectional slices. I have a cross-sectional slice for each x value between A and B, so I can think of the total volume of the solid as the integral from A to B of A of x dx, where A of x is the area of the cross-sectional slice at the x value of x. But A of x itself can be thought of as an integral. We can write A of x as the integral from the y value of c to the y value of d of f of xy dy. Here we're holding x constants, that's just telling us which slice we're talking about, and we're integrating with respect to y. If we put these two pieces together, we have that the volume, represented by the double integral, is going to be the integral from x equals a to x equals b of the integral from y equals c to y equals d of f of xy dy dx. This inner integral represents our a of x, and the outer integral, which is the volume, we get by integrating our resulting area expressions. We can do an analogous process by slicing in the other direction with planes that are parallel to the xz plane. Now, our volume is going to be the integral as y ranges from c to d of our cross-sectional area, which is now a function of y. But as before, the cross-sectional area at position y can itself be thought as an integral, now going in the x direction from x equals a to x equals b of our function dx. So putting this together, our double integral is our integral with respect to y of our integral with respect to x. This result is known as Fubini's theorem, which says that if f is continuous on this rectangle, then the double integral, defined in terms of the Riemann sum, is equal to the iterated integrals. In other words, this double integral can be written as the integral with respect to x of the integral with respect to y of our function, or it can be written as the integral with respect to y of our integral with respect to x of our function. In fact, this theorem still holds even if f is not continuous on the whole rectangle. As long as f is bounded on the rectangle, f is discontinuous only on a finite number of smooth curves, and the iterated integrals exist. Notice that Fubini's theorem actually gives us two different ways to compute a double integral. We could either integrate with respect to y first, or integrate with respect to x first. Which way we choose will usually depend on which way makes the integrals easier to compute. Let's use Fubini's theorem to calculate an exact answer for this integral that we only approximated with a Riemann sum in a previous video. We can rewrite the integral either by integrating with respect to x first, or by integrating with respect to y first. In the first situation, the bounds of integration here are going to be x values. So those bounds will be from x equals 0 to x equals 2, while the bounds on the outer integral will be y values, so that'll be from y equals 0 to y equals 1 to agree with our rectangle's bounds. If we do the integrals instead in the other direction, Now our inner integral will be y values, and the bounds for our outer integral sign will be x values. Now let's start to integrate. If we use the setup shown here on the left, then we start by integrating this inner integral. Since in integral with respect to x, we're thinking of y as a constant. We could integrate this using integration by parts, but I think it's going to be easier to use this setup shown here on the right, because now when we integrate this inner integral with respect to y, x is a constant, that's simpler to integrate. First, I'll just copy down the outside integral sign. We're not going to even mess with that for a while. And then as far as the inside integral, I can just carry down the x, which is a constant as far as this integral's point of view. And the integral of e to a power is basically going to be e to that same power. But I think I'm going to need to divide by negative x in order to make things work out right. So let's see. I'll rewrite that. Well, this is evaluated from y equals 0 to 1. I'll just rewrite this one more time. And I can check that I did the integration right by just taking the derivative of this and making sure I do, in fact, derivative with respect to y, and making sure I do, in fact, get this, the result. And it does work out because of the chain rule. So now I'll copy down my outer integral sign again. I'm going to evaluate at the bounds of integration. So that gives me minus e to the minus x minus e to the minus x times 0. I'm just plugging in y equals 1 and y equals 0. That simplifies to minus e to the minus x plus 1. Now I just need to integrate a simple function of one variable, and so that gives me e to the minus x plus x evaluated between x equals 0 and x equals 2. So I can plug in 2 for x and 0 for x, and I get a final answer of e to the minus 2 plus 1. As a decimal, that's about 1.14, which is very close to the Riemann sum approximation we got using a midpoint rule in a previous video. In this video, we learned to compute double integrals as iterated integrals, and that you could integrate in different orders. In previous videos, we integrated functions of two variables over rectangles. In this video, we'll integrate functions of two variables over more general regions, like this one. Suppose we want to find the integral of the function x squared plus 2y over the region D drawn below, bounded by the parabolas y equals 2x squared, that's the blue curve on the bottom, and y equals 1 plus x squared, that's the red curve on the top. We can think of this integral as representing the volume between the surface z equals x squared plus 2y and the xy plane above this region here. Let's imagine slicing this volume with planes perpendicular to the yz plane. That'll give us vertical cross-sections that might look something like this. The vertical cross-sections correspond to different values of x along the x-axis. So I can write a of x to represent the area of the vertical cross-section at position x. Then the total volume, or double integral, can be written as the integral of these cross-sectional areas integrated with respect to x, from x equaling the minimum x value, which looks like -1, to the maximum x value, which looks like 1. But the cross-sectional area itself can be thought of as an integral. It's the integral of my function, given here, integrated in the y direction, from the minimum y value, which is the y value on this curve, to the maximum y value, which is the y value on that curve. So I'll write that down. This expression here represents my a of x. But I still need to put down the bounds of integration, which are going to be y values. And notice how the y values that are the bounds of integration vary depending on x. So I can't just write them down as numbers, I have to write them down as functions of x. And in fact, the lower bound of integration is the y value lying on this curve, so that's 2x squared. And the upper bound of integration is the y value that lies on this red curve, so that's 1 plus x squared. Now I have an expression that I can integrate. I start from the inside and integrate this function with respect to y to get x squared y plus y squared. That's going to be evaluated between the bounds 1 plus x squared and 2x squared. Notice those bounds are things I'm going to plug in for y. I'm still going to have to integrate that answer, whatever I get, with respect to x between x equals -1 and 1. So plugging in my bounds of integration, I get x squared times 1 plus x squared plugged in for y plus 1 plus x squared squared, and that whole thing corresponds to plugging in the first bound of integration. Now I plug in the second bound of integration. That's x squared times 2x squared plus 2x squared quantity squared. All that will be integrated with respect to x. After simplifying, and simplifying some more, we're in a position to integrate, and that integral evaluates to 12/5. Let's use the same ideas to calculate the double integral of the function y over the region bounded by the straight line y equals x minus 1 and the parabola y squared equals 2x plus 6. It'll be helpful to know the coordinates of these intersection points, and since they're not obvious from the graph, we can find them by solving our two equations together. One way to do this is to plug in the expression x minus 1, which is equal to y in the first equation, in for the variable y in the second equation. So that gives that x minus 1 squared equals 2x plus 6. Distributing it out, this is x squared minus 2x plus 1 equals 2x plus 6. So x squared minus 4x minus 5 is equal to 0. I can factor this quadratic and get the x values of 5 and -1. By plugging these x values into my original linear equation, I see the corresponding y values are y equals 4 and y equals -2. So the intersection points have coordinates 5, 4, that must be this point, and -1, -2, which must be that point. Now let's work on finding the integral. As before, we can think of the double integral as representing the volume between the surface z equals y and the portion of the xy plane within this region. Actually, in this case, it's better to think of it as a net volume, since the surface z equals y lies above the xy plane for part of the region and below the xy plane for another part. In the previous example, we sliced our volume by planes parallel to the yz plane to get vertical cross-sections like this. But in this example, that would be complicated to do because some cross-sections, like this one, stretch between the blue curve and the red curve, while other cross-sections, like this one, have a base with both endpoints on the blue curve. Now that's not a total deal breaker. We could still compute our integral this way by first dividing our base into two pieces, one region over here and another region over here. But it's going to be a little simpler if we back up and use vertical cross-sections that go the other direction. So I'm going to slice with planes parallel to the xz plane and get cross-sections that look something like this. Now all of our vertical cross-sections will stretch between the blue parabola curve and the red straight line curve, which will make it easier to write out our integrals and find the bounds of integration. This time our cross-sections are indexed by the variable y, so we can write a of y as the cross-sectional area at a particular y value of y. Our double integral, or net volume, is going to be the integral as I integrate in the y direction of these cross-sectional areas. The bounds are going to go from the minimum y value that's -2, to the maximum y value of 4. But the cross-sectional area itself can be thought of as an integral going in the x direction. We're going to integrate our original function, y, from the minimum x value to the maximum x value. Now these x values that are in the bounds of integration are not fixed numbers, they depend on y. So I need to write in my bounds of integration for the left bound this x value in terms of y. Since this curve is given by this equation, I can just solve for x. So x is y squared minus 6 over 2, and that gives my left bound of integration as a function of y. And then for the right bound of integration, I can solve this equation for x. That gives me x equals y plus 1. So that's my rightmost bound of integration as a function of y. Now I'm ready to evaluate my inner integral. Remember that we're integrating with respect to x, not with respect to y. So the integral of y is yx, evaluated at the bounds of integration. And then we'll still have to integrate that answer with respect to y. So let me plug in these bounds and simplify. And I'll simplify a little further. And now I can integrate again and evaluate at my bounds of integration to get a final answer of 18. In our two examples so far, we've integrated over two types of regions. In the first type of region, looked like this, our boundary curves could be written with y as a function of x. The boundary curve satisfied the vertical line test. In the second type of region, that looked like this, our curves could be written with x as a function of y. Those boundary curves satisfy the horizontal line test. We'll call the first type of region a type 1 region and the second type a type 2 region. For the first type of region, we can take cross sections going in this direction. So we're going to integrate first in the direction of y, and our bounds of integration are going to be y values written in terms of x. So that's going to be given by those functions g of x and h of x. That gives us the cross-sectional area, and then we integrate that cross-sectional area with respect to x, where our bounds of integration are given by the minimum and maximum x values. Here that's written as a and b. For a type 2 region, we're going to integrate instead in the x direction first. So our inner integral will be dx, and our bounds of integration are x values that are written in terms of y in terms of these functions. That gives us a typical cross-sectional area, and then we integrate that in the y direction from the minimum y value, which is written as c, to the maximum y value of d. From time to time, you might encounter a region that's both a type 1 region and a type 2 region. In that situation, you get to choose which way to integrate. And you might find that one way to integrate is simpler, easier to compute than the other. You also might encounter regions that are neither type 1 regions nor type 2 regions. In that situation, a nice trick is to divide the region up into a union of type 1 and type 2 regions and integrate over each piece separately. In this video, we integrated functions over type 1 regions by integrating first in the y direction and then in the x direction. And we integrated functions over type 2 regions by integrating first in the x direction and then in the y direction. When we're integrating over a region that's circular or part of a circle, it's often easier to use polar coordinates instead of Cartesian coordinates. This video explains how. Suppose we want to integrate the function x squared y over the region D, where D is the top half of the disk with center at the origin and radius 5. It would certainly be possible to compute this integral using ordinary Cartesian coordinates, but because the boundary of the region is partly a circle, it ends up being much easier to use polar coordinates. In order to use polar coordinates, I'm going to need to convert my x's and y's to r's and thetas, using the equations x equals r cosine theta, y equals r sine theta. I'm also going to need to find the bounds of integration in terms of r and theta. Finally, instead of writing dA as dx dy, I'm going to write dA as r dr d theta. You may be wondering, why do we have this extra factor of r here? We didn't have an extra factor of x or y when we used Cartesian coordinates. I'll give an informal justification here. For a more formal justification, please see the next video. Remember that an integral is a limit of a Riemann sum. To compute the Riemann sum in Cartesian coordinates, we divide our region into little tiny Cartesian rectangles. The area of each one of these rectangles is going to be delta x times delta y, where delta x is the width in this direction and delta y is the width in that direction. But when we compute the Riemann sum in polar coordinates, we think of dividing up our region that's somewhat circular into little polar rectangles. That is, little shapes that are bounded by rays through the origin on two sides and bounded by arcs of circles on the other two sides. If two of the rays have an angle of delta theta between them, and two of the circles have a difference in radius of delta r, then the area of the little polar rectangle bounded by the rays and arcs, which I'll still call delta A, it's not equal to delta r times delta theta. Instead, it's approximately equal to delta r times r delta theta. That's because these side lengths here are approximately equal to delta r, but these side lengths here are approximately equal to r delta theta, because to get the arc length along a circle, you multiply the angular displacement by the radius to get out there. This makes sense, right? Because if you have twice as big a circle, like twice the radius, then you'd have twice the arc length to get through the same bit of angle. So this approximate area of delta r times r d theta becomes our area element, r dr d theta, when we do the integral. Now that we've outlined the setup, let's go ahead and compute this integral. First, we'll convert the x squared y that we're integrating into polar coordinates. So x is r cosine theta, and y is r sine theta. So that simplifies to r cubed cosine squared theta sine theta. Next, we need to find the bounds of integration in terms of r and theta. We can do this by writing the region in terms of polar coordinates. So this region D is the set of points with r theta, where r is between 0 and 5, since 5 is the radius of the circle, and theta is between 0 and pi, since the region extends from the positive x-axis, where theta is 0, to the negative x-axis, where theta is pi. The bounds on r and theta become our bounds of integration. R goes from 0 to 5, and theta goes from 0 to pi. I'll copy down the function that I'm integrating, so that's r cubed cosine squared theta sine theta, and then we need to include the area element, which is always r dr d theta for polar coordinates. This integral simplifies to the integral of r to the fourth cosine squared theta sine theta dr d theta. We need to integrate with respect to r first. That's our inner integral. But since cosine squared theta sine theta is a constant with respect to r, we can pull that constant multiple outside this integral sign. Furthermore, this whole integral here, once I compute it, will just be a number. So I can pull this constant multiple out of this integral sign. Now I have a product of two separate integrals, each one involving only one variable, which will make it a little bit easier to work with. This is a handy trick that always works if your original integrand is a product of a function of one variable times a function of the other variable, and your bounds of integration are all numbers. To compute the integral of r to the fourth dr, I just get r to the fifth over 5. and I can compute the integral of cosine squared theta sine theta d theta by doing a u substitution. I'll let u be cosine theta, so du is negative sine theta d theta. And I'll go ahead and convert the bounds of integration as well. So when theta is 0, u is going to be 1, and when theta is pi, u is going to be negative 1. So I'll rewrite this integral, and I'll integrate to get negative u cubed over 3, evaluated between negative 1 and 1, times the rest of my problem. After some arithmetic, this works out to 1,250 over 3. The method used in the previous problem works more generally. If f is any continuous function on a polar rectangle, by that I mean a region that's a collection of points with coordinates r and theta, where theta is between two constants and r is between two constants, then we can evaluate the integral of the function in polar coordinates by converting x in terms of r and theta, converting y in terms of r and theta, writing the area element r dr d theta, and letting r range between its bounds, a and b, and let theta range between its bounds, alpha and beta. Please do remember to write down the r dr d theta. It's easy to get into trouble by omitting the r or omitting the area element altogether. In this video, we computed the integral on a semicircular region by converting to polar coordinates. This video gives a justification for why we throw in the r dr d theta when we integrate using polar coordinates. Recall that when we integrate using polar coordinates, we convert the x's to r cosine theta, the y's to r sine theta. We put the bounds of integration in terms of r and theta, and we throw in this area element of r dr d theta. Let's see why this works. First of all, we know that an integral is really a limit of Riemann sums. In this case, since we're going to be working with polar coordinates, we divide the region that we're integrating over into a bunch of little polar rectangles by drawing a bunch of rays out from the origin that are spaced apart by an angle of delta theta, and we draw a bunch of concentric circles whose radii differ by delta r. We can imagine drawing a prism on top of each one of these polar rectangles, the height of the prism being given by the function f that we're integrating. When we add up the volumes of all these little prisms, that gives us an approximation to the integral, and the actual integral is found by taking the limit as the number of little polar rectangles that we're dividing up into goes to infinity. In this formula, we're letting m be the number of intervals in the radial direction, and n be the number of intervals in the angular direction, and the index I counts each interval in this direction, while the index j counts the intervals in this direction. So the little polar rectangle rij means I go I rectangles over in the radial direction and j over in the angular direction. So this rectangle here would actually be 1, 2, 3, 4, 5, 6, 7. In this direction, 1, 2, 3, 4, 5, 6. It would actually be R7, 6. So now the volume of the prism over polar rectangle Rij is going to be the height of the prism times the area of Rij. As usual, the height is going to be given by the function evaluated at some sample point, say Ri star theta j star. So the height is going to be given by f of Ri star cosine theta j star, Ri star sine theta j star, since that's the sample point converted into x and y coordinates, since f is a function of x and y. So we need to multiply that by the area of rectangle Rij. So next, let's work out the area of one of these little polar rectangles, Rij. If I kind of blow up part of the picture, I get this big wedge, and my polar rectangle is a piece of that wedge. The angle of the wedge is delta theta, and I'm going to call this first radius Ri minus 1, and the second larger radius I'll call Ri. Now I know that the area of a circle of radius Ri is pi times Ri squared. So the area of a wedge of radius Ri and angle delta theta, that's this whole shape here, is going to be just a fraction of the area of the circle. So, and that fraction is going to be its angle delta theta over 2 pi, since 2 pi would be the angle in the whole entire circle. That makes sense, right? Because if delta theta were, say, pi, I would have half a circle. Pi over 2 pi is a half. And if delta theta were just like a quarter of 2 pi, or pi over 2, then delta theta over 2 pi would be 1/4, and I'd have a quarter of the circle. So that gives the area of my wedge, but I just want the area of this polar rectangle. So I need to take the area of the big wedge of radius Ri and subtract the area of the smaller wedge of radius R sub I minus 1. So the area of the polar rectangle is going to be delta theta over 2 pi times pi Ri squared minus delta theta over 2 pi times pi Ri minus 1 squared. Now I'm going to simplify this by canceling out some pi's and factoring out a delta theta over 2. Now I'm going to rewrite some more by factoring out my difference of squares. Let me rearrange things a bit. Now notice that this quantity, this difference of radii, is just my delta r. I'll carry down my delta theta. And finally, this quantity here is the midpoint between r sub I and r sub I minus 1. So I can think of this midpoint as my sample point, Ri star. So in my limit of Riemann sums, I can replace this area with the formula Ri star times delta r delta theta. I'll write that down here. As I take the limit of Riemann sums and pass to integral notation, this delta r delta theta becomes my dr d theta. The r sub I star and theta sub j star just become r and theta, and my summation becomes my integral sign. So notice that this extra factor of r in my area element came from the calculation of the area of a polar rectangle as given by this quantity. This video justified the arc length element when integrating using polar coordinates by thinking about the area of a polar rectangle. A polar rectangle with angle delta theta and side length here of delta r that's out at a distance of r has area approximately equal to r delta theta times delta r. And the way I like to remember this is that the area of this rectangle is approximately this side length times that side length. This side length is the delta r, and that side length, which is the arc of a circle out at radius r, is r times the angle delta theta. This video gives one of my favorite applications of polar coordinates, computing the area under the standard normal curve. There's actually a whole family of normal curves. They differ based on where their center is and how big their spread is. The standard normal curve is the one whose mean or center is at 0 and whose spread, given by its standard deviation, is 1. And it turns out that this equation, 1 over the square root of 2 pi e to the minus x squared over 2, gives you this exact shape of the standard normal curve. The e to the minus x squared makes sense it'll be tallest when x is 0, and then it'll decay rapidly as you go on either side. And dividing by 2 turns out to be necessary to get the right spread or standard deviation. But you might wonder, what about this factor of 1 over square root of 2 pi? That's just affecting the height of the curve. Why pick that number? And why not just have a number 1 in front to make it simpler? Well, the reason that coefficient is used is in order to make the total area under this normal curve equal to exactly 1, which is exactly what you want it to be if this total area is representing a total probability. So let's prove that the area is 1. The area, I'll call it A, is given by the integral from negative infinity to infinity, since this function goes on forever in either direction, just gets kind of vanishingly small, of our function 1 over square root of 2 pi e to the minus x squared over 2 dx. Now this function, e to the minus x squared over 2, is notoriously difficult to integrate. In fact, it has no elementary antiderivative. There's no simple way to integrate it. So here's the trick. Instead of calculating a, the area, we're going to calculate a squared. So that's going to be the same integral times itself. It's hard to imagine that that would make anything easier to compute, but in fact it will. I'm going to copy the first integral over as it is, but for the second integral, it doesn't really matter whether I call this dummy variable x or y or t, so I'm going to replace that variable with y's. Next, I'm going to rewrite this product of two single variable integrals with a double integral. This is just a special case of the general principle we've seen in class, that if you have the integral of a product of two functions, one is just a function of x and the other a function of y, dx dy, that's equivalent to doing the integral f of x dx times the integral of g of y dy. You might be starting to notice now how polar coordinates might creep in to help us. Let me first bring the 1 over square root of 2 pi factors out to the front. And I can use my exponent rules to rewrite e to the minus x squared over 2 times e to the minus y squared over 2 as e to the minus x squared over 2 minus y squared over 2, since when I take the product, I add the exponents. And I'm going to start to disconnect from the x and y by rewriting dx dy as just dA. In fact, I think I'll also change my bounds of integration. Instead of writing out my bounds, x goes from negative infinity to infinity, and so does y, I'm just going to say that we're going to integrate over the entire xy plane. So I'll just write this as the integral over r, where r is the xy plane. Now let me write this in polar coordinates. So it's 1 over 2 pi, and instead of dA, I'm going to write r dr d theta. Instead of e to the minus x squared minus y squared over 2, that's the same thing as e to the minus r squared over 2. And theta, let's see, r is going to run from 0 to infinity, and theta will run from 0 to 2 pi to cover the whole xy plane. Now I've got something I can actually compute. I'm going to use the same property to split up my integral into the integral from theta equals 0 to 2 pi of d theta times the integral from r equals 0 to infinity of e to the minus r squared over 2 r dr. First integral is just theta between 2 pi and 0. And for the second integral, the integral of negative r squared over 2 r dr, I could do a u substitution, but I think I'm just going to kind of do a u substitution in my head. In other words, use a guess and check method. My guess is that this integral is just going to be e to the minus r squared over 2. And I'm going to check over here by taking the derivative. E to the minus r squared over 2. Let's see, I get e to the minus r squared over 2 times the derivative of minus r squared over 2, which is minus 2r over 2. So that's going to give me e to the minus r squared over 2 times minus r. So I was close, but I didn't quite get it right. To get it right, I'm going to need to stick a minus sign in there. Okay. Now I'm being a little sloppy when I write my bound as infinity. You can't really evaluate at infinity. What this really means is I'm doing the limit as t goes to infinity of minus e to the minus r squared over 2 between t and 0. The first bit of my expression for area squared is just 1 over 2 pi times 2 pi minus 0. So that actually cancels out to just 1. So all I have left to do is to evaluate this limit. So it's the limit as t goes to infinity of minus e to the minus t squared over 2 plus e to the minus 0 squared over 2. Well, that part's just 1. And as t goes to infinity, e to the minus t squared over 2, that's e to the minus a very large number, so that's getting vanishingly small. That part is just going to 0. So the end result is that the area squared is equal to 1, and therefore the area equals 1, just as we wanted to prove. So 1 over the square root of 2 pi turned out to be the perfect factor to make the area under our standard normal curve equal to 1, and the trick for proving it had to do with taking area, squaring it, going up a dimension, and then using polar coordinates to compute it. What genius. I've heard this proof attributed to Gauss, but I don't actually know the history of it, so if anyone else knows, please leave me a note in the comments. So I hope you enjoyed this proof that the area under the normal curve is 1. This video gives an application of integration to calculating center of mass. As a warm-up problem, let's suppose there are 4 children, Abe, Beatrice, Caledonia, and Drew, and they're all sitting on a seesaw. The children are at a distance from the left end of the seesaw of 1 meter, 3 meters, 5 meters, and 7 meters, respectively. And they have masses of 25 kilograms, 30 kilograms, 10 kilograms, and 35 kilograms. We're supposed to figure out where to put the fulcrum of the seesaw in order to make the seesaw balance perfectly, ignoring the mass of the seesaw itself. I'll call the position of the fulcrum x bar, so x bar represents the number of meters of the fulcrum from the left end of the seesaw. And I've drawn it here in between child B and child C, although it could conceivably end up being in some other interval of the seesaw. Now each child is causing a rotational force on the seesaw. The children on the left side of the fulcrum are making the seesaw want to rotate this way, and the children on the right side are making the seesaw want to rotate that way. For each child, the rotational force is proportional to their mass times the distance from the fulcrum. So child A will cause a force proportional to 25 times x bar minus 1, and child B will cause a force proportional to 30 times x bar minus 3. Assuming temporarily that the fulcrum is in between child B and child C, the forces caused by the children on the left of the fulcrum need to be counteracted exactly by the forces caused by the children on the right side of the fulcrum. So these forces here need to equal 10 times 5 minus x bar plus 35 times 7 minus x bar. This equation can be rearranged as follows. Notice that I've subtracted these two terms to the other side of the equation, but instead of creating a negative sign, I've just switched the order instead of 5 minus x bar to x bar minus 5 to account for the negative sign. And similarly, 7 minus x bar to x bar minus 7. By writing the equation in this form, we can see that the assumption in the drawing that x bar is between B and C really doesn't matter. Each of these terms has the exact same form, whether the child is on the left side or the right side of the fulcrum. To solve this equation, I'll distribute out and move my constant terms to the right side. I can factor out the x bar and divide to solve. With a little arithmetic, I get an answer of 4.1. That's how many meters from the left side I need to put my fulcrum. Notice that the numerator of my expression is equal to the sum of the masses times the distances, while the denominator is the sum of the masses. So in general, if we have n point masses located at distances x1 through xn from the left side of the seesaw, with masses m1 through mn, then to find the position x bar where we want to put the fulcrum to balance the seesaw, we can compute the sum of the mi times the xi divided by the sum of the mi. This follows from the fact that in order to get the seesaw to balance, we need the sum of the forces to be 0, and the forces are proportional to the masses times the distances from the fulcrum. Solving this equation gives us this formula for x bar. The numerator of this expression is called the moment, and the denominator represents the total mass. I want to make one final comment about this problem. I've been using the x's and the x bar to represent the distance from the left end of the seesaw, so I've been putting my 0 on my number line right here. But in fact, nothing of significance would change if I let my 0 on my number line be like somewhere over here, and my xi's and my x bar be the distance from this point. By saying that nothing of significance would change, I mean that my derivation and my final formula wouldn't change. That's because I'd still be working with the difference in positions, whether or not the positions are calculated with respect to this point or that point. Of course, while the formula wouldn't change, the final answer will change and should change. If I'm calculating everything with respect to, say, this point that's, say 3 units over, then all my numbers would have to increase by 3, and my x bar should increase by 3 as well. If you're not convinced, then I encourage you to try it yourself. The takeaway point here is that instead of talking about distances from the left side, I could just say positions. Now let's suppose we have a thin rod lying along the x-axis between x equals a and x equals b. The rod is made of a non-uniform material whose density at position x is given by a function rho of x. If we want to balance the rod, where should we put the fulcrum? Let's assume that this density is a linear density, so it's the amount of mass per unit length, in other words, something like kilograms per meter. In order to use our work from the previous problem, let's first divide our interval into a bunch of tiny little subintervals. So in typical calculus fashion, we'll assume that there are n subintervals, each of length delta x, and we'll pick a sample point, x sub I star, from each of these subintervals. So x sub I star is some point on the x-axis inside subinterval number I. So we're going to think of each subinterval as approximately like a kid on the seesaw in the previous problem. Then we can use the formula from the previous problem. X bar is going to be the moment over the total mass, which was given in the previous problem as the sum of the mi's times the xi's over the sum of the mi's, where mi represents the mass here of a subinterval and xi its position. Now the position of each subinterval is approximately equal to its sample point value. So I can write my position as xi star. And in order to figure out mi, I can just take the density times the length, and so that's going to be approximately rho at my sample point times delta x. Substituting this expression into my formula for x bar, I get the following. So x bar is approximately equal to the quotient of these two Riemann sums. And to get the exact value of x bar, I need to take the limit of the Riemann sums as the number of intervals goes to infinity. Well, the limit of a Riemann sum is an integral, so x bar is going to be the integral of rho of x times x dx divided by the integral of rho of x dx. These integrals are evaluated from the left endpoint to the right endpoint. Once again, this top expression is called the moment, and the bottom expression represents the total mass. Finally, let's suppose we have a lamina or thin sheet in the shape of a region D. The density of the lamina at a point xy is given by the function rho of xy, which we're going to assume is in units of mass per unit area, for example, something like kilograms per meter squared. As before, we want to figure out where to put the fulcrum. In this case, the fulcrum will have two coordinates, x bar and y bar. For starters, let's assume our region is in the shape of a rectangle. And let's divide it up into tiny little subrectangles. Using subintervals from I equals 1 to m in the x direction and from j equals 1 to n in the y direction. Let's also pick sample points, xi star for the subintervals in the x direction and yj star for subintervals in the y direction. So a typical sample point in one of these subrectangles would have the form xi star, yj star. Focusing first on the x direction and x bar, it seems plausible we could use the same kid on the seesaw analogy where each subrectangle functions as a kid and we're just interested in the horizontal distance between that subrectangle and x bar. So x bar should equal the sum of the masses of each subrectangle times the horizontal position of the subrectangle divided by the sum of the masses. Writing this in notation, that will be the sum over all subrectangles, so I equals 1 to m, j equals 1 to n. The mass of subrectangle is given by, approximately, given by its density at its sample point times the area, and then its horizontal position is just given by its sample point in the x direction. Let's divide that by the sum of the masses, which is given by the density at the sample points times delta A. Taking the limit of these Riemann sums as the number of subintervals goes to infinity gives x bar as an integral. The integral needs to be taken over the region D. An analogous expression can be given for y bar. And although the argument was given for a rectangular region, the same formulas work for any shape of the region. The numerator in this expression is called the moment about the y-axis and is written as m sub y, while the denominator once again represents the total mass, which I'll call capital M. Similarly, the numerator in this expression is called the moment about the x-axis and is written m sub x. So you may see the formulas in the textbook. X bar is equal to m sub y over m, and y bar is equal to m sub x over m. The way I remember that x bar, the x position, is written in terms of m sub y, the moment about the y-axis, is that x bar is the horizontal position of the fulcrum to avoid rotation around the y-axis, where y bar is the vertical position of the fulcrum to avoid rotation about the x-axis. The point x bar, y bar is called the center of mass. Finally, let's use the formulas we just derived to set up equations to find the mass and center of mass of the region enclosed by the curves x equals y squared and x equals 4 if density is given by rho of xy equals x plus y squared. I'll call this region D, and I'll write down the coordinates of these two intersection points, so that's when x equals 4 and y equals 2 or negative 2. Now the mass is going to be given as the integral of the density. So if we integrate first in the x direction and then in the y direction, we can write this as, let's see, in the x direction, we're going to be integrating from x equals y squared to x equals 4, and in the y direction, we're integrating from y equals negative 2 to 2. Since we're just interested in setup, I won't carry out the integration, but in case you're curious, it works out to 512 over 15. The center of mass means the coordinates x bar and y bar. We know that x bar is equal to the moment about the y-axis divided by the mass, and y bar is the moment about the x-axis divided by the mass. To find the moment about the y-axis, we need to integrate the density times x. And to find the moment about the x-axis, we integrate the density times y. The rest of the setup is very similar to the setup for the mass computation. We can integrate first in the x direction and then in the y direction using the same bounds of integration, and carry out the similar process for setting up the moment in the x direction. In case you're curious, m sub y works out to 2048 over 21, and m sub x works out to 0. So x bar works out to 2048 over 21 divided by 512 over 15, which simplifies to 20 over 7, whereas y bar is 0 over 512 over 15, which is 0. It's plausible that y bar should be 0 because y bar represents the vertical position that we would need to place the fulcrum to balance this region. And since both the region and the density function are symmetric with respect to the x-axis, we'd want to put the fulcrum somewhere on the x-axis. The value of x bar of 20/7 is also plausible, since 20/7 is about 3, so that puts the horizontal position of the fulcrum about here and the center of mass around this point. In this video, we use the analogy of a seesaw to figure out the center of mass of a thin rod and of a thin lamina. Previously, we defined double integrals over a rectangle or over a more general region. In this video, we'll define triple integrals over a rectangular box and over more general regions. We can define the integral of a function f of 3 variables over a rectangular box in terms of a Riemann sum. We can think of dividing the big rectangular box into a bunch of tiny, smaller rectangular boxes using, say, L subintervals in the x direction, M subintervals in the y direction, and N subintervals in the z direction. We can think of taking a sample point x sub I star from subinterval I in the x direction, y sub j star from subinterval j in the y direction, and z sub k star from subinterval k in the z direction. Then the point with coordinates x sub I star, y sub j star, z sub k star will be the coordinates of some little sub-box sitting in the middle of our big rectangular box. We can build a Riemann sum by summing over all of these little sub-boxes. So that's the sum from I equals 1 to L, that's in the x direction, from j equals 1 to m in the y direction, and from k equals 1 to n in the z direction, of the function evaluated at the sample point in that little sub-box times the volume of the sub-box. I'll call the volume of the sub-box delta v. Now, when we were doing two-dimensional integrals, we thought of the function f as representing the height of a function over a subrectangle. And here we can think of this as being the 4D height over our sub-box, although it's a little hard to visualize that. That is a way of thinking about what it represents. So you can think of this Riemann sum as representing an approximate 4-dimensional volume. Now, what I've written here is not quite right. The integral is not equal to this Riemann sum, but it is equal, by definition, to the limit of this Riemann sum as the number of sub-boxes goes to infinity. In other words, as L, M, and N go to infinity. So this is the Riemann sum definition of a triple integral, but when we go to actually computing triple integrals, we'll rarely use the Riemann sum. Instead, we'll compute them as iterated integrals, just like we did for double integrals. So we'll integrate one variable at a time. Fubini's theorem for triple integrals says that if f is a continuous function over the box B, as described above, then we can compute the integral by first integrating f of x, y, z with respect to z from z equals r to s, those are the bounds for z, and then integrating with respect to y, where y ranges between its bounds of c and d, and then integrating with respect to x, where x ranges between its bounds of a and b. But that's just one way of computing the integral. We could instead integrate in the order dz dx dy, or dx dz dy. In fact, there are 6 different orders of integration possible. I encourage you to write out all these orders for yourself. One final comment. To tie together the Riemann sum notation and the iterated integral notation, it's helpful to rewrite delta v as delta x times delta y times delta z, where delta x is the width of each subinterval in the x direction, and likewise for delta y and delta z. The delta x, delta y, delta z correspond to the dx, dy, dz below. It's also possible to compute integrals over general regions that are not boxes. For example, let's evaluate this triple integral of e to the z over y over this region. We can compute this integral as an iterated integral, integrating in any order that makes sense. To see what order might make sense, let's look at the bounds of integration. Notice that the bounds for y are numbers, but the bounds for x include the variable y, and the bounds for z include an expression that contains both the variable x and the variable y. For that reason, we need to integrate with respect to z first, then with respect to x, and finally with respect to y. When we actually integrate with respect to z and plug in the bounds of integration, we'll get rid of our variable z and just have x's and y's. Then when we integrate that in terms of x and plug in its bounds, we'll get rid of the variable x and just have y's and numbers in our expression. And finally, when we integrate with respect to y and plug in bounds, we'll replace all the y's with numbers, so we'll just have a numerical answer. Now that we've set up this integral as an iterated integral, let's do some computation. The integral of e to the z over y with respect to z is going to be just e to the z over y times y, which you can check by taking the derivative of this expression with respect to z and using the chain rule. Now I need to evaluate that between my bounds of integration, and I'll just copy down the rest of the problem. So I'll substitute in my bounds for z and simplify. Next, we need to integrate with respect to x, plug in those bounds of integration, and I'll simplify that. Now the first 3 terms are easy to integrate, but the last term is going to require integration by parts. So let me find some more space. And I'm going to evaluate this first part of my expression. Let's see, that's going to be e over 2 minus a half plus a third minus this integral. Now I'll go ahead and compute the integral using integration by parts over to the side here. So I'm going to let u equal y and dv equal e to the y dy. So then du is dy and v is e to the y. Using the formula for integration by parts, I have u times v, so that's y e to the y, minus the integral of v du, so that's e to the y dy. Of course, these are all evaluated from 0 to 1. So that's going to be y e to the y minus e to the y. And let's see, that simplifies to negative 1. So putting this all together, I get e over 2 minus a half plus a third minus 1, which is e over 2 minus 7/6. This completes the computation of this triple integral. This video covered the definition of triple integrals as a limit of Riemann sums. It covered evaluating triple integrals over rectangular boxes as iterated integrals, where you can integrate in any order you like. And it covered triple integrals over general regions, where you have to be more careful about the order of integration. In a previous video, we looked at polar coordinates in 2 dimensions and how to compute double integrals using them. In this video, we'll look at cylindrical coordinates in 3 dimensions, and we'll use cylindrical coordinates to compute some triple integrals. The cylindrical coordinates of a point P in space are given by 3 numbers, r, theta, and z, where z represents the height of the point above the xy plane, and r and theta are the polar coordinates of the projection of the point onto the xy plane. In other words, r is the radius of the projection of the point, and theta is the angle that projected point makes from the positive x-axis. As with polar coordinates, we allow r to be either positive or negative. And the negative r just means you rotate by 180 degrees around the z-axis from where the positive r would have taken you. So for example, for this point, where r is 2, theta is 2 pi over 3, and z is 1, that means our point is 1 unit above the xy plane at a radius of 2 and an angle of 2 pi over 3 from the positive x-axis. We could also have described this point using the cylindrical coordinates of -2, 5 pi over 3, and 1. Please pause the video for a moment and see if you can find equations to relate the Cartesian coordinates of x, y, and z to the cylindrical coordinates of r, theta, and z. As with polar coordinates, x is given by r cosine theta and y is given by r sine theta. Z is the same thing as z whether you're talking cylindrical or Cartesian coordinates. R squared is equal to x squared plus y squared, just like for polar coordinates, and tangent of theta is equal to y over x, just like for polar coordinates. You may have noticed that cylindrical coordinates are pretty much just the same thing as polar coordinates with the extra coordinate z added on. Please pause the video for a moment and see if you can describe the surfaces in three-dimensional space that are described by these equations in cylindrical coordinates. R equals 5 describes a cylinder of radius 5. Theta equals pi over 4 describes a plane that's at an angle of pi over 4 from the positive x-axis. It's a plane and not a half plane because r could be positive or negative. And z equals 1 describes a horizontal plane at height 1 above the xy plane, just like in Cartesian coordinates. Let's use cylindrical coordinates to describe the region above the xy plane that's bounded by the cone z equals 4x squared plus 4y squared, and by the plane z equals 6. So that's the region inside this ice cream cone-shaped figure. I think it would be helpful first to describe this cone in cylindrical coordinates. Since x squared plus y squared is the same thing as r squared, this equation translates into z squared equals 4r squared. In other words, z is plus or minus 2r. In fact, we can write this more simply as just z equals 2r. That's because each point on the cone can be described by either a positive r or a negative r by adjusting theta accordingly, and we can just assume that we're representing points on the top part of the cone by positive r's and positive z's, and the bottom part of the cone with negative r's and negative z's. Now, to describe the inside of this region, I find it handy to start with bounds for the z values in terms of the other variables, and then worry about the r and theta value bounds. Z can get as small as it is when it touches this cone and as big as when it touches the plane. That means that for the inside of the region, Z is bigger than or equal to 2r, that's what it's equal to when it's on the cone, and Z is less than or equal to 6, since that's what it is when it's on the plane. To find bounds now for r and theta, I find it handy to project this three-dimensional region onto the xy plane or the r theta plane and see what shape it spans. In this case, it'll span a circle where the radius is between 0 and 3. The 3 is because the very widest part of the region is up here, where z is 6, and since z equals 2r at this widest point on this cone, when z is 6, r will have to be 3. Theta can be absolutely anything, but I'll bound it by 0 to 2 pi to get all the way around without redundancy. So these three equations describe our region in cylindrical coordinates. Now we're ready to try a problem involving integration using cylindrical coordinates. we want to find the mass of a solid cone bounded by z equals 2r and z equals 6 if the density at any point is proportional to the distance from the z-axis. Well, this is the cone we've just been talking about. I'll draw it again. And we know that we can find mass by taking the triple integral of density. Density is proportional to the distance from the z-axis, so that means it's some constant, I'll call it k, times distance from the z-axis. Distance from the z-axis is the square root of x squared plus y squared, or, using cylindrical coordinates, we can write that as the constant times r. So we want to take the triple integral of some constant times r with respect to volume. We need to find still the bounds of integration, and we also need to write dv in terms of dr, d theta, dz. Recall that in polar coordinates, the area element dA was equal to r dr d theta. So in cylindrical coordinates, dv is going to be equal to r dr d theta dz. So we want to integrate k times r dr d theta dz. And finally, we need to put together our bounds of integration. From the previous page, we know that z is ranging between 2r and 6, r is ranging between 0 and 3, and theta is ranging between 2 pi and 0. If I write these down in this order, r on the inside, then theta, and then z, I run into a problem. My bounds for z still include other variables, namely the variable r, so I won't actually get a number or even an expression with k in it out of this integral. Instead, I better integrate in a different order. I'm going to integrate with respect to z first. After that, it doesn't really matter which order I do, since my other bounds just have constants in them. So that gives me this expression where now z goes between 2r and 6, r goes between 0 and 3, and theta goes between 0 and 2 pi. Integrating one variable at a time, I first get kr squared z, which evaluates like this. Next, I get, 2kr cubed minus kr to the 4th over 2, which simplifies to 27 halves k. And one more integration gives us 27 k times pi, where k is the constant of proportionality. The method we used in the previous problem works in general. Whenever we have a region of space that can be described by theta in terms of two constants, r in terms of two functions of theta, and z in terms of two functions of r and theta, then we can integrate a function with respect to volume using cylindrical coordinates by doing an iterated integral. Theta goes between alpha and beta, r goes between its functions of theta, and z goes between its functions of r and theta. Of course, we have to convert our function into cylindrical coordinates. We can do that by substituting in r cosine theta for x, r sine theta for y, and z just stays as z. And then we have to write our volume element dv as r dz dr d theta, using the same order as our bounds of integration. Integrating with respect to cylindrical coordinates is especially handy when our regions that we're integrating over are either cylinders or cones. Cylindrical coordinates are a lot like polar coordinates, just with an extra z coordinate attached. And the same ideas work to integrate with cylindrical coordinates. Namely, the volume element gets broken down as r dz dr d theta. We've seen how to describe points in a plane using either Cartesian or polar coordinates. And we've seen how to describe points in three-dimensional space using either Cartesian or cylindrical coordinates. In this video, we'll see how to describe points in three-dimensional space in a third way, using spherical coordinates. The spherical coordinates for a point P in three-dimensional space are given by three numbers: rho, theta, and phi. Rho gives the distance of the point from the origin. In other words, rho is the length of the line segment connecting the origin to the point. If we now project that line segment onto the xy plane, then theta gives the angle between the positive x-axis and that projected line segment. One way to think of theta, it's the same theta as in polar coordinates for the point projected onto the xy plane. Now phi is a different angle. It's this angle here, the angle between the positive z-axis and the line segment from the origin to P. For spherical coordinates, there are restrictions on the possible values of rho and phi. Rho is required to be greater than or equal to 0, and phi is required to be between 0 and pi. The coordinate theta can still take on any value. This is a little different from polar and cylindrical coordinates when both r and theta can take on any value. In this example, our point has spherical coordinates given by 2, pi over 4, and pi over 3. So 2 is our value of rho. That tells us the distance from the origin to our point. Pi over 4 is our value of theta. That tells us this angle here between the positive x-axis and the projection of this line segment onto the xy plane. And finally, our phi is pi over 3. That's this angle here from the positive z-axis down to our line from the origin to P. Please pause the video and see if you can relate the Cartesian coordinates of a point to its spherical coordinates by filling in these 6 equations. A hint is you might want to start with the equation for rho in terms of x, y, and z, and the equation for z in terms of r, theta, and phi, since those are the easiest. It might also help you to use this more general picture, which happens to have 2 right triangles sitting in it. So starting with rho, rho represents the distance between the origin and the point P, and therefore this distance is given by the square root of x squared plus y squared plus z squared. If we want to find z in terms of rho, theta, and phi, well, z is the length of this line segment here, which is one leg of this right triangle whose hypotenuse has length rho. Since the only angle I've named in this triangle is this angle here, which is phi, and z is the length of the side adjacent to phi, I'm going to pull out my trig formula for cosine and say cosine of phi, that's adjacent over hypotenuse, so that's z over rho. And therefore, z is given by rho cosine phi. Now moving on to x and y are the legs of this right triangle, whose hypotenuse is given by this line segment, labeled in the diagram with an r. In terms of this labeled angle theta, I know that x is the adjacent side to theta, so I can say cosine of theta is adjacent over hypotenuse, that's x over r, and since y is the opposite side to theta, I can say sine of theta is y over r, so that gives me x equals r cosine theta, y equals r sine theta, but there's a problem here because r is not one of our 3 spherical coordinates. The 3 spherical coordinates are rho, theta, and phi, so I still need to rewrite r in terms of rho, theta, and phi. Now r is the length of this line segment, but it's also the length of this line segment on top, since these 4 lines form a rectangle. So I can use this right triangle and the fact that r is the length of the side opposite to phi to write down the equation sine of phi is opposite over hypotenuse, so that's r over rho, and therefore r is equal to rho sine phi. Substituting this in for r, I now have that x is equal to rho sine phi cosine theta, and y is equal to rho sine phi sine theta. Finally, I can relate theta and phi to x, y, and z by thinking about the fact that tangent theta, tangent of this angle, is going to be the opposite over the adjacent. So that's y over x. Also, tangent of phi, that's going to be opposite over adjacent here. So that's r over z. But r, which is the radius in polar coordinates, is just going to be the square root of x squared plus y squared. So I have that tan phi is the square root of x squared plus y squared over z. These 6 equations are handy for getting back and forth between Cartesian coordinates and spherical coordinates. Please pause the video and decide what surfaces are described by these 3 equations. Rho equals 5 describes the set of all points that are of distance 5 from the origin. So that's a sphere of radius 5. Theta equals pi over 4 describes all points whose angle from the x-axis is pi over 4. So that's going to be a half plane at an angle of pi over 4. The reason it's a half plane and not a full plane is because rho is only allowed to be positive and phi is only allowed to be between 0 and pi, and therefore there's no way to get onto the back part of this plane. Finally, the equation phi equals pi over 6 describes all points whose angle down from the z-axis is pi over 6. So that's going to be the shape of a cone. There won't be any bottom side to this cone below the xy plane because rho is required to be positive. In this video, we describe points in terms of the spherical coordinates rho, theta, and phi. We use the following 3 equations to convert x, y, and z to spherical coordinates, and 3 more equations to relate rho, theta, and phi to x, y, and z. Spherical coordinates are a very good way to integrate over regions that are shaped like this one, sort of bounded by 2 spheres and by 2 values of phi and by 2 values of theta. To carry out an integration in spherical coordinates, we need to rewrite the volume element dv in terms of d rho, d theta, and d phi. Like with polar and cylindrical coordinates, there's a conversion factor, and in this case, dv turns out to be equal to rho squared sine phi times d rho, d theta, d phi. So we compute our triple integral as an iterated integral, where we have to convert x, y, and z in terms of rho, theta, and phi. So we do that by plugging in rho sine phi cosine theta for x, rho sine phi sine theta for y, and rho cosine phi for z. Those are based on the equations from the previous page. And then we convert our volume element dv into rho squared sine phi d rho d theta d phi. I still have to put on my bounds of integration, and in the order I wrote it here, integrating with respect to rho first, let's see, that these will be bounds in terms of rho, so I wrote that as a to b, just reading up here. And then next theta, so theta is ranging from alpha to beta, and finally phi is ranging from gamma to delta. The previous video introduced spherical coordinates, the numbers rho, theta, and phi that can be used to describe a point in space. Recall that rho represents the distance from the point to the origin, theta represents the angle between the positive x-axis and the projection of this line segment onto the xy plane, and phi represents this angle here that's between the positive z-axis and the line from the origin to the point. Recall also that we can convert x, y, and z from Cartesian coordinates into spherical coordinates using the equations x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. We'll be using these equations on the next page. Suppose we want to integrate over a region E in space that's given by these three inequalities. Rho is between two constant bounds, theta is between two constant bounds, and phi is between two constant bounds. This region of space looks something like this sort of curvy box. Because this curvy box region of space can be described more simply in terms of spherical coordinates than in Cartesian coordinates, it's going to be handy to integrate it using spherical coordinates. Now to do that, we're going to need to convert our variables x, y, and z into spherical coordinates. We're going to need to write our bounds of integration in terms of the bounds given in spherical coordinates. And we're going to need to write our volume element dv in terms of d rho, d theta, d phi. But it turns out that dv, the volume of a tiny little spherical box like this, is not equal to just d rho times d theta times d phi, the change in radius times the change in the angles. Instead, we're going to need a conversion factor, and that conversion factor turns out is equal to rho squared sine phi. I'll explain later informally where that conversion factor comes from, but for now let's just take it for granted and write out our integral. So we can write out our triple integral as an iterated integral. We convert our x, y, and z into rho, theta, and phi using the equations on the previous page. So x becomes rho sine phi cosine theta, y becomes rho sine phi sine theta, and z becomes rho cosine phi. We write out, instead of dv, we have our rho squared sine phi, d rho, d theta, d phi, and finally we write in our bounds of integration. Since I've written it in this order, with integrating with respect to rho first, my innermost bounds need to be my bounds for rho, so that's between a and b. A and b. My next integral is going to be in terms of theta, so my bounds on theta are alpha and beta, and finally my last integral is with respect to phi, and those bounds are gamma and delta. By the way, this same process works even if our bounds of integration are not all constants. For example, if our bounds of integration on rho, for example, had not been constants a and b, but had been functions a and b, functions of, say, theta and phi, then I could still write out the same thing. It's just my bounds here would also be functions of the other variables. Now I know I haven't explained where this rho squared sine phi comes from yet. Bear with me, I'm going to do an example first, and then I'll give an informal justification. Now let's use spherical coordinates to find the volume of the solid that lies within the sphere of radius 2 around the origin, and below the cone given by z equals the square root of x squared plus y squared. So that's going to be the stuff around the outside of the cone, but the inside of the sphere. First, let's describe this region, I'll call it E, in terms of spherical coordinates. We know that rho, the radius, is going to be between 2 and 0. Because we're lying below the cone and above the xy plane, phi is going to be bounded by whatever angle that is for the cone and that bigger angle of pi over 2. We know from the previous video on spherical coordinates that tangent of phi is equal to the square root of x squared plus y squared over z. So for points on the cone, where z is equal to the square root of x squared plus y squared, tangent phi is equal to 1. Therefore, phi must be equal to pi over 4, and that's going to be our lower bound for phi. Finally, theta can be anything, but to avoid redundancy, I'll just put it between 0 and 2 pi. Now to find the volume, I'm just going to integrate dv, so I'll write that out as a triple integral. I'll convert my dv to rho squared sine phi d rho d theta d phi, and I'll plug in my bounds of integration for rho, theta, and phi. Since this integrand is a product of separate functions in each variable and the bounds are all constants, it's possible to rewrite this as 3 integrals. An integral with respect to phi, an integral with respect to theta, and an integral with respect to rho. So the phi integral gets the sine phi in it. The theta integral just gets, I guess, 1. That's between 0 and 2 pi. And the rho integral gets the rho squared in it. Integrating each of these separately, the integral of sine phi is negative cosine phi. The integral of 1 is just going to be theta. And the integral of rho squared is rho cubed over 3. Evaluating these gives us square root of 2 over 2 times 2 pi times 8/3, which simplifies to 8 square root of 2 pi over 3. So now I'm going back to the previous slide, and I want to justify where the factor of rho squared sine phi comes from when we're integrating in spherical coordinates. Remember, we said that dv was not just given by d rho d theta d phi, it was given by rho squared sine phi d rho d theta d phi. So to understand where the rho squared sine phi comes from, let's take a closer look at this diagram. We want to estimate the volume, I'll call it delta v, of a tiny little spherical box. Now, the top face and bottom face of this box are given by different values of rho that differ by the amount delta rho. So the length of this blue line segment is delta rho. The side on the left and the right of this box are given by 2 different values of phi that differ by an angle delta phi. So that's the angle delta phi. And the front face and the back face are given by 2 different values of theta that differ by the angle delta theta. So delta theta is that green angle from here to here. Now the size of this spherical box is approximately equal to the length of this side times the length of that red arc times the length of the green arc. The length of the blue line segment is just delta rho. Now to find the length of the red arc, notice that this red arc is a portion of this giant red circle of radius rho. The circumference of the red circle is equal to 2 pi times its radius, so 2 pi rho. But the red arc is just a fraction of that entire circumference, and the fraction is given by the ratio of this angle, delta phi, to the entire angle of 2 pi. Therefore, the length of the red arc should be the entire circumference times that fraction, delta phi, over 2 pi. That cancels out to rho times delta phi. In fact, you might remember that formula from trig, that the length of an arc is always equal to the angle it subtends in radians times the radius of the circle. We can use the same principle to figure out the length of the green arc. It should be equal to the angle it subtends, which is delta theta, times the radius of this green circle. I'll call that radius r. So we have that the length of the green arc is equal to r delta theta, and I just need to figure out what r is in terms of my spherical coordinates. But looking at this right triangle, it has a right angle here, an angle of phi here, a hypotenuse of rho, and a side opposite to this angle of r. So based on trig, I can say sine of the angle phi is equal to opposite of our hypotenuse, so that's r over rho. And in other words, that means r is rho sine phi, which means that the length of the green arc is going to be rho sine phi delta theta. I'll copy that down up here, rho sine phi delta theta. That was my expression for delta V. Now, if I simplify things a little bit, I have 2 copies of rho, a copy of sine phi. That gives me rho squared sine phi, delta rho, delta phi, delta theta. And if I now change all my deltas to d's in the usual calculus sort of way, I get dv is going to be equal to rho squared sine phi d rho d phi d theta, which is exactly what I want, just in a slightly different order. So I've now given an informal justification of where that rho squared sine phi comes from. It comes from estimating the size of a tiny spherical box. In this video, we integrated in spherical coordinates, using the fact that dv is equal to rho squared sine phi times d rho d theta d phi. Be careful. It's easy to forget the rho squared sine phi, but you always have to stick it in. So far in this class, we've studied a lot of different kinds of functions. We studied ordinary one-variable functions, functions that go from r to r, something like f of x equals x squared, for example. So their input is one variable, and the output is one variable. You've been studying those kind of functions for a long time, certainly used them a lot in Calculus 1. At the beginning part of this class, we also studied functions that go from r to, say, r2 or r3. So their input is one variable, and their output is 2 or 3 variables. So for example, that would be something like f of t is given by the three-dimensional vector t squared, t cubed. We called those kind of functions vector functions or vector-valued functions, because we're thinking of their output as being a vector in R2 or R3. And in fact, we emphasize their vector output by putting a little vector arrow sign above the function name. Now later in the class, we started looking at functions with 2 or 3 variables as input and one variable as output. So those would be functions that take R2 to R or R3 to R. For example, something like f of xy equals x squared plus y squared, or f of xyz equals x squared z plus yz. Those would be examples of that kind of function. We looked at that kind of function when we were studying partial derivatives and gradient and doing maximization problems. So those are the 3 types of functions we've studied so far, and now you can probably guess what the next kind of function is going to be. Well, obviously it's going to be called a vector field, and it's going to have an input of 2 or 3 variables, but it's also going to have an output of 2 or 3 variables. So that would be some kind of function that takes, say, R2 to R2, or R3 to R3. Once again, because it has multiple variables as its output, we'll think of its output as being a vector, and we'll use a vector notation when talking about these kinds of functions called vector fields. So a vector field on R2 is a function f that takes R2 to R2. Or it could be a function that takes some set D to R2 where D is a subset of R2. Now for each point in the domain D, we're going to get an output that has 2 coordinates. We can think of those 2 coordinates as defining a vector. So it's kind of like we're attaching a vector or drawing a little arrow at each point in the domain. So this picture is an example of a vector field on a domain of R2. At each point we have an arrow with a direction and a length. In fact, this vector field represents wind speed. Looks like there's a storm off the coast of Florida. Similarly, a vector field on R3 is a function that takes R3 to R3. Or it could be a function that takes some set D to R3, where D is a subset of R3. Once again, we can think of the vector field on R3 as a collection of vectors or arrows, one for each point of the domain. Let's draw a picture of this vector field on R2 by drawing some arrows. I'll start by making a table of values. I'll plug in some values for x and y, and I'll figure out what the output f of xy is according to this formula here. I'll start with x equals 0, y equals 0, then f of xy is 0i plus 0j, or in components 0, 0, the 0 vector. Kind of hard to draw that one, but I'll just put a little dot here. Now when x is 1 and y is 0, then I get the vector j, or in components that's 0, 1. So at the point where x is 1 and y is 0, I have a vector going straight up in the j direction. When x is 0 and y is 1, I'm getting the vector I. So I can draw that when x is 0, y is 1, I'm going straight over in the I direction. Please pause the video and compute some other values for this table, maybe these ones. I get the following vectors as output for f. Now I'll draw them as arrows on my graph. To get a sense for what this vector field looks like, I need to draw a lot more arrows. And remember, they're not just arrows at the integer lattice points, they're also arrows when x and y are any kind of fraction in here. But my diagram is already starting to look messy, and that's partly because my vectors are so large and unwieldy. So it's a handy trick, instead of using full-size vectors, to rescale all the vectors when I draw them, so make them maybe a fourth as long as they should be. That's a trick that a lot of graphing apps will use. Other graphing apps will use color to represent the length of vectors instead of actual length, just to keep the diagram looking more neat. So I'm going to erase all the arrows I drew and draw them back again, scaled proportionally smaller. I'll compute a few more values and add a few more arrows to my diagram. So I'm starting to get a rough idea of what the vector field looks like. For a more accurate picture, it's handy to use graphing software. Here I have a picture that I made using Mathematica. And here's the same vector field graphed with the MacGrapher, where color is representing length. In this class, you won't be expected to graph a lot of vector fields by hand, but you will be expected to identify whether the output of a software program actually matches the equation given, so that you can tell when something goes horribly wrong. This video introduced vector fields, which are functions whose input is 2 or maybe 3 variables, and whose output can be thought of as a vector with 2 or maybe 3 variables. We also showed how you can represent vector fields as a bunch of arrows graphed on the plane or in space. Previously, we've talked about integrating functions over a region of the plane. In this video, we'll talk about integrating functions over a curve. The ds in this notation refers to arc length, and this integral is called a line integral with respect to arc length, even though we're integrating over a curve and not necessarily a line. In this section, we'll work with parametrized curves. That is, a curve C that's parametrized by some vector function r of t, which can be written as a function x of t, the x values, and y of t, the y values, where t ranges between two numbers a and b. We'll only consider curves that are smooth, which means that under some parameterization, r prime of t exists for the values of t that we're interested in, and r prime of t is never 0. Intuitively, a smooth curve doesn't have cusps or corners. Or we'll sometimes consider curves that are piecewise smooth. They may have cusps or corners, but they can be divided up into finitely many pieces, each of which is smooth. Now for a smooth curve in the plane, parameterized by some vector function, as follows. Let's suppose we have some function f defined on the plane. We want to find this line integral with respect to arc length. This picture is intended to give the intuition. Here's the curve down here lying in the plane, And we can think of f as giving the height of a curtain above that curve. We can think of this line integral with respect to arc length as representing the area of the curtain. Let's consider this special case first. If the function is always 1, so the curtain has constant height of 1, then this line integral, representing the area of the curtain, should be exactly equal to just the length of the curve times that constant height of 1. Since timesing by 1 unit doesn't affect the numerical value of the answer, just the dimensions, the units, then that means that this line integral should just be equal numerically to the arc length. In other words, this integral of 1 ds should just equal to the integral of dx dt squared plus dy dt squared dt, because that's how we compute arc length. Now, if instead our function always had a constant height of 3, then the area of our curtain should just be 3 times the arc length, and more generally, it seems plausible that the area of our curtain should be given by the function's value at each point on the curve times that arc length factor. And that is exactly the definition of a line integral with respect to arc length. We can think of this expression here as representing ds. If you're not familiar with this expression for computing arc length, I encourage you to go back and look at the video on arc length to see where it comes from. Let's do an example and integrate this function. So here f of xy is equal to xy over the curve given by this parameterization. First, we know that this integral is defined as the integral from a to b of our function times the arc length element. From above, we know that x of t is t squared and y of t is 2t, so x prime of t will be 2t and y prime of t will be 2. Plugging all that into this, we get the integral of t squared times 2t times the square root of 2t quantity squared plus 2 squared dt. Let me simplify this, and I'll factor out the 4 and pull it out of the square root sign. Now, I wish I could do a u substitution and just let u be the stuff inside the square root sign. The only tricky part is that the du, which is 2t dt, is not exactly appearing outside here. I'm still going to have a t squared left over. But if I just plunge ahead and try it anyway, here I'll change my bounds of integration also. So when t is 0, u is going to be 1, and when t is 1, u is going to be 2. So if I just try it anyway, we're going to get the integral from 1 to 2. My 2t dt becomes my du, so I'm going to have still a 2t squared left over. So I have 2t squared, I have my du, and then my square root becomes a square root of u. Now I need to convert this t squared into u, but that's not hard at all, because I know that t squared is u minus 1. So I can rewrite this as the integral of 2 u minus 1. I'll write this as u to the 1/2 du, and then if I simplify, grab a little more space, so that becomes twice u to the 5/2 times 2/5 minus u to the 3/2 times 2/3. Evaluated by 2 and 1, after a little arithmetic, that becomes 8/15 times the square root of 2 plus 1. Those of you who like Riemann sums will be happy to know that it's also possible to define this integral in terms of the limit of a Riemann sum. And if we do so, we get an equivalent definition. If you're interested in seeing the details, I'll put them in a separate video. I do want to draw your attention to the fact that in order to compute a line integral with respect to arc length over a curve C, you're first required to find a parameterization of the curve C. Now, there are many ways to parameterize a curve, and you might wonder, well, if you parameterize it in two different ways, do you actually get the same answer for your line integral? Well, fortunately, you do get the same answer. The line integral of f over c with respect to arc length does not depend on the parameterization of c, as long as the parameterization goes from t equals a to t equals b for some numbers a and b with a less than b. If your parameterization is going from a bigger value of t to a smaller value of t, then when you compute your line integral, you're actually going from a bigger to a smaller number. It's kind of like you're integrating backwards, and you end up getting the negative of the answer you would if your parameterization went from a smaller number to a bigger number. In this video, we defined the line integral of a function of two variables with respect to arc length as follows. Here, x of t and y of t are the components of the parameterization of the curve. So basically, all you have to do to compute one of these line integrals is to find a parameterization of the curve. And I stated, but didn't prove, that it doesn't matter which parameterization you use. Then you use that parameterization to write all your x's and y's in terms of t. Then you substitute in your arc length factor for your ds. Now that everything's just in terms of a regular integral in the variable t, you can integrate. In the previous video, we defined a line integral of a function with respect to arc length by parameterizing the curve and using this formula. I said that the line integral was supposed to represent the area of a curtain, where the base of the curtain is the curve C and the height of the curtain is given by the function f. So this formula makes intuitive sense because the area of a little piece of curtain should be given by a little piece of arc length times the height. In this video, I'll support this intuition by giving a more precise derivation of the formula using Riemann sums. Those of you who like Riemann sums will be happy to know that it's also possible to define this integral in terms of the limit of a Riemann sum. And if we do so, we get an equivalent definition. Let's see what happens. We have our curve, and we have some parameterization. Let's divide up our time interval from a to b into a bunch of little time subintervals. I'll mark the corresponding points on the curve. Remember that this integral is supposed to represent the area of a curtain over the curve with height given by the function f. In the past, we've approximated the length of the curve by drawing little straight line segments and adding up their lengths. We can do something similar here, and we can write the area of the curtain as the sum of the length of line segment I times the height of the curtain at some point ti star, where ti star is a sample point in interval number I. We add this up from I equals 1 to n, where n is the number of subintervals. Now the length of line segment I is given by the square root of x at, ti minus x at t sub I minus 1, that's the difference in x's, plus the difference in y's. So that's the length of line segment I, just using the distance formula. And now the height is given by our function. Let's assume that the length of each of these subintervals is delta t. Then I'm going to multiply each of these terms by delta t over delta t. That hasn't changed the value of my expression since I've just multiplied by 1 in a fancy form. I'll save the delta t in the numerator, but I'll suck the delta t in the denominator inside the square root sign, so it'll be a delta t squared on the inside. If I rewrite things a little and move this delta t to the end, now these expressions here are actually difference quotients. they look a lot like the definition of derivative, right? And by the mean value theorem, we can actually replace this by the derivative x prime for some t value in the middle. Of course, this Riemann sum is only an approximation of the area of the curtain, which gets closer and closer to the real area of the curtain as the number of subintervals goes to infinity. So the actual integral, the actual area of the curtain, is going to be the limit as n goes to infinity of this Riemann sum, which can be rewritten as the integral of the square root of x prime of t squared plus y prime of t squared f of x of t, y of t, dt as before. So the Riemann sum definition gives the same definition as our intuitive definition before. In this video, we wrote the area of the curtain in terms of a limit of a Riemann sum and used that to derive this formula for the line integral with respect to arc length. In a previous video, we computed line integrals with respect to arc length. These line integrals were computed over curves in the plane, and the ds represented the arc length. In this video, we'll compute a different kind of line integral. Again, it's over a curve in the plane, and we're integrating a function, but this time we're integrating with respect to x or with respect to y. In this video, we computed line integrals with respect to x and with respect to y by first parametrizing the curve c and writing everything in terms of the parameter. To compute the line integral of a function over a curve with respect to x or y, we first have to parameterize the curve. Then, like when we were doing line integrals with respect to arc length, the next step is to write everything in terms of the parameter, t. So we put our bounds of integration in terms of t. We write x and y in terms of their formulas in terms of t. And finally, we need to write dx in terms of t. Using differential notation, when x is a function of t, then dx is going to equal x prime of t dt. So substituting in x prime of t dt for dx gives us our definition of the line integral with respect to x. And we have a similar formula when we integrate with respect to y. The integral between the t bounds of f, where x is written in terms of t and y is written in terms of t, and then dy is y prime of t dt. Finally, if we want to compute a line integral of this form that has both a dx component and a dy component, we just compute it by breaking up the integral into two parts. So we write this as the integral of the dx part plus the integral of the dy part, and then we use the preceding two formulas to rewrite those in terms of t. This will all make a lot more sense once we do an example. The last step in doing these line integrals, once we've got everything in terms of the parameter t, we just integrate using regular Calculus 1 techniques. Although our first step was to parameterize the curve, there are lots of ways of doing this, and it certainly looks like the integral might depend on the functions we use to parameterize it. It turns out that the line integral with respect to x and the line integral with respect to y are independent of the parameterization. It doesn't matter what parameterization you use, you still get the same answer, provided that the parameterizations traverse c in the same direction. So you want both your parameterizations to go in the direction of the arrow this way, or both go in the opposite direction. If one goes in one direction and one goes the opposite direction, then your integrals end up being the negatives of each other. Now that we've got the definitions written out in the abstract, let's bring some life to them with an example. So we want to compute the integral of y dx plus x dy over the curve c, where c is the line segment between these 2 points. There are many ways to parameterize the line segment, but a natural parameterization is to let x of t be 1 plus 3t and y of t be negative 1 plus 4t. I came up with those parameterizations by starting at the first point where x is 1 and y is -1, and then looking at how fast x has to go to travel between its first value of 1 and its last value of 4 in unit time. It has to go 3 units in say 1 second, so that's sort of a speed of 3 units per second. That gives me the 1 plus 3t. And y, on the other hand, has to go all the way from -1 to 3, so that's 4 units in a second. So that's a speed of 4 units per second, so that gives us the -1 plus 4t for the parameterization of y. One convenient thing about this parameterization is that t is going to range in between 0 and 1. Notice that when t is 0, I'm at this initial point where x is 1, y is -1, and when t is 1, I've gone all the way to the end where x is 4 and y is 3. Now, based on the definitions on the previous page, we can write this integral by breaking it up into 2 pieces. So we can write it as the integral of y dx plus the integral of x dy. Now we can resolve these 2 integrals by writing everything in terms of t. We've already got y and x written in terms of t, but we need dx and dy. So I'll go ahead and write those down. Let's see. Dx is going to be x prime of t dt. So that's going to be the derivative of x with respect to t is just 3. So it's 3 dt. Similarly, dy is going to be y prime of t dt. So dy, that's the derivative of y with respect to t. That's just 4 dt. Now we're ready to substitute in and write everything in terms of t. So first, we can write our bounds of integration in terms of t. It goes from t equals 0 to t equals 1. Y, the formula of y in terms of t is -1 plus 4t, and we saw that dx is just 3 dt. The second integral resolves similarly. T goes from 0 to 1. X is equal to 1 plus 3t, and dy we calculated as 4 dt. From here, we have a pretty routine integration problem. I'll pull out the 3 and integrate to get minus t plus 2t squared. And I'll pull out the 4 and integrate to get t plus 3t squared over 2. Evaluating gives an answer of 13. In this video, we worked out integrals over a curve C with respect to x and with respect to y by first parameterizing the curve C and then using the parameterization to write everything in terms of the parameter t. By doing this, we got the following formulas. These formulas are easy to remember if you remember the differential notation that dx is x prime of t dt and dy is y prime of t dt. In this video, we'll address the question of whether line integrals are affected by the parameterization of the curve. We'll prove that in general, the answer is no, except in some cases, one parameterization will give you a positive value and another parameterization will give you a negative value for the line integral. Recall that a parameterized curve can be thought of as a vector-valued function that takes some interval of real numbers from a to b into either R2 or R3. If we're working in R2, we can think of R of t as having components R1 of t and R2 of t. We'll work only with smooth parameterizations. By that I mean that R prime of t is continuous and R prime of t is never 0. A nice fact about smooth parameterizations that I won't prove is that they're invertible. And this implies that if we have another parameterization, q, taking another interval, say cd to R2, then we can rewrite R of t as q of phi of t, where phi is some function that takes the interval ab to the interval cd. We can think of phi as matching up points in the interval AB and points in the interval CD that hit the exact same point in the image curve. This is called a reparameterization of the curve. we will be working with smooth reparameterizations, that is, phi prime of t is continuous and is never equal to 0. I want to make an important distinction between two types of reparameterizations. We could have a parameterization of a curve and a reparameterization that both go in the same direction. They both start at the same initial point, which I could call R of A or Q of C, and they both end in the same point, which I could call R of B or Q of D. On the other hand, we could have instead two parameterizations that go in opposite directions. So in this case, R starts down here, so this point is R of A, and R ends here at R of B, but Q starts up here, so this is also Q of C, and the point down here is Q of D. In the same direction situation, we have that phi of A is C and phi of B is D. This follows from the picture where R of A is Q of C and the reparameterization formula. Therefore, if I draw a picture of Q, here's the interval AB, remember that A is less than B, and here's the interval CD, remembering that C is less than D. Since phi of A is C and phi of B is D, my function phi must connect this point to this point, so it must be an increasing function. Phi of t must be bigger than 0 for all t, if we recall that phi of t can't be equal to 0. In the other case, where the parameterizations are in opposite directions, we have from the picture that R of A equals Q of D. And so looking at this formula here, R of A is Q of D, so phi of A must be D. And similarly, phi of B is C. And now if I draw the picture, phi of A is D, so this point is on the graph of phi, and phi of B is C, so that point is on the graph. And since phi prime can't be 0, phi must be decreasing, and phi prime must be negative for all t. We'll see that this key idea about parameterizations that go in the same direction versus parameterizations that go in opposite directions is what determines whether line integrals are affected by the parameterization of the curve in terms of their positive and negative sign. First, let's tackle line integrals with respect to arc length. Suppose that R of t is one parameterization of the curve C and Q of W is another parameterization. Then the line integral with respect to arc length will have the same value using either parameterization, assuming we always compute integrals from the smaller value of the parameter to the larger. So we always do things like integrate from 1 to 2 instead of from 2 to 1. If we integrate from 2 to 1, of course, we'll get the negative of what we would if we'd integrated from 1 to 2. To prove that parameterization doesn't matter, we'll use the reparameterization formula. So we know that R of t is equal to Q of phi of t for our reparameterization function phi. Let me write out the definition of the line integral with respect to arc length using the parameterization R. So by definition, that's the integral from t equals a to t equals b of f of R of t times the norm of R prime of t dt. Using the reparameterization formula, that's the same thing as the integral from a to b of f of q of phi of t times the norm of q composed with phi prime of t dt. I think it's easier to understand what this expression means if I write everything in terms of components, even though it's a little bit messier. So I'm going to write R of t in terms of components R1 of t, R2 of t, and I'll write Q of W in terms of Q1 of W, Q2 of W. I'm assuming here that we're working in R2 to keep things simpler. Now, Q composed with phi of t is going to be Q1 of phi of t, Q2 of phi of t. And so if I take the derivative, Q composed with phi prime of t, that's just the derivative of each component. I can expand this out using the ordinary chain rule of calculus 1 to be q1 prime of phi of t times phi prime of t, and q2 prime of phi of t times phi prime of t. The reason I took the derivative is because I'm trying to get an expression for this normed component in terms of coordinates. So let me take now the norm of this expression, which I get by taking the square root of the squares of each component. Now each of these terms is going to have a phi prime squared in it. So I can factor out the phi prime squared and take the square root of it. The square root of a squared is given by the absolute value of phi prime of t, and I'll carry over the rest of the expression. So now I have a way of writing this normed expression in my line integral in terms of components, and I'll just plug this formula into my line integral. Remember, we're trying to show that the line integral with respect to arc length doesn't depend on parameterization. So I need to make this expression here look like the expression I'd get with using the parameterization q. And to do that, I'm going to perform a simple u substitution and set u equal to phi of t. So we have u equals phi of t, and du is phi prime of t dt. Now if phi prime of t is greater than 0, then the absolute value of phi prime of t is just the same as phi prime of t. And so a u substitution is very easy, and I can rewrite my line integral as the integral from u equals phi of a to u equals phi of b of f of q of u times the square root of q1 prime of u squared plus q2 prime of u squared times du. Now recall that phi prime of t being greater than 0 corresponds to the case when phi of a is equal to c and phi of b is equal to d. Both parameterizations are going in the same direction. So my integral is the integral going in the direction from u equals c to u equals d, which is the usual way to do an integral because c is less than d. And so this line integral is by definition the line integral of f with respect to arc length using the parameterization q. So we've proved that the line integral doesn't depend on parameterization, at least in the case that phi prime of t is 0, in the case that the parameterizations go in the same direction. But we still need to consider the case when the parameterizations go in opposite directions. So we need to consider if phi prime of t is less than 0. In this case, the absolute value of phi prime of t is equal to the negative of phi prime of t. And this is the case also in which phi of a is equal to d and phi of b is equal to c because our parameterizations are going in opposite directions. So when I do the u substitution, I get almost the same thing as before, but I get a negative sign in front of my du because of replacing the absolute value with the negative when I get rid of the absolute value signs. And instead of the order from c to d, I'm going to be integrating from d to c. So let me write that down. But notice that I'm integrating now from d to c, where d is bigger than c. So let me rewrite this in the usual direction of integration. So we go from a smaller number c to a bigger number d. Of course, that introduces an additional negative sign, which cancels with this negative sign and makes my integral positive again. So once again, even when the case when parameterizations are in opposite directions, we still are left with an expression that's exactly equal to the integral of f ds using the parameterization q. So the parameterization does not affect the value of the line integral with respect to arc length, even if we go in opposite directions. Now, of course, if we were to write down our integral and decide to be contrary and integrate with going from like 2 to 1 instead of 1 to 2, then of course our integral would be the negative of what we got. But as long as we're integrating from a smaller bound to a larger bound, our integrals with respect to arc length will always come out the same no matter what the parameterization. Next, let's look into line integrals with respect to x or y. The situation is very similar in this case, except now, if our two parameterizations go in opposite directions, then our line integrals will be the negatives of each other. In other words, if r of t is one parameterization of the curve c and q of w is another parameterization of c, then the line integral with respect to x will have the same value using either parameterization as long as both parameterizations traverse the curve in the same direction. And otherwise, if they traverse the curve in opposite directions, we'll write that the integral going one way of f dx is the negative of the integral going the other way, where negative c means the parameterization goes in the opposite direction. To prove this theorem, we'll again start out using the reparameterization formula, so we know that r of t is q of phi of t for our reparameterization function phi. We'll also write out what it means to be the line integral of f with respect to x using the parameterization r. That means we integrate from t equals a to t equals b f of r of t times r1 prime of t dt, where r is broken up into components as r1 of t, r2 of t, and q also is broken up into components as q1 of w, q2 of w. Now let's use the reparameterization formula to re-express this integral in terms of q and phi. So we have the integral from a to b of f of q of phi of t times q1 composed with phi prime of t dt. We can use the ordinary chain rule of calculus 1 to expand this out as q1 prime of phi of t times phi prime of t dt. Now this integral is practically begging for u substitution using u equal to phi of t and du equal to phi prime of t dt. When I make those substitutions, I get the integral from u equals phi of a to u equals phi of b, f of q of u times q1 prime of u du. Again, let's consider two cases. In the first case, we have phi prime of t is bigger than 0. That corresponds to phi being increasing and phi of a equals c and phi of b equals d. So we can rewrite our integral as u equals c to u equals d of f of q of u, q1 prime of u du, which is exactly what's meant by the line integral of f with respect to x using the parameterization q. Note that c is less than d, so we're integrating in the normal ordinary order. Suppose, on the other hand, that phi prime of t is less than 0. We now have a situation where our two parameterizations are going in opposite directions. In this case, we've seen that phi of a is d and phi of b is c. So when I rewrite my integral, I have the integral from d to c of f of q of u, q1 prime of u du. Now we're integrating in the wrong order, and in order to return this to a more normal expression, we have to switch the order of integration, which introduces a negative sign. So now we have an expression that's same as the line integral over c of f dx with respect to q, except it's actually the negative of that line integral. So using a parameterization that reverses the direction of traversing c gives us a negative sign here. And the two integrals aren't exactly the same, they're the negatives of each other. This completes the proof for the line integrals with respect to x, and the line integrals with respect to y are similar. Finally, let's look at line integrals of vector fields. Here, the situation is similar to line integrals with respect to x and y. If we have two parameterizations, r and q, then the line integral of the vector field dr is the same as the line integral of the vector field dq as long as R and Q traverse the curve in the same direction. Otherwise, we have that the line integral of f dr is going to be the negative of the line integral f dq, and I'll signify the fact that the q is going in the opposite direction, again with the negative c. You'll be relieved to see that the proof of this is very easy. If we write f in terms of components, so it's p I plus q j, then the line integral f dr is really just going to be the integral of p dx plus q dy, where dx and dy, of course, are expressed in terms of r1 prime of t dt and r2 prime of t dt. They're expressed in terms of r. We've seen that that's the same thing exactly as the line integral of p dx plus q dy if we use q as long as r and q are in the same direction. So therefore, it's the same thing as the line integral of f dq, just by writing things in terms of components. And for the same reason, we know that f dr is going to be the negative of f dq if the parameterizations are going in opposite directions, just because of that exact same fact for line integrals with respect to x and with respect to y. That completes these proofs that line integrals don't depend on parameterization, except for parameterizations that go in opposite directions, that introduces a negative sign. In this video, we saw that the integral with respect to arc length does not depend on the parameterization. The integral of a function with respect to x or with respect to y and the integral of a vector field don't depend on parameterization either, except that if you parameterize in the opposite direction, you get the negative of the original integral. I proved these results only for curves in R2, but the exact same proofs work for curves in R3 or any Rn. These facts about reparameterization will come in handy when we study Green's theorem and other theorems concerning line integrals. This video gives a definition for closed curves in the plane and the definition for simple curves in the plane. And it puts these two definitions together to give a definition for simple closed curves in the plane. A curve C is called closed if its initial point and terminal point coincide. So this first curve is not closed because its initial point and its terminal point do not coincide. The second curve is also not closed. But the third curve is closed and the fourth curve is closed. No matter how you parameterize it, the initial point, say I start here, then I would also go all the way around and end in the exact same place. So the initial point and final point coincide. A curve C is called simple if the curve does not intersect with itself, except possibly at the endpoints. So the first curve is simple. It doesn't intersect itself. But the second curve is not simple because it does intersect itself right here. The third curve is simple, and the fourth curve is not simple because of the self-intersection right here. Please pause the video and decide which of these curves are closed and which of them are simple. Curve A is closed but not simple because it intersects itself. Curve B is not closed. It has distinct initial and terminal points, but it is simple. It doesn't intersect itself. Curve C is not closed and not simple. Curve D is closed but not simple. Curve E is closed and simple. And curve F is not closed and not simple. One last definition. We call a curve a simple closed curve if it's a curve that's both a simple curve and a closed curve. So if you look at the curves drawn above, there is one simple closed curve. See if you can find it. If you said E, you're correct. This video defined closed curves and simple curves and simple closed curves in the plane. This video defines open, connected, and simply connected regions of the plane. Informally, a region D is called open if it doesn't contain any of its boundary points. A region D is called closed if it contains all of its boundary points. In the figures below, the first region, I'll call it A, is open. It doesn't contain any of its boundary points. The dotted line here means the edge or boundary is not included. The second region, B, is also open. It doesn't contain any of its boundary points either because of that dotted line. The third region, C, is also open. The next region, which I'll call D, is not open because it contains its boundary points. That's what that solid line means, that the edge or boundary is contained in the region. In fact, since D contains all of its boundary points, we say that D is closed. Similarly, the next region, E, is closed because it contains all of its boundary points. This final region, F, contains some of its boundary points, but not all of them. It can't be closed because it doesn't contain all of its boundary points, but it can't be open either because it contains some of its boundary points. So F is an example of a region that is neither open nor closed. A region D is called connected if any 2 points in D can be joined by a path in D. For example, this region on the left is connected because any 2 points in D can be connected by a path that lies entirely in D. The next region is also connected. If I pick any 2 points, I can always get from one to the other by a path that lies entirely in D. In fact, there may be several such paths. This third region, however, is not connected because it's divided into 2 pieces or components. And if I take a point in one of the pieces and a point in the other, there's no way to connect them with a path without going outside of my region D. Our next and last definition is simply connected. A region D is called simply connected if every simple closed curve C that you can draw in the region D encloses only points of the region D. Informally, simply connected means no holes. Let's look at some examples. This first example is simply connected because any simple closed curve that I can draw in the region will only enclose points of the light blue region. The second region is also simply connected. Even though it has 2 components, any simple closed curve that lies entirely in the region will only enclose points of the region. This next region, which looks like an O, is not simply connected. That's because if I draw a simple closed curve that goes around the O, it will enclose points that don't lie in the region. Similarly, this last region is not simply connected. Again, if I draw a simple closed curve that surrounds one or both of the holes, then that simple closed curve will contain points in the holes that are not in the region D. Please pause the video for a moment and classify each region. Decide if it's open, connected, and simply connected. The first region is open because it doesn't contain any of its boundary points. It's also connected because it just has one piece, and it's simply connected because it doesn't have any holes. The second region, B, is not open because it contains some of its boundary points. In fact, it contains all of its boundary points, so it's closed. It's not connected because it's divided up into 7 different components, but it is simply connected. It doesn't have any holes. And if I draw any simple closed curve that lies entirely in the region, it'll enclose only points in that light blue region. The last region, C, is not open because it contains some of its boundary points, but it doesn't contain all of them, so it's not closed either. It is connected, but it's not simply connected because it has two holes in it. And if I draw a simple closed curve around one of those holes, it'll enclose points that are shaded white and not just points that are shaded light blue. This video gave definitions for open, connected, and simply connected regions of the plane. These definitions will come in handy when we state precise conditions for vector fields to be conservative. This video states and proves a relationship between conservative vector fields and vector fields whose line integrals are independent of path. Although we'll restrict our attention to vector fields in 2 dimensions, all of the results will still hold for vector fields in 3 or more dimensions. Recall that a vector field f is called conservative if f can be written as the gradient of some function phi called its potential function. A continuous vector field f is said to have line integrals that are independent of path if, whenever you have 2 paths, C1 and C2, that start at the same place and end at the same place, the line integral f dr over C1 is equal to the line integral f dr over C2. In other words, it doesn't matter what path you take to get from point A to point B, the line integral will be independent of path. It'll be the same regardless. The continuous condition on the vector field here is thrown in so that these line integrals make sense. We've seen before that the fundamental theorem of line integrals says that you have a vector field that's conservative and it's continuous. Then the integral over any curve of f dr is just going to be phi evaluated at the end point, the terminal point, minus phi evaluated at the start point. And therefore, the line integral's value only depends on phi's value at the start and end point and won't depend on the path taken. Therefore, if f is a continuous vector field that's conservative, f's line integrals will be independent of path. In this video, I want to prove the converse. That is, that if f has line integrals that are independent of path, under suitable conditions, f will be conservative. So suppose that f is a continuous vector field on an open connected region D. Open means D doesn't contain any of its boundary points. For any point in D, there's a little disk around that point that also lies in D. Connected means that D is one contiguous piece, and in particular, for any 2 points in D, there is some path connecting them. So if f is a continuous vector field on an open connected region D, then if f dr is independent of path, this implies that f is conservative, i.e., f is the gradient of some function phi. So to prove this, let's assume f has line integrals that are independent of path, and let's build a function phi that f is the gradient of. If this is my region D, I'm going to start with some home base point, which I'll call x naught, y naught. I'm going to define phi at x naught, y naught to be 0, just to keep things simple. I could define it to be 13 if I wanted to, but we'll just define it to be 0 there. For any other point, xy in D, I'm going to define phi at xy to be the integral of f dr along a curve C, where C is any path from my home base point to my point xy. Since f has line integrals that are independent of path, it doesn't matter which path I take from the home base to xy, I'll still have the same line integral. Now, you may be wondering, where in the world did this definition of phi come from? But I want to argue that this is really the only way it's reasonable to define phi if we want any hope of f being the gradient of phi. Because if f is the gradient of phi, then by the fundamental theorem of line integrals, we'll know that the integral of f dr will have to be equal to phi of the endpoint minus phi of the start point, which is going to be phi at xy minus phi of x naught, y naught, my home base point, which is just phi of xy since I chose to set phi of x naught, y naught to be 0. So the only reasonable definition of phi is to actually make it equal to the integral of f dr over that path c, so that the fundamental theorem of line integrals will actually hold as it has to. But this little check of reasonableness here is not enough to guarantee that the phi we've defined really works. So let's go about now and make sure that it does work. Let's make sure that f really is the gradient of phi. So if I write f in components, say as little f, little g, I need to show that phi sub x is equal to f and phi sub y is equal to g. That will prove that my vector field is really the gradient of phi. Now to show that phi sub x is equal to little f, the first component of my vector field, I'm going to look at a point xy, and I'm going to take a small little disk around that point xy that lies within my region D. I know it has to exist because D is open. And then I'm going to take another point that's just a smidgen to the left of xy, so I'll call that point x1y. And I'm going to pick the particular path that goes first from x naught, y naught to x1y, and then it just goes directly right to the point xy. So this is my path C. I'll call it's made up of, say, a subpath C1 and this subpath C2, where C2 is completely horizontal. Now, by definition of phi, we know that phi is equal to the integral over C of our vector field f dr, which is the integral over C1 plus the integral over C2. So phi sub x is the derivative with respect to x of these integrals, which I can break up as the derivative of each integral separately. Now, as x varies, as I change this little point by moving its x, I'm not going to change my C1. I'm just changing my C2. And therefore, this integral is just a constant as x changes, and its derivative is 0. Let's write out what's going on with C2 in more detail. I can parameterize C2 by letting my x-coordinate just be t, where t ranges between x1 and my x, and my y-coordinate is just going to be fixed at y. So I'm taking the derivative with respect to x of the integral from t equals x1 to x of, I'll put f, capital F in components, fg, dotted with x prime of t, y prime of t, dt. Well, x prime of t is 1 and y prime of t is 0, since that y value on my path here is not changing. It's just a constant horizontal line. So this integral, the derivative of this integral is the derivative of fg dotted with 1, 0 dt which ends up being the derivative of the integral of just f, x of t, y of t, dt. But remember, x of t is just t, y of t is just that fixed y. And so we have something where we're taking the derivative of an integral of a function of one variable. And we know by the fundamental theorem of calculus, that's just equal to f with that bound of integration x plugged in. So we've just shown that phi sub x equals f, which is the first part of what we wanted to show. To show that phi sub y equals g, we use a very similar argument. This time, we fix a point x, y1 that's just below our point xy, and we make a path that first visits x, y1 and then goes straight up to xy. Again, I'll call this path C1 together with C2. So C equals C1 union C2. And we know that phi is defined as the integral over C of f dr, which can be broken up as the sum of integrals. And so phi sub y is the derivative with respect to y of these integrals. And once again, this first path is just fixed, not varying as y varies. So the derivative of that integral is the derivative of a constant, which is just 0. And we just need to worry about what happens with the second integral. We can parameterize C2. X of t is fixed at x, and y of t is just going to be t, where t ranges between y1 and y. So x prime of t will be 0, since x is fixed, and y prime of t will be 1. So if we write out our integral, it's going to be integral from t equals y1 to y of fg dotted with r prime, which is 0, 1 dt. So that's d dy of the integral of just g, x of t, y of t, dt, or the derivative of the integral of g of fixed x and y of t is t. Once again, by the fundamental theorem of calculus, the derivative of the integral is just the integrand with that y plugged in for t. And so phi sub y is just g, as we wanted to prove. So we have built a function phi such that phi sub x, phi sub y is exactly equal to the components of our vector field. In other words, our vector field f is a conservative vector field. It's the gradient of phi. That completes the proof. In this video, we showed that for a continuous vector field on an open connected region, if f has line integrals independent of path, then f is conservative. It's the gradient of some potential function. And we proved that by actually constructing the potential function by using line integrals. This video is about Green's theorem, a theorem that relates two kinds of integrals. Green's theorem relates a line integral over a simple closed curve, C, to a double integral over the region that C encloses. Recall that a simple closed curve, closed means that the curve starts and ends at the same point, and simple means the curve doesn't intersect itself. So a simple closed curve is the kind of curve that would enclose a region of the plane. Because the orientation of a curve affects the value of certain line integrals, when you switch the orientation of the curve, the line integral can switch from positive to negative. For that reason, we need to make a definition about orientation. A simple closed curve that forms the boundary of a region D is called positively oriented if, as you traverse C, the region always lies on your left. So if I draw the following region and the following boundary curve for that region, then if I want the boundary curve to be positively oriented, I need to orient it counterclockwise so that my region will always be to my left as I travel along this curve. If I were to orient it the other way, so that the region lies to my right as I travel around the curve, that would be negatively oriented. Sometimes a region might have several boundary curves. For example, a non-simply connected region like this one has 3 boundary curves. I'll call them C1, C2, and C3. In order for these boundary curves to be positively oriented, C1 has to be oriented counterclockwise, so the region will be to the left, but C2 and C3 had better be oriented clockwise so that the region, again, will be to the left as I travel around this curve. With those definitions out of the way, we can state Green's theorem. Let F be a vector field with components P and Q, and suppose that P and Q have continuous first partial derivatives. We're going to use the notation partial D to represent the positively oriented, piecewise smooth curve or collection of curves that bounds a region D. So smooth, a curve is smooth if it can be parametrized by a vector curve R of t such that R prime of t exists and is not 0. That prevents us from having cusps or corners in the inside of the curve, although we can still use a piecewise collection of smooth curves, so we can still have cusps or corners between the pieces, C1 and C2, for example. So we have a region D and a boundary that's positively oriented that we're calling DD. Although it may seem weird to use the partial notation for a boundary, we use it for derivatives in the past, there's actually a correspondence between taking boundaries of regions and taking derivatives of functions, so it's no coincidence here. Green's theorem is going to let us relate the line integral around the curve, boundary of D, to a double integral inside the region. We're going to take the line integral of our vector field, so that's the line integral of f dr, and that's going to equal the double integral of q sub x minus p sub y, where p and q, recall, are the components of the vector field f. Remember that we can write this line integral as the integral of p dx plus q dy. So another way to state Green's theorem is that the line integral around the boundary of p dx plus q dy is the double integral of the partial q sub x minus the partial p sub y dA. Recall the reason that f dr is equal to this expression is that we can write this as pq dotted with r prime, which is x prime, y prime, which is the same thing as p x prime of t plus q y prime of t dt, which is the same thing as p dx plus q dy, since dx is x prime of t dt and dy is y prime of t dt. That justifies that this second statement of Green's theorem is the same thing as the first. There are a few common alternate notations for this expression with the boundary of D. Instead of the boundary of D, we can just write C, where we assume C is the positively oriented boundary of D. Sometimes we write this line integral with a circle around it to help remind us that we're taking the integral around a closed curve. The reason we're making such a big deal about the boundary being positively oriented is because if we take the opposite orientation, the negative orientation, for a line integral, that's the negative of the original integral. So that won't be equal to the double integral like it would be if we were positive oriented. It would instead be the negative. So let's use Green's theorem to evaluate a line integral. The line integral given here, where C is the positively oriented boundary of the rectangle with vertices at 0, 0, 3, 0, 3, 4, and 0, 4. So that's this rectangle. And positively oriented means we go in this direction. I'll write this as the union of four curves, four smooth curves, C1, C2, C3, and C4. Now, of course, I could compute this line integral directly, just by parametrizing each of these four curves in terms of t, and then writing everything out and computing four integrals, one for each of the four curves. But it's actually going to be a lot easier to use Green's theorem. So remember that Green's theorem says that this line integral of p dx plus q dy is the double integral of q sub x minus p sub y. So this is our p here, gets multiplied by dx, and the q is the part multiplied by dy. So therefore, q sub x is the derivative of q, so that's just 2e to the x again. P sub y is the derivative of the p part with respect to y, that's e to the x. And so if we do the double integral of q sub x minus p sub y with respect to area element, that's the double integral of 2e to the x minus e to the x, which is the double integral of e to the x. Now, I can compute this dx dy or dy dx. It'll be pretty easy either way. I'll do dx dy. My x bounds are just going to go from 0 to 3. My y bounds are going from 0 to 4. So I'll compute with respect to x first. So the integral of e to the x is e to the x, evaluated between 0 and 3. That gives me the integral of, let's see, e to the 3 minus e to the 0. So that's going to be the integral of e cubed minus 1 dy. Integrating that, I get e cubed minus 1 times y between 4 and 0. And so my answer is 4 times quantity e cubed minus 1. Green's theorem made computing that integral super easy. In this video, we saw that if we have a region D and we positively orient its boundary, in this case its boundary consists of two curves, C1 and C2, then the line integral around the boundary of a vector field with components PQ, F, dr is equal to the double integral of the partial of Q with respect to x minus the partial of P with respect to y integrated over that region. This can also be written as the integral over the boundary of P dx plus Q dy is that double integral. This video gives a proof of Green's theorem, a theorem that relates line integrals to double integrals. Suppose that f and g are functions of two variables with continuous first partial derivatives. Let's let C be a positively oriented piecewise smooth curve or collection of curves that bounds a region R, which I've shaded in light blue. Positively oriented means that as I travel around each of these boundary curves, the region needs to stay on my left. So this outside curve needs to be oriented counterclockwise, but the inner curves need to be oriented clockwise so that the region still stays on the left as I travel around them. Piecewise smooth means that my boundary curves can be broken up into finitely many pieces such that each piece can be parameterized by some r of t that gives the x and y points on the curve such that r prime of t exists and is never zero. Under these conditions, Green's theorem says that this line integral over the curve C of f dx plus g dy is equal to a related double integral, where we integrate the partial of g with respect to x minus the partial of f with respect to y over the region R bounded by the curves. Recall that this notation, integral of f dx plus g dy, since this is a line integral over a curve, this really means that we take the integral of f, evaluated at x of t, y of t, times x prime of t dt, plus the integral of g of x of t, y of t, times y prime of t dt, where t ranges over the interval for the curve, and here again x and y refer to the components of the parameterization, so r prime of t is our x prime of t, y prime of t. To prove Green's theorem, we'll first prove some related results on special types of regions, and then we'll put those regions together to get Green's theorem on more general regions. The two special types of regions we'll start with are called type 1 and type 2 regions. Type 1 regions are bounded by curves at the top and at the bottom, but straight lines on the left and right sides. It's okay if one or more of those straight lines collapses to points. What's important is that the top and bottom curves can be written as y as a function of x. So here I'll write y as h2 of x, and this bottom one I'll write y equals h1 of x. So those curves have to satisfy the vertical line test. Type 2 regions are like type 1 regions turned sideways. So in this case we have the left and right side might be curves, and the top and bottom are going to be straight lines. Those straight lines again are allowed to collapse to points if we want them to. But in this case what's important is that the left and right curves can be written as x as a function of y. So I'll write x equals k1 of y for the left curve and x equals k2 of y for the right curve. So those curves need to satisfy the horizontal line test so that x will be a legitimate function of y on those curves. So our first step in proving Green's theorem is to show that if R is a type 1 region, then the integral over C of f dx is equal to the double integral over the region of negative df dy. Our next step will be to show that if R is a type 2 region, then the line integral of g dy is equal to the double integral of dg dx. The third step will be to put these together to prove Green's theorem for regions that are both type 1 and type 2. Here's an example of a region that's both type 1 and type 2. Since this curve here satisfies both the vertical and the horizontal line test, we can think of this as a type 1 region with curves on the top and bottom where y is a function of x and a vertical line on the left side. Or we can think of it as a type 2 region with curves on the left and the right where x is a function of y and a straight line on the bottom edge. After proving Green's theorem for regions that are both type 1 and type 2 regions, our fourth and final step will be to prove Green's theorem in general by putting together type 1 and type 2 regions into general shapes. Let's start with step 1 and a type 1 region. To compute the line integral of C f dx, we need to parameterize our curve, our boundary curve. So I'm going to break this boundary curve up into 4 pieces, call it C1, C2, C3, C4, and orient them positively with respect to the region. Now my line integral is going to be the sum of the 4 line integrals over these 4 different curves. I'm going to compute these line integrals one at a time. Let's start with C1. The easy way to parameterize it is to use the copycat parameterization, x equals t, y equals h1 of t. So x prime of t is going to be 1, and y prime of t is going to be h1 prime of t. So the integral over c1 of f dx is by definition the integral of f of x of t, y of t, times x prime of t dt. That goes from wherever t starts. So let's see, if our curve down at the bottom is starting at x equals a, that'll mean t will start at a. And if it ends at x equals b, that'll mean t ends at b. So substituting in, this is the same as the integral from a to b of f of t, h1 of t, times 1 dt. So that's my first integral. Let's next parameterize c2. Well, since that's just a vertical line, that can just be parameterized. X is always equal to b, and y can be equal to t. So I'm going to have x prime of t is 0, and y prime of t is 1. When I write out the integral, f dx, since x prime of t is 0, I'm just going to get 0 for this integral, and it doesn't matter. Next, let me parameterize c3. Actually, I'll parameterize negative c3, since it's a little easier for me to go from left to right. Then I can let x equals t and y equal h2 of t, where t goes from a to b again. So x prime of t will be 1, and y prime of t will be h2 prime of t. If I set up my integral, as before, over negative c3, I get the integral from t equals a to b of f of t h2 of t dt. Now this was the integral over negative c3, so the integral over c3 of f dx is going to be the negative. Finally, looking at c4, or maybe negative c4, I'm going to parameterize that with x equals a, y equals t. So x prime is going to be 0 once again. So when I set up that integral, since x prime of t is 0, I'll once again get 0 for my answer. That means that my integral over the whole boundary curve C is just going to equal the integral from t equals a to b of f of t h1 of t minus f of t h2 of t dt. That comes from this piece here and this piece here that has a negative sign in front of it. Now I want to show that my line integral equals the double integral of negative df dy. So let me clear myself a little space, and I'm going to be starting on the right side of this equation, that is computing the double integral over the region of negative df dy dA. Since we're working with a type 1 region, it's very natural to compute this integral going in the y direction first and then in the x direction. So then y is going to go between h1 of x and h2 of x, and x is going in between a and b, because remember we were calling this vertical line at x equals a and that one x equals b. So now by the fundamental theorem of calculus, if I integrate a derivative with respect to y and then integrate with respect to y, I just get the original, which is negative f in this case, evaluated at the bounds. The bounds for y are h2 of x and h1 of x. So that'll be at negative f x h2 of x minus negative f x of h1 of x, and then this is still integrated dx, where x goes from a to b. If I simplify a little bit, rearrange things, x equals a to b, I get positive f of x h1 of x minus f of x h2 of x dx. But that's exactly what I got when I did my line integrals. I'm just calling it t here and x here, but it's exactly the same integral, exactly the same answer. So my left side and my right side are in fact equal, and I've completed step 1. The proof of step 2 is almost exactly like the proof of step 1. So I invite you to pause the video and work it out for yourself. For step 2, we're going to start with a type 2 region. Let's say that this bottom side is at y equals c and the top side is at y equals d. Once again, I'll divide my boundary into 4 pieces, c1, c2, c3, and c4, oriented positively. And I'll get to work parameterizing my 4 curves. c1 will be parameterized by copycat parameterization, y equals t, x equals k2 of t. c2, which is at the top, will just be, I'll parameterize negative c2, and it'll just be x equals t, y equals d. c3, I'll parameterize negative c3 and use y equals t, x equals k1 of t. And c4, I'll parameterize with x equals t, y equals c. When I compute x prime and y prime for each of these parameterizations, I see that for c2 and c4, y prime of t is 0. So when I go about computing the integral of g dy, I'm going to get 0 in both these cases. For the integral over c1 of g dy, I'm going to get the integral of g of x of t, y of t, so that's k2 of t, t, times y prime of t, so that's 1 dt, where y and t are both going from c to d. When I compute the integral over negative c3 of g dy, that's going to be the integral. T is again going from c to d because t is just following y, and that's going to be g of x of t, so that's k1 of t. Y of t is t times y prime of t, which is 1 dt. So I get that the integral over the entire curve c of g dy is the sum of these, which is the integral from t equals c to d of g of k2 of t, t, minus g of k1 of t, t, dt. The negative sign pops in here because I computed this integral over negative c3, which means if I'd computed it over c3, I would get the negative of my answer. I've computed the left side of this equation. Now I need to compute the right side and make sure I get the same thing. To compute the double integral over the region of dg dx, dA, since it's a type 2 region, it's most natural to compute that in the x direction first, and then the y direction. So x is running from k1 of y to k2 of y, and y is running from c to d. Once again, fundamental theorem of calculus lets me rewrite the integral of this derivative by just going to the original function, g, evaluated at the boundary. So that's where x is k2 of y, and y is just staying where it is, minus g of k1 of y, because I'm plugging in k2 and ky for x, which is my variable that I integrated with respect to. Okay, so now I have exactly the same expression here as I got for my line integral here, just with written in terms of y's dy's versus t's dt's. And I am done with step 2 of Green's theorem. Fortunately, step 3 is super easy. For a region that's both type 1 and type 2, I have both step 1 and step 2's results hold. So I know that the line integral of f dx plus g dy is just going to be the sum of these two double integrals. And that's what Green's theorem says right here. So I've used these two statements to prove Green's theorem for regions that are both type 1 and type 2. Finally, let's do step 4 and prove Green's theorem for a general region like the one I drew previously. I'm going to take my region and divide it into a bunch of smaller regions in such a way that each of those smaller regions is both a type 1 and a type 2 region. I can do that by just drawing enough horizontal and vertical lines so that my remaining curvy lines are in segments that are all both satisfying the vertical line test and the horizontal line test. I'll label those smaller regions like R1, R2 through, say, Rn. And now my double integral over my entire region R of dg dx minus df dy can be written as the sum of those integrals over all these tiny regions. Now, since each of these regions is both a type 1 and a type 2 region, I can rewrite those double integrals as single integrals over the boundaries of these tiny regions. Single integrals, that is, of f dx plus g dy. But notice how the boundaries of these little regions, adjacent little regions, match up. Since we're going in the positive direction around that little region, and we're also going in the positive direction around that little region, their shared edge, that vertical line there, will be traversed twice. Once for the region on the right, say that's R4, and once for the region on the left, say R3, but they'll be traversed in opposite directions. For R4 will be going down, and for R3 will be going up. So the line integrals on that shared boundary, they'll cancel out from the two regions. And in fact, that'll happen for all the shared boundaries, which means all that's left in these line integrals, the only curves that we actually end up going around that don't cancel out is the original curve C, because those curves are not shared by regions on either side. So that means that this sum of integrals over here, the sum of line integrals, is actually just equal to the line integral over the original bounding curve C of f dx plus g dy. And we've proved Green's theorem for general regions. That completes the proof of Green's theorem. This video is about parametric or parametrized surfaces. Recall that a parametric curve r of t equals x of t, y of t, z of t gives the x, y, and z coordinates of points on the curve in terms of another variable, t. A parametric surface, r of uv equals x of uv, y of uv, z of uv, gives the x, y, and z coordinates of points on the surface in terms of two parameters, u and v. I've graphed the parametric surface given by this equation below. In this graph, the x-axis runs in this direction, the y-axis is back here, and the z-axis goes straight up. What curves do we get if we fix v to be a constant and vary u? For example, if we set v equal to 0, we get r of u0 is u cosine 0, u sine 0, 0, which simplifies to u 0, 0. That's a line that runs in the x direction with y and z equal to 0, so it's a line that goes along the x-axis. If instead we set v equal to pi over 4, r of u pi over 4 is u cosine pi over 4, u sine pi over 4, pi over 4, which simplifies to square root of 2 over 2u, square root of 2 over 2u, pi over 4. That's a line at constant height, pi over 4, and since the x-coordinate equals the y-coordinate, we're lying along the line y equals x at height pi over 4. So that looks like this line right here. Let's do one more. If we set v equal pi over 2, we get the following expression. That's 0u pi over 2. So it's a line that goes in the y direction at constant height pi over 2. So when we fix v to be a constant, we're getting these constant height lines that are going straight out from the z-axis, kind of like steps on our staircase. If instead we set u to be a constant, so let's set, for example, u equal to 0, then we get r of 0v, which is 0 cosine v, 0 sine v, v, so that's just heading up the z-axis. If instead I set, say, u equal to 1, I get r of 1v, so that's going to be 1 cosine v, 1 sine v, v. If I set u equal to 2, that's going to be 2 cosine v, 2 sine v, v. Both of those are spirals heading up the staircase. The curves of constant u and constant v are called grid curves. And they can be a good way to help identify or visualize a parametric surface. In the previous example, we were given a surface that was already parametrized. But sometimes we want to find a parameterization for a surface that's given to us in Cartesian coordinates. That is, we want to rewrite x, y, and z in terms of two new variables, u and v. One common way to do this is to use a copycat parameterization. That means we let two of our variables from x, y, and z just copy or equal u and v. In this example, it's natural to make y and z copy u and v, so I'll set y equal to u and z equal to v, although I could do them in the opposite order. That's because x is already solved for in terms of y and z, so now I can just write x in terms of u and v as x equals u squared plus v squared. So my parameterization, r of uv, is equal to u squared plus v squared, u, v. Since u squared plus v squared is my x, u is my y, and v is my z. But anytime I see a variable squared plus another variable squared, I start thinking about sine and cosine, like polar coordinates. And that gives another alternative way to parameterize this surface. So I'm going to set y equal to r cosine theta and z equal to r sine theta, and now I know that x, which is y squared plus z squared, is r cosine theta squared plus r sine theta squared, which simplifies to just r squared. Putting this all together, I have my parameterization in terms of r and theta is, let's see, x is just r squared, y is r cosine theta, and z is r sine theta. If I want to rewrite this in terms of u and v, which might be a good idea because having r mean two different things in two different places is a bit confusing, then I can just write this as, let's see, r becomes my u. So this is u squared, u cosine v, u sine v. In the first parameterization, the copycat parameterization, there were no restrictions on u and v. U and v could just be anything from negative infinity to infinity. In fact, I need all those values to cover the entire paraboloid. In the second parameterization, I only need r to range from 0 to infinity and theta to range from 0 to 2 pi to cover the whole surface. In other words, u, which is functioning as my r, is going to be from 0 to infinity, and v is going to go from 0 to 2 pi. As a final example, let's parameterize the hemisphere x squared plus y squared plus z squared equals 9 with y greater than or equal to 0. Since we only have y greater than or equal to 0, it's possible to solve for y and then use the copycat parameterization. We have y squared is 9 minus x squared minus z squared, so y is plus or minus the square root of 9 minus x squared minus z squared, but since we assume that y is positive, we only have the plus version. Now we can set x to copy u, z to copy v, and we have y is the square root of 9 minus u squared minus v squared. So this gives us the parameterization r of uv is, let's see, x is u, y is the square root of 9 minus u squared minus v squared, and z is v. It's a bit tricky to put bounds on my parameters u and v in this example. It's true, since we're talking about a sphere of radius 3, that u is between -3 and 3, and v is between -3 and 3, but I don't have that whole rectangle on the UV plane at my disposal for parameterizing the hemisphere. Instead, the projection on of the hemisphere onto the UV plane, which is the XZ plane, is really just going to be a circle of radius 3. So a better way to describe the domain for the parameterization is the set of UV such that u squared plus v squared is less than or equal to 9. The copycat parameterization works just fine for this example, but because we're talking about a hemisphere, it's also natural to use spherical coordinates. The spherical coordinates of a point are given by rho, phi, and theta, where rho is the distance of the point from the origin, phi is the angle from the positive z-axis, and theta is just the same theta as in polar coordinates. If we project the point onto the xy plane, then theta is the angle made to the positive x-axis. Recall the equations to convert between rho, phi, and theta and x, y, and z. We have x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. But we don't need all three of these variables, rho, phi, and theta, to describe a two-dimensional surface. We should only have two parameters. And in fact, since the radius of our sphere is always 3, our rho is always 3. And so we can use just phi and theta as our parameters and write x equals 3 sine phi cosine theta, y equals 3 sine phi sine theta, z equals 3 cosine phi. I'll put this in vector notation. Now to find bounds on my parameters phi and theta, notice that since I'm only looking at the hemisphere where y is positive, I'm over here, theta is just going to range between 0 and pi. Phi also ranges from 0 up here at the top of the hemisphere all the way to pi down at the bottom. If I prefer to write my parameters as u and v instead of phi and theta, I can just replace phi everywhere with u and theta everywhere as v. And that completes my parameterization. In this video, we talked about parametric surfaces, how to visualize them using grid curves, and how to parameterize them using copycat parameterization, polar parameterization, and spherical parameterization. Recall, in the spherical parameterization, we use spherical coordinates, but we set rho equal to a constant. It's also possible to use cylindrical coordinates to parameterize a surface. For example, a good way to parameterize an actual cylinder is to use cylindrical coordinates and set r equal to a constant. Which of these and other methods you use depends on the surface you're given. And in many cases, you'll have several options to choose from. In this video, we'll find a formula for computing the surface area of parametrized surfaces. Then we'll use the formula in an example. Suppose we're given a surface parameterized by the variables u and v, where u and v range over certain intervals of values. The equation for the parameterization, r, tells us how we get from the input variables, u and v, shown here on the uv plane, over to x, y, and z coordinates in space. We want to find the area of our actual surface, and we're going to do this by approximating the area of little patches of the surface and then adding up those patches. We'll get the patches on our surface by first creating little subrectangles in the UV plane by dividing the interval from A to B into a bunch of little subintervals in the U direction, and then dividing up the interval CD into a bunch of little subrectangles in the V direction. So each little subrectangle over here, I'll call its width delta U, and I'll call its height delta V. I'll call this lower left point U sub I, V sub j, where I is indexing my subintervals in my U direction and j is indexing my subintervals in my V direction. So I can say if they're like n subintervals in my U direction, I can say like I is between 1 and n, and j is between 1 and m, say. Let me also label the other 3 corners of my subrectangle. So this corner here has coordinates u sub I still, but v sub j plus 1 because it's moved up a bit. So I can also write that as u sub I, v sub j plus delta v, since each subrectangle has height delta v. If I want to label this corner, that's going to be u sub I plus delta u v sub j, since I've moved over by delta u in the u direction. And this corner I've moved in both directions, so that's u sub I plus delta u v sub j plus delta v. Let me color code the 4 edges of my subrectangle. My parameterization function takes this subrectangle to this patch of surface. I'll color its edges too. Notice that these edges don't necessarily need to be straight lines anymore. They might be wiggly curves. Let me blow up this picture a bit. So I've got 4 curves bounding a curvy, wiggly patch of surface. Let me identify the 4 corners of this patch of surface. This corner comes from ui vj under the parameterization function r, so its coordinates are given by r ui vj. This corner has coordinates r ui vj plus delta v. Here I have r of ui plus delta u vj, and here I have r of ui plus delta u vj plus delta v. Now I want to find the area of this patch of surface, but it's going to be a lot easier to find the area of the parallelogram that approximates the patch of surface. The parallelogram spanned by these 2 vectors. I'll call this vector A and this vector B, and I'll write down that the area of the patch of surface is approximately the area of the parallelogram spanned by A and B. Well, let me write down more information about A and B. You can get the components of A by subtracting the coordinates of its endpoint and its beginning point. So A is going to be r of ui plus delta u vj minus r of ui vj. I'm going to do a little trick here and divide and multiply by delta u. That doesn't change the value, but it does allow me to recognize this as a difference quotient as I move in the u direction but keep v fixed. In other words, this expression is approximately equal to the derivative in the u direction times delta u. This delta u remains. Similarly, if I write out B, its components are the difference of the coordinates of its endpoint and beginning point. So that's r of ui vj plus delta v minus r of ui vj. And I'll write it this time by dividing by delta v and multiplying by delta v, here I have a difference quotient where I'm changing in the v direction but holding the u direction constant. So that's approximately r sub v times delta v. Now the area of the parallelogram spanned by A and B is the magnitude of the cross product of A and B. And the magnitude of the cross product of A and B is the magnitude of the cross product of r sub u delta u cross r sub v delta v. If I pull out the scalars delta u and delta v, I get the magnitude of r sub u cross r sub v times delta u delta v. That's my best approximation for the area of a patch of surface. So to get the entire surface area, I'm going to add up all the areas of my patches from I equals 1 to n, j equals 1 to m. I'm adding up magnitude of r sub u cross r sub v, delta u, delta v. If I want my exact surface area, I'm going to let those patches get smaller and smaller. I'm going to let my n and m go to infinity and take the limit, and that's going to give me the integral of r sub u cross r sub v du dv, where u ranges between its bounds a and b, and v ranges from c to d. So now we have a formula for surface area for a parametrized surface. Although we've worked out this formula in the case where u and v range over a rectangle in the UV plane, the same idea works even if u and v range over some other region in the UV plane. In that case, we just have to write surface area equals the double integral over that region in the UV plane of r sub u cross r sub v dA. So this is a region in the UV plane. Now that we've got a formula for surface area, let's work an example. I want to find the area of the portion of the surface z equals xy that lies within the cylinder x squared plus y squared is 1. Let me start by parameterizing my surface. I'll use the copycat parameterization, x equals u, y equals v, z equals u times v. In vector notation, r of uv is u, v, u times v. Since I'm within the cylinder, x squared plus y squared equals 1, that means my u and v parameters range over the disk where u squared plus v squared is less than or equal to 1, since u and v just copycat x and y. Next, I'm going to plug into the formula for surface area, which is the integral of the magnitude r sub u cross r sub v du dv over the region of the UV plane that I need to integrate over. R sub u, by taking derivatives with respect to u, I get 1, 0, v. R sub v is 0, 1, u. And I'll compute the cross product as I times negative v minus j times u plus k times 1. The magnitude of the cross product is the square root of negative v squared plus negative u squared plus 1 squared. So that's the square root of u squared plus v squared plus 1. So I need to integrate that. The best way to do that is going to be to use polar coordinates. I'm thinking polar coordinates because I see a square root of u squared plus v squared here, plus the region that we're integrating over is circular. So I'm thinking of setting u to be r cosine theta and v as r sine theta. Converting my integral, I get the integral from r equals 0 to 1, because I've got a disk of radius 1. Theta is going to go from 0 to 2 pi. My square root of u squared plus v squared plus 1 is going to be the square root of r squared plus 1. And my du dv converts to r dr d theta. Now I can integrate this using a u substitution, although I'm going to call it a w substitution since u is already being used to mean other things in other places. So I'll set w equal r squared plus 1 dw is 2r dr, so 1/2 dw is r dr. When r equals 0, w is 1, and when r equals 1, w equals 2. So I can convert my integral, and I get the square root of w times 1/2 dw d theta. Since my bounds of integration are just constants, I can rewrite the integral of the product as the product of two integrals. The integral with theta in it, I'll say 1/2 d theta, and the integral for the w part, w to the 1/2 dw. Integrating gives 1/2 theta between 2 pi and 0 times 2/3 w to the 3/2 between 2 and 1. Plugging in my bounds of integration, I get 1/2 times 2 pi times 2/3 times 2 to the 3/2 minus 1 to the 3/2. So that's 1/3 pi 2 to the 3/2 minus 1 as my final surface area. In this video, we approximated patches of surface with parallelograms to get a formula for surface area, and used it in an example. This video defines divergence of a vector field in 3 dimensions. Informally, if the vector field F represents the velocity of a fluid, then the divergence of F at the point xyz represents the net flow from the point xyz. I've drawn 2 example vector fields below. These vector fields are drawn in 2 dimensions, and to calculate divergence we need a vector field in 3 dimensions. So what we're going to do is we're going to assume the vector field in 3 dimensions looks like this 2-dimensional vector field for each horizontal slice. So here's the equation for F. Notice that it doesn't depend on z. This would be the way the vector field looks at z equals 0, and it looks exactly like this when z equals 1 or 2 or 3. So I'd like to think about this vector field and decide if the divergence of the vector field at the origin is positive, negative, or 0. Notice that the arrows are all pointing horizontally inward and getting smaller and smaller as we go towards the origin. If I were to put some kind of net ball around the origin and look at the fluid is flowing into the ball. So there's net accumulation or net flow into the origin. That means that the divergence is going to be negative, because a positive divergence means the fluid is flowing out from the point. And here we're doing the opposite. We're flowing in towards the origin. So that's a negative divergence. For the second example, the arrows are going round in circles. So we're kind of circulating around the origin, but if I made my little ball of netting, there would be no net flow into or out of that ball around the origin. And therefore, the divergence of the vector field at the origin is going to be 0. Now that we've got an intuition for what divergence means, let's write down the mathematical formula. For a vector field F, written with components P, Q, and R, the divergence of F is defined as d dxp plus d dyq plus d dz of R. Often this definition is written with the shorthand notation gradient dotted with F, where the gradient is meant to be this d dx, d dy, d dz. Now the gradient operator is not really a vector, but this notation is really handy to help remember the definition, because if you now write the gradient dotted with F formally, and just write out the symbols without thinking too much, without worrying too much about what they mean, what they could possibly mean. If you just write it out formally and then do the sort of formal dot product kind of smushing together d dx times p, it's not really times, I guess it's of, d dy, smush that together with q, d dz, smush that together with r, you get the definition of divergence. So this notation you'll see a lot, and it really is a handy mnemonic to remember the formula for divergence. Notice that the divergence of F gives you a scalar quantity, not a vector. Let's think for a minute why this formula might give you a positive answer when the flow of a fluid is out from a point, and give you a negative answer when the flow of a fluid is into a point. If you have fluid flowing out from a point, kind of in a starburst kind of formation, notice that I'm making those vectors be really small near the origin, so the vector field will be continuous at the origin, and then they can get bigger as I go further out. Now if I look at d dx of p, that's the rate at which the x component of my vector field is changing as I increase x. If I look at these arrows over here, they have a positive x component, but that positive x component is getting bigger and bigger. So the x component of my vector field is increasing. In other words, d dx of p is positive. Similarly, if I look up in this direction, the y component of my vectors is positive and increasing, so d dy of q is positive. And if we imagine the starburst happening in the z direction too, as we go up in the z direction, the z component of our vectors will be positive and increasing, so d dz of r will be positive. Even if we look like along this direction, where the x components of our vectors are negative, and they're getting more and more negative as we go in the negative x direction, but of course d dx means you have to go in the positive x direction. So they're negative but getting less and less negative as I go this way, which means d dx of p is still increasing. So thinking about the intuition with a starburst, you can see that these, for a starburst fluid flowing out of a point, these three quantities should be positive, and you'll get a positive divergence. And a similar argument shows that intuitively that if you have a vector field kind of collapsing into a black hole center kind of thing, then you'll get a divergence that is negative, because your d dx of the x component will be negative, and so on for the y component and z component. So that's my explanation for why this formula agrees with our intuition for divergence as measuring the net fluid flow out from a point. So now let's use the formula for divergence to actually compute the divergence in the two examples we saw at the beginning. So remember, the divergence is the gradient dotted with the vector field. I'll write that out. And that means that I take d dx of negative x plus d dy of negative y plus d dz of 0. So that's going to be negative 1 minus 1 plus 0, or negative 2. And we do indeed get a negative answer, which agrees with our intuition from the first picture. Remember that our first picture looked like this, and we saw intuitively that it should have a negative divergence at the origin. But our formula is showing that it has a negative divergence actually everywhere. There's no dependence on x, y, and z here. And that actually agrees with intuition too, because if we stick sort of like our net bag anywhere else in the picture, then the arrows are bigger going into that circle than they are going out. So there's still a net accumulation of fluid flow, even if we are looking at a point that's not the origin. And net accumulation, or net flow into a point, means negative divergence. Now let's look at the second example. We want to compute the gradient dotted with f. That gives us d dx of negative 2y plus d dy of 2x plus d dz of 0. Well, that's just 0 plus 0 plus 0, which gives us a divergence of 0. Once again, that agrees with our intuition. Since this was a vector field where the fluid was flowing around but not into a net around the origin, I'll let you puzzle over your intuition for why the divergence is 0 at a point that's not the origin as well. In this video, we defined the divergence of a vector field f as the gradient dotted with f. If f has components p, q, and r, this means that the divergence of f is defined as d dx of p plus d dy of q plus d dz of r. We saw that intuitively, divergence of f at a point represents the net fluid flow from the point. This video defines the curl of vector fields in 3 dimensions. I'll start with an intuitive notion of curl. Let's suppose that F represents the velocity of a fluid. Then the curl of F at a point xyz represents the net rotation of the fluid around the point xyz. Curl is a vector, and the direction of the curl vector is the axis of rotation as given by the right-hand rule. And the magnitude of the curl can be thought of as the speed of the rotation. This will make more sense as we look at the 2 examples below. Notice that these 2 examples are drawn in 2 dimensions, but to apply the curl to a vector field, we need a vector field in 3 dimensions. So we're going to think of these as representing vector fields in 3 dimensions, where every horizontal slice of the vector field looks exactly like this. So here's the equation for the vector field. Notice that z is not written anywhere. So the vector field looks like this when z equals 0. It looks like this when z equals 1 or z equals 2, and so on. Notice also that the z component of the vector field is 0. So the vectors aren't pointing up or down out of their horizontal plane. They just point, in this case, sort of towards the center of their horizontal plane. So to figure out the curl around the origin, I'm going to think of putting a tiny little ball in my fluid. Now these arrows represent the motion of the fluid. They're pointing in towards the center. So they're pushing on the ball pretty evenly in every direction, which means the ball is not going to rotate. So in this example, the curl of F at the origin is going to be 0. No net rotation. In the second example, however, if we put a little ball at the origin in this example, the fluid is pushing it in this direction. So if I do my right-hand rule and curl my fingers in the direction of rotation, my thumb will point straight up in the direction of the positive z-axis. So the curl of F is going to be some number, I'll just say c times k. Once we have a formula for curl, we'll actually be able to work out what that number c is. But right now we're just giving a qualitative idea of curl, and the qualitative idea is, in this example, yes, the ball will rotate. It'll rotate counterclockwise. So the right-hand rule says the axis of rotation is in the positive z direction, or some positive number times k for the curl. The formula for curl is a little complicated. The easiest way to remember it is using this mnemonic that the curl of F is given by the gradient cross F, where the gradient is this operator that's written in vector notation, d dx, d dy, d dz. So if we take the cross product, we write out d dx, d dy, d dz, and then the components of our vector f, and we work that out as I times d dyr minus d dz q minus j times d dxr minus d dz p plus k times d dx q minus d dy p. I just wrote all those symbols formally without worrying too much about the fact that gradient isn't actually a vector, and that this doesn't actually really make any sense if you just sort of follow your nose and work it out formally and write down the symbols. You get the definition of curl. I'm going to rewrite this a little bit by distributing in the negative. So I'm going to write this as the curl of F is going to be equal to this expression. Notice that the curl is a vector, not a scalar. Let's use this formula to calculate the curl for the 2 examples that we saw in the pictures. So we want to take the gradient cross F, and that's going to give us I times d dy of 0 minus d dz of negative y minus j times d dx of 0 minus d dz of negative x plus k times d dx of minus y minus d dy of minus x. That simplifies nicely to 0i plus 0j plus 0k. In other words, we have the 0 vector. And if you remember, that agreed with our intuition for this example in which the vector field was going into the origin. Let's do another example. For the second example, if we compute the gradient cross f and work out the cross product, we end up with 0i plus 0j plus 4k. So just like we predicted for this vector field that was rotating counterclockwise, the curl or rotation axis should be in the positive k direction. And now we actually have a numerical magnitude for that vector. It has magnitude 4. Notice that in these two examples, the curl didn't actually depend on which point xyz we were at. I'll let you think about the intuition behind that. And I want to point out that in many examples, the curl will depend on which point xyz you're measuring it at. In this video, I gave a formula for the curl of a vector field as the gradient crossed with the vector field. And I gave the intuition that this measures the rotation of the fluid flow.